Hi there, welcome to the course. My name is Sharad Bodle and I'm a faculty of management at the Jones Graduate School of Business at Rice University in Houston, Texas. The course is a part of the Business Statistics and Analysis Specialization, and this specialization through these various courses aims to develop a robust and practical understanding of various aspects of business statistics using the popular software Excel. The spreadsheet software Excel is an industry standard, and getting to apply all these skills, the business statistics skills using the software, would go a long way in its applicability to the industry. It is a great source of pride and joy when students come back and tell me how they were able to apply these courses at their workplace. It also helps in iterating these courses and making them relevant to today's business. The course that you're taking will give you ample opportunities in applying these various statistical tools to a variety of business applications. I'm very passionate about teaching these courses. My own academic background is a very quantitative one. An undergraduate in engineering, an MBA in quantitative techniques, and finally a PhD from the Carnegie Mellon University in Pittsburgh. My own research deals with application of various statistical tools and quantitative methods to various issues and problems faced in the industry. In this lesson, we will be seeing some of the common methods of reading data into Excel, namely when the data is presented as a regular Excel file or it is presented as a text file where the text is delimited either by a comma, a tab, or a space. Before we can do any processing of data, we need to properly bring it into the software. We will look at two common input formats, namely the regular Excel data file with a .xlsx or .xls extension and text files with a .txt extension. Within the text files, we will further look at a comma separated data file, a tab delimited data file, and a fixed width data file. The data that we'll be using comes from a store in Canada selling office supplies online. The data consists of orders received by the store over a period of time and contains various variables associated with the order. Let us start by reading the Excel format data file. So let's open Excel and read this file. So if you click on the file store sales, which is an Excel file, Excel reads in the data file and notice the various variables are organized in these columns. The very first column is an order ID, which is the identification mark given by the store to every order received. The next column is the order date, the day on which the order was received. The format of the date is month, day, and then year. The priority of the order, the store attaches either a low priority, a medium priority, high priority, or a critical priority to every order, and some of the orders do not have any priority attached to them. The quantity of order, the number of units ordered, the total sales in terms of dollars, the shipment mode for the order, so the store ships the products either by a delivery truck, regular air or express air, the shipping costs involved in dollars, the province or state within Canada to which the order is to be shipped, the customer segment, the store classifies its customers either as individual consumers, small businesses, home offices, or corporate clients. The product category, there are three broad product categories: office supplies, technology products, and furniture products. The subcategory within the main product category. The container in which the order is shipped, it's either a small box, a medium box, a large box, a wrap bag, or a jumbo drum. And finally, the date of shipment of the product. Next, let us read the data into Excel when the data is presented in a text format, and in particular, a text format which is a comma separated format. So such a data, if you were to read in any of the text editors, this is how the file would look, or this is how the data would look. Notice the data is all arranged in one big row, these different rows of data there, and every data is separated by the other data by way of commas. Hence the name, a comma separated text format. So let's see how do we read this data into Excel. So let's open Excel, and we'll be reading the data in a text format, in particular a comma delimited format, the store sales comma delimited file. So when we click this file, Excel guides us through its text import wizard. And notice we need to choose the delimited option because we are reading a delimited file. So we choose the delimited option, do a next. And in particular, amongst the options of delimiters, since this file is comma separated or comma delimited, we'll choose the comma as a delimiter. Then do a next, and then do a finish. So notice the file or the data has now been read into Excel. But also notice that the column widths have been reduced. So to get back our original column widths, we select all the columns, do a double click on any of the column, and we get back our original column widths. Next, let us quickly see how do we read the data when the delimiter is a tab rather than a comma. So now the data is in a tab delimited format. So once again, the process is the same. Let's open Excel spreadsheet. Let's go to the file, store sales, tab delimited text. Click on it. Again, the text import wizard opens up. And since it's a delimited file, we choose the delimited option, do a next. But now notice amongst the set of delimiters, we'll choose the tab as a delimiter because this is a tab delimited data file. Do a next, do a finish. And once again, the file is all read into Excel. We'll rearrange the column widths by selecting all the columns, doing a double click on any of the column, and we get back our column widths all properly arranged. Finally, let's read the data when the data is presented in a text format, but now rather than being delimited by a comma or a tab, the data is in a fixed width text format. So once again, let's open an Excel spreadsheet and let's read the file. Let's click on the file, store sales, fixed width. Now notice, since the data is not delimited, but rather it's of fixed width, hence we need to choose the fixed width option there. So we choose the fixed width option, do a next. And now what Excel has done is Excel has put in these column separators. And we have an option to change or modify these column separators. So let's quickly glance from left to right, taking a look at these column separators. Notice the column separator for the shipping mode. We do not need this particular column separator, so we can remove it by double clicking on that. Further, we also do not need the column separator that Excel has put in for the product container. So we can remove that too. Do a next and then do a finish. So once again, the data is read into Excel and we can change the column widths to get back the data in its original format. This lesson deals with some basic data manipulation in Excel. We will see how to move across cells in a spreadsheet. For example, how to move from the top of a column to the bottom of that column, how to format cells, how to sort various columns in a spreadsheet, how to add levels to the sorting, how to hide some columns so that they are not visible, how to unhide them. Let's continue with a study of basic data manipulation in Excel. So let's open Excel and let's open the Excel data file, store sales. Now, how many orders are there in this data file? Or in other words, how many rows of data are in this file? So one easy way to find that out is to put your cursor on cell A1 and then press Control down arrow. So notice the file has 8,399 orders. Remember, the very first row is a header row. To go back to the very first cell, you press Control and the arrow up takes you to the very first cell. Also notice the sales column. Some of the sales values have decimal places in excess of 2. For example, that particular value has 4 decimal places. So if we wish to organize sales such that we only get to see 2 decimal places, so we select the column, do a right click, format cells, number, decimal places, 2 decimal places, do an OK. Now notice the decimal places, all the decimal places have been shortened or rounded off to 2 decimal places. Also, the file is not organized in any particular order. For example, notice the very first order has a 2011 date, the second order a 2010 date, third order 2012. So let's sort this data file in an increasing order of the date on which the order was received. Further, on a particular day, the store might have received many orders. So within a particular day, we'll sort it based on the dollar sales amount. And in particular, we'll sort it on a decreasing order of the dollar sales amount. So let's first select the entire data file. One easy way to do that is put your cursor in the very first cell, cell A1, press a Control, Shift, right arrow, then a Control, Shift, down arrow. So the entire data file gets selected. Then we click on Data, Sort. We wish to sort on the order dates. So we select Sort by order date. Remember, the order dates, the format of dates is month, day, and then year. The order of sorting, we want the oldest dates first and the newest later. Then after that, within a particular date, we wish to sort based on the sales dollar amount. So we'll add a level here. Check on sales. And sales, we wish to order, rather than ordering from smallest to largest, we wish to order it largest to smallest. Then do an OK. And also notice, since my data has headers, I need to make sure that the box which says my data has headers needs to be checked. And I press an OK then. So the file is now all properly sorted as per an increasing order date, and within a particular day, the orders have been sorted in a decreasing order of sales amount. Now, this data has many columns. If we wish not to see all the columns, we can hide some of the columns. For example, let's say if we wish not to see the product subcategory and the product container columns. So we can select the 2 columns, do a right click, do a hide, click on hide. So what it does is it hides the 2 columns, column K and column L. It does not delete them, it simply hides them. If we wish to unhide them, what we do is we select the 2 adjacent columns, do a right click, unhide. So it brings them back into the view. We will now see how to perform arithmetic manipulations in Excel. We will see how to enter a formula in a spreadsheet, to add a column, subtract them, divide and multiply them, how we can then copy and paste these formulas across the spreadsheet. Some arithmetic manipulation in Excel. Let's say in this data file store sales, we wish to calculate the unit price of an order. The unit price of an order is nothing but the sales amount in dollars divided by the order quantity. So let's insert a column next to sales, right click, insert, and let's call this column as unit price. The formula to calculate unit price is sales divided by order quantity. So we do a is equal to, and then select the cell E2, which is the sales amount. You could also type in E2, divided by the cell D2, which is the order quantity. So that gives us the formula for unit price. Then we do an enter and we get the price, unit price as $96.94. We can further copy this formula all the way down by selecting the cell and taking the cursor to the right hand bottom corner of the cell till you see a thin plus sign, and then do a double click. So notice the entire column gets populated by the formula for unit price. For example, $309.77 is the unit price for the order ID 37537, and so on. Next, let us calculate the total cost to the consumer. The total cost to the consumer is the sales plus the shipping cost. So once again, let's insert a column next to shipping cost. Insert, and let's call it total cost. So the formula for total cost is equal to the sales amount in dollars, which is cell E2, plus the shipping cost, which is cell H2. So this is the total cost for the very first order. And once again, we can copy and paste this formula all the way down by selecting that cell, taking the cursor to the bottom right hand corner till you see a plus sign, and then doing a double click. So we have the total cost column. Next, let's introduce a running serial number into this data file. Since the order ID is not organized as per any particular order, so let's insert a column next to before order ID and insert running serial numbers there. So let's call it serial number. The very first order gets a serial number 1. The second order, the serial number gets incremented by 1. So we do a is equal to, we type in a formula, is equal to the previous serial number, which is cell A2, incremented by 1, and then an enter. So we get the number 2. And now we can copy and paste this formula all the way down. So notice we have these running serial numbers which run from 1 all the way to 8,399, the total number of orders in the data file. One small point there, let's say for whatever reason you do not wish to copy the formula. That is, when you copy this last number 8399 to the next cell, you wish to copy the number 8399 and you do not want that number to be incremented. So what we do is, we select that cell, do a copy, right click copy, and then when we are pasting it to the next cell, we do a right click, and in the paste options, we choose the second option, which is pasting values as they are. So this would paste the particular value without the formula behind that value. So notice when I do a paste value, the number has not been incremented and the number remains the same. In this lesson, we will study how to format the headers or the column titles in Excel by freezing the very first row. We will also use the sum function to sum across a data range and the sum if function to selectively sum across a data range. We have the Excel file open, store sales. So this file contains data on sales made by a store in Canada which sells office supplies online. So to start, let's increase the zoom level of this file from 100% to 150%. So at the bottom right hand corner, we increase the zoom level to 150%. Next, notice that this file has headers. Every column has a header. So let's freeze that very first row. So what it will do is it will help us while we scroll down the file. So let's select the file, select the first row, go to view, freeze panes, freeze top row. So what it does now is it has frozen the top row. So as we scroll down, it's easy to see what that particular column consists of. We will now calculate the grand total sales made by the store
across all these time periods, which simply is the sum of all the sales in column E. So let us go at the bottom of this file by pressing end and then down arrow. So it takes us to the very last row of the file. Notice we still see the headers. So we still know that column E is the sales column. So let us calculate the sum of this particular column. So let me put down the title here, grand total sales, and that is nothing but the sum of column E. So the command to calculate the sum is equal to sum open parenthesis, then I select this entire column E. So one easy way to select that is put your cursor in the very last cell of that column, do a shift, control and up arrow. So it selects, notice down here it has selected all the cells from E1 through E8400. Now notice the very first cell E1 is a header cell, we don't really need that. So let's change it to E2. And then we close parenthesis. So this is the grand total sales made by the store during this time period. It's about $14.91 million. Next, let us calculate total sales broken up as per customer segments. This store categorizes its customers into 3 segments or 4 segments: the home office segment, the corporate segment, consumer segment, and small business segment. So let's calculate sales across these 4 segments. So I put down total sales, the corporate segment, total sales, the home office segment, total sales for the consumer segment, and total sales for the small business segment. Now to calculate total sales specifically for the corporate segment, we use the sum if command. So we do a is equal to sum if open parenthesis. Now this command requires 3 inputs. The very first input is the range which the if command refers to, which is nothing but column I. So let's select the entire column I. I put my cursor there, shift control up arrow. I really don't want it to start from I1, so I change it to I2. So that's my first input, the range which the if command refers to. Second input is the criteria. So within that range, I wish to sum up sales for the corporate segment. So I give a quotation mark, corporate, close quotation, then a comma. And the last input required is what particular column or what particular range needs to be selectively summed, which in our case is the sales column, which is column E. So I select the entire column E, shift control up arrow. Again, I don't need to start from E1, so I'll change it because E1 is my header. I'll change it to E2, and that completes my sum if command. Close parenthesis, and notice this is the sales during the entire period specific to the corporate segment. So this sales is about $5.49 million. We can also format these numbers by selecting them, doing a right click, format cells, choosing the currency format and choosing an appropriate format to put the commas in, doing an OK, and maybe increase the size of spread of the column. So it's been formatted as per the dollar format. We can follow the same process to get total sales for the home office, consumer and the small business segments. And you can confirm that the sum of sales for all the 4 segments taken together is indeed equal to the grand total sales.
In the following lesson, we will introduce how to enter formulas in Excel using absolute reference to a particular cell and also using relative reference to the cell. We will also introduce functions or formulas to calculate the maximum of a data range, the minimum of the range, to count the number of data elements in a particular range, to selectively count the number of data elements, and to use the power function in Excel, which is raising a number to a particular power.
In an earlier lesson, we had calculated the grand total sales for the store using the sum function in Excel, and we had also calculated the total sales broken up across the 4 customer segments using the SUMIF function. Now, we will calculate the percentage contribution of these customer segments towards the grand total sales, which is nothing but the total sales for that particular customer segment divided by the grand total sales. So for that, we simply divide the total sales, let's say for the first customer segment, corporate, divided by the grand total sales. We can also change the format of these numbers by selecting these numbers, right click, format cells, choosing a percentage format with 2 decimal places. Now, to calculate the percentage contribution for the other segments, the home office, consumer, small business, we can copy this formula for these other segments. So we do a copy. However, notice what happens if we copy and paste the formula. We get an error there. Why do we get an error? If you notice, the formula that has been copied, the numerator refers appropriately to the total sales for home office, but the denominator now has incremented, and rather than referring to the cell E8409, it refers to the cell E8410. So to prevent such kind of incremental copying, what we need to do is to go back to the formula, our original formula, and make some changes in the denominator so that when this formula is copied and pasted, the denominator always refers to the particular row, which is row 8409. Or in other words, we need to fix the row so that when this formula is copied, the row is not incremented. So we fix the row by putting a $ in front of the row. So now, if we copy and paste this formula, the formula has been properly copied, and the denominator, notice, is referring to, rightly is referring to the cell E8409. And this can then be copied for the other 2 segments also. So that's the contribution of these various customer segments towards the grand total sales. We will also introduce a few more Excel functions that are helpful in the study of business statistics, namely the max function, the min function, the count function, the COUNTIF function, the power function. So the max function, as the name suggests, calculates the maximum of a particular range. For example, if we wish to calculate the maximum of the sales across these 4 customer segments, we'll do a max, open parenthesis, select this data, and then close parenthesis. So it will give you the maximum sales among the set of those 4 sales. Similarly, the minimum sales are calculated as min, open parenthesis, selecting the range of data, close parenthesis. It gives you the minimum sales across the set of those 4 sales. Count, as the name suggests, counts the number of observations in a given range. So count, open parenthesis, you select the entire range, close parenthesis. So it counts the number of data points in that range, which is 4. COUNTIF extends the count function and adds an if statement to it. So for example, if we wish to count the number of sales across this set of 4 sales which are in excess of $3 million, so we will do is equal to COUNTIF, open parenthesis, we need to specify the range first. The range is the set of these 4 sales, comma, then we need to specify the criteria. And the criteria, as we mentioned, was sales in excess of $3 million. So we do apostrophe greater than 3 million, close apostrophe, and close parenthesis. So this is the command count if the sales in that specified range is in excess of $3 million. Do a enter. So it gives us the number 3, which is the power function is used to calculate powers of number. For example, if we wish to calculate 3 raised to the power 10, we would do is equal to power, open parenthesis, the number 3, comma, and the power which we want to raise it to, which is 10. So the answer is 59,049. We could have also calculated the same number by doing is equal to 3, then using the special hat character, and then the number 10. So 3 raised to the power 10.
In the lesson that follows, we will revisit the functions in Excel and specifically see the copying and pasting of functions or formulas using relative and fixed referencing.
We have been talking about functions in this course, and in some lessons we have also used them. Functions make Excel a very powerful software. So let us visit them again to emphasize their importance. The general format of entering a function in Excel is to put a is equal to sign, then you put in the function name, and then within parentheses you put in the arguments that the function takes. For example, if you wish to sum up the numbers in a spreadsheet in cells A1 through A25, so you would do a is equal to, then the function sum, then within parentheses you would type in the arguments that this function takes, which is the cell reference A1 through A25. Let us look at yet another example by opening the Excel file survey results. So this file contains data on opinions about a new dining facility on campus. A group of college students across 4 years, year 1, year 2, year 3, year 4, were surveyed on their opinions about a new dining facility on a college campus. Did they approve of the dining facility? Did they disapprove? Or did they have no opinion about the new dining facility? So in this table, we are provided with partial results of the survey. Why partial? Because in this data, we know the total number of students who approved of the dining facility, who disapproved of it, and who had no opinions. However, we do not know how this total number is distributed across the 4 years. Or in other words, how this number, how many of the 100 people who had no opinion, how many of them belong to year 1, how many of them belong to year 2, how many year 3, and how many year 4. On the other hand, another piece of information that we have is, we have the total number of year 1 students who participated in the survey, the total number of year 2 students, 180 students, total number of year 3, and total number of year 4 students. And now, given this information, we are tasked to fill in these empty boxes within the table, under the assumption that the year of a particular student is independent of his or her opinion about the dining facility. We begin by calculating the total number of students, which is nothing but the sum of the row totals, which also would be equal to the sum of these column totals. So let's enter the totals. Let's enter the function is equal to, then the sum, open parenthesis, and then we could add up the column totals C8 through F8, close parenthesis, enter. So the total number of students that participated in the survey was 600. Now notice that 200 is 1/3 of 600, or in other words, 1/3 of students who participated in this survey approved of the dining facility. So if we were to fill up these boxes in the first row here, we would expect that 1/3 of year 1 students approved of the dining facility, 1/3 of year 2, 1/3 of year 3, and 1/3 of year 4. Or in other words, the very first box would be 1/3 of 120, which is equal to 40 students. Now we could have also used a formula for that, and the formula for that is nothing but the row total multiplied by the column total divided by the grand total. So let's enter the formula is equal to the row total multiplied by the column total divided by the grand total, and which gives us the answer 40. To populate this entire table, we can now copy this formula and paste it across the entire table. However, before we copy and paste, we need to put in appropriate referencing in this formula. For example, if you look at this formula, the denominator is the grand total. And when we copy and paste this formula, we always want the grand total to refer to cell G8. So we need to fix the column G and row 8. So we do that by putting a $sign in front of G and a $sign in front of the numeral 8. In terms of the numerator, which is my row total multiplied by column total, when I copy and paste this formula across the first row, I always want my row total to refer to cell G5. However, when I'm copying and pasting this formula in the next row, I want my row total to refer to cell G6. And in the third row, I want my row total to refer to cell G7. So I do that by fixing the column G, because the column G always remains the same, but I do not fix the row. So this will allow a relative referencing of the row, but a fixed referencing of the column. And by the same logic, my column total, when I copy and paste this formula, I would want to fix the row by putting a $sign in front of the numeral 8, while I'll allow the column to be relatively referenced. So this puts in appropriate referencing in the formula, which is now ready to be copied and pasted across the entire table. So I give an enter here, and now I could select this cell and put my cursor at the bottom right hand corner of the cell till I see a small plus sign and drag it across the row. So this will copy it for the entire row, and this entire row I can then drag it down so that formula is copied across the entire table. And if you look at any cell, you would see that the formula has been appropriately copied. Row total multiplied by column total divided by grand total. And so is the case with all the cells. Row total multiplied by column total divided by grand total.
My name is Justin Mintzer. I'm a Rice MBA with over 10 years of experience in the industry, and I've been working very closely with Dr. Borlée to design and develop this course. Now, almost any company out there today uses Excel in some way, whether that's for a very basic spreadsheet for tracking or a much more complicated interactive program. And because of that, employees are expected to not only understand how to use these spreadsheets, but also understand how to create them. You absolutely will, at some point in your career, be asked to take a spreadsheet and mine through some data or organize some information. You have to be able to do that. Excel is no longer a nice-to-have skill on a resume. It's a business requirement.
In this lesson, we will introduce the if command or function of Excel. We will understand what it does, what is the syntax of this function, and then we'll apply it to text data using a data file.
The if command in Excel, also known as the if statement, is a very useful command, and its proper usage can make data analysis in Excel a lot more productive and fun. Let us see the syntax of the command. So the syntax begins with the word if, so is equal to if, open parenthesis, and the syntax takes in three inputs. The very first input is the logical test, that is the condition that you wish to evaluate, based on which you would take subsequent decisions. So that is the logical test, the first part of the syntax, the first of the three inputs. The next input it takes is, based on evaluating this logical test, what should you do if the logical test turns out to be true? Or in other words, what action do you need to take, or what value you need to put in if the logical test is true. So that is the second part of the syntax, value if true. The last part of the syntax, the last input that the if command takes, is what action do you need to take, or what value you would put if the logical test turns out to be false. So that completes the syntax of the if command. So once again, you begin with an is equal to if, open parenthesis. The first part of the syntax is the logical test that you wish to evaluate, comma, what action or what value you need to put if that logical test turns out to be true, comma, finally, what value or what action you need to take if that logical test turns out to be false, close parenthesis. Let's look at it by way of an example. So let's open our Excel spreadsheet and let's go to the file store sales. This file we have been using in various lessons, and this contains sales data from a store in Canada that sells office supplies online. Amongst the many variables that this file has, one of the variables is the order priority. So every order that this store receives, it attaches a priority to that order, either a low priority, a medium priority, a high priority, a critical priority, or sometimes the order does not get any priority. So the priority is not specified. So these are 5 categories of priority that the store attaches to every order. Now let's suppose the store wants to categorize the order priority rather than across these 5 categories. It wishes to have only 2 categories, and in particular it wants to give a 3-star order priority if the order is of critical importance, that is the priority is critical, and in all other cases it wishes to give a priority of a single star. So that is to say, if the order priority is either low, medium, high, or not specified, the order gets a priority of a single star, and if it's critical, it gets a priority of 3 stars. So let's see how we can use the if command to achieve this. So we insert a column where we'll put in our new variable. So I select this column, do a right click, insert. So a new column is inserted. Let me increase the width of the column. So I would give some heading or title to this column. Let me call it priority star rating. So I'll give either a star rating of 3 or a star rating of 1 to that particular order. And now we'll use the if command to implement our rule. So I begin with an is equal to sign, then the word if, that starts my if command, open parenthesis. If command takes in 3 inputs. The very first input is the logical test, the condition that I wish to evaluate. In my case, it is the condition or the test whether or not the order priority in column C is equal to critical or not. So my logical test is whatever is in the cell C2, if that is equal to critical. Now since critical is textual data, I will enclose it in quotation marks. and then close quotations. So the logical test is if whatever is in cell C2, if that is equal to critical, quote unquote critical, comma, then the second part of the syntax, what do I do if this condition is met? That is, if the order priority is indeed critical, what do I wish to do? And as per my rule, I wish to put in 3 stars there. Again, the 3 stars is textual data, so I will enclose it within quotation marks. Open quotations, I put in 3 stars and close quotations, and then a comma. So now I come to my third input of the syntax, which is what do I need to do if the order priority is not critical? That is, it is something other than critical. And as per my rule, I wish to put a single star there. So a quotation and a single star, close quotation. So that finishes the 3 inputs of my if command. So I close parenthesis and do an enter. So now, since the order priority for the very first order in this file is a low priority, so as per my rule, the priority star rating should be a single star. Let me now copy this formula and paste it in the next cell. So I can select this cell, take my cursor to the bottom right hand corner till I see a thin plus sign and drag it down. The second order has a high priority. Again, as per my rule, the priority star rating would be a single star rating. Again, I copy it down. Again, the not specified order priority should get a single star rating, which it does. When I copy it again, in this case, since the order priority is critical, so as per my rule, I should be getting a 3-star priority star rating, which is what the formula does. And I can copy and paste this formula all the way down in the entire file by taking my cursor till I see a plus sign and then doing a double click. So this copies and pastes the formula in the entire column. In this case, whenever the priority is critical, the priority star rating is 3 stars. In all the cases, when the priority is either low, high, medium, or not specified, all these cases have a single star rating.
This lesson is a continuation of our study of the if function of Excel. We will now be applying the if command or function to numeric data as contrasted to textual data that we applied it to in the previous lesson.
Continuing with our study of the if statement, we will now apply it to numeric data as contrasted to textual data that we have been applying it to. So this file which we have been using, stores sales, also has data on the dollar sales amount of that order. So some of the dollar sales amount are in excess of 2 decimal points, but we can easily round it off if we want to. So this column, what we'll do is we will tag these orders, and specifically we'll put a tag of 1 if the order is in excess of $1,000, and we'll put a tag of 0 if the order is equal to 1,000 or less than $1,000. So we'll do that using the if command. So to begin, let's insert a column next to sales. Do a right click, insert. Let me extend this, let me increase the width of this column. And let me name the column as sales. Since we are tagging sales in excess of $1,000, sales in excess of $1,000. So the syntax of the if command is equal to if, open parenthesis, if the sales amount in the previous column, which in this case cell F2, if that is equal to greater than $1,000. So if F2 is greater than $1,000, notice I'm not putting 1,000 in quotation marks since 1,000 is a numeric data, comma. So my second part of the syntax, what do I need to do if it's greater than $1,000? I need to put a tag of 1. Again, since 1 is a numeric data, I do not enclose it in quotation marks, comma, the last part of the input. If it is not in excess of $1,000, I'll put a 0 there. And that completes my if statement. So I close parenthesis, press and enter. So since this particular order, which is $390.20, is not in excess of $1,000, I get a tag of 0. I can copy and paste this formula all the way down. And in this case, I get a 1 whenever the order is in excess of $1,000. And whenever the order is less than or equal to $1,000, I get a tag of 0. So the important consideration in using the if statement in such situations is that I do not enclose the numeric data or the numeric numbers that I put in within quotation marks.
In the following lesson, we extend our usage of the if command in Excel by nesting another if statement within an existing if command. In other words, creating a nested if command. We then apply this to an existing data.
Let us see how we implement the nested if command in Excel. So the nested if command uses the same syntax as the if command. It starts with a is equal to if, open parenthesis, then the logical test that you wish to test. Then based on that test, if that test is true, what value do you want to put? Value if true, a comma, and then the third input is the value that you wish to put if that logical test is false. However, what makes it a nested if command is that now instead of putting in a value if the logical test is false, or for that matter if it is true, we would replace it with yet another if command. So in this case, for example, we'll replace the value if the logical test is false with a if command. So if command replaces the value if false. So now we have an if command, a logical test. Based on that logical test, we put in a value if that logical test is true. And if in case that logical test is false, rather than putting in a value, we execute yet another if command. So that is what makes it a nested if command. Let us illustrate this by way of an example. So if we open our Excel spreadsheet and open the data file store sales, this file contains sales data from a store in Canada that sells office equipment online. In an earlier lesson illustrating the use of if command, we had looked at one of the columns, the order priority, and recategorized that column using the if command. So in our data, order priority takes in 5 categories: low, medium, high, critical, not specified. So instead of categorizing them in these 5 categories, we had recategorized them into 2 categories. So whenever the order priority was critical, we had given it a 3-star priority, and in all other cases we had given it a single-star priority. Now let us extend that. So now instead of having just 2 categories, we'll recategorize them into 3 categories. So we'll give a 3-star priority star rating whenever the order priority is critical. Whenever the order priority is high, we'll give it 2 stars, and in all other cases, low, not specified, or medium priority, we'll give it a single-star rating. And we'll use a nested if structure to implement this. So let's insert a column, extend or increase the width of that column, give it a title, priority star rating, start implementing the nested if structure. So we begin with is equal to if, open parenthesis, if whatever is in the cell C2, which is the order priority column, if that is equal to quote unquote critical. So that's our logical test. If the order priority is critical, the value that we wish to put is a 3-star rating, and since star is a textual data, we enclose it within quotations, and so is critical a textual data, so that too is enclosed in quotations. Now if the cell C2 does not contain critical, that is, if the order priority is not critical, rather than putting in a single star as per our revised rule, we would execute yet another if command. And that is what the nested if structure is. So whenever the priority is not critical, we execute yet another if command. If now we test whether or not the priority is high. So we have already ruled out that the priority is critical, and that is the reason why in the first place the program execution would reach this particular point. And at reaching this point, since critical has been ruled out, we are now testing whether the order priority is high. So if again whatever is in cell 2 C2, if that is equal to quote unquote high, then put a 2-star rating, else comma put a single star rating. And this completes the nested if part, or so to say the small if part of the structure. So we give one more parenthesis to complete the entire nested if command. So once again, this command begins with an if statement. If the order priority, if it is equal to critical, then put a 3-star rating. Else, if it is not equal to critical, then execute yet another if command and test whether the order priority instead is equal to high. And if it is high, mind you, we have already ruled out critical. And if indeed it is high, then put a 2-star rating. Otherwise, put a single star rating. So a single star rating would be put in all the cases where the order priority is neither critical nor high. And then we close the command by these matching parentheses. And when we press enter, this gives you a single star rating. Why single? Because the order priority is neither critical nor high. Let me copy this command down. So my next order, since the order priority is high, and as per my rule, it should get 2 stars, the nested if structure indeed gives it 2 stars. Further copied down, again a single star. Further copied down, a 3 stars, because now the order priority is critical. And so the nested if structure seems to be working appropriately. I can copy and paste it all the way down. So that is how the nested if structure is implemented in Excel.
This lesson explores the lookup functionality of Excel. We introduce the vlookup or vertical lookup function, understand its syntax and situations where it is applicable, and then apply it and demonstrate it using data.
The syntax begins with a is equal to vlookup open parenthesis, and then it takes in 4 arguments or 4 values. 3 of them are required arguments, and the 4th one is an optional argument, and hence that's also put in square parenthesis. So let's understand these arguments by using an example in Excel. So we'll go to Excel and let's open a file, store sales, which we've been using across various lessons. So this file has data on sales by an online store in Canada selling office supplies. In one of the earlier lessons, what we had done was we had looked at the order priority column. Again, recollect that the store assigns a priority to an order. The priority could either be a low priority, a medium priority, high priority, critical, or sometimes there's no priority. So in an earlier lesson, we had recategorized this order priority and given them some priority star ratings. We had given them a 3 stars if the order priority was critical, a 2 star if the order priority was high, and in all other cases, a single star was given. We had done that by using the nested if functionality in Excel. We will now do something similar. However, we'll use a vlookup function. So let's insert a column here. Right click, insert. And give it a name, priority star rating. And since the vlookup function requires a lookup table, rather than putting the lookup table at some other place in the worksheet, let's say at the end of the worksheet or in some other different worksheet, for the purposes of illustration, let us put the lookup table right here next to the priority star rating column. So what I'll do is I'll insert a few empty columns so that I have my space to put up the lookup table. So I'll put the lookup table here. The lookup table, the very first column of the lookup table is the value that you wish to match in your data. So in our case, the order priorities, there are 5 categories of order priorities. So let's put all those 5 categories in the lookup table. So my first category is low, then I have medium, then high, critical, and one of the categories is also not specified. We need to be careful that we put in proper spellings there. The spelling should match the spelling that is there in our database. So that's the first column of my lookup table. Now based on these order priorities, when I recategorize the order priority in terms of star ratings, I wish to give a 3 star whenever the order priority is critical. 3 star whenever the order priority is critical, 2 stars whenever it is high, and in all other cases a single star. So this completes my lookup table. So the lookup table, the very first column is the value that I wish to match in my database, and the second column here is the value or the star rating that I wish to assign based on order priority. Now one important aspect of the lookup table is that the lookup table should be sorted in an ascending order based on the very first column. So let's do that. Let's sort this lookup table in an ascending manner based on the very first column. So I select my lookup table, go to data, sort. My data does not have headers, so I'll keep this box unchecked. And then I need to sort by the very first column, which is column E. And then I do an OK. So my lookup table now is properly sorted in an alphabetical manner, in an increasing alphabetical manner based on the very first column. Now I can execute my vlookup command. So I go to my cell D2 and type in the command is equal to vlookup open parenthesis. Remember, the vlookup command takes in 4 inputs, 3 of them are required and 1 is optional. So the very first input required is the lookup value. What do you want to look up? In my case, I wish to look up the corresponding star rating for the order priority low. So I want to look up low and attach it a corresponding star rating from the lookup table. So instead of typing low, I'll use the cell reference C2, comma. My next input is where is my lookup table? Where is the table array? So I select my entire lookup table. That's my second input. And before proceeding, remember that we'll be copying and pasting this vlookup formula all the way down. So to make sure that the referencing for the lookup table is always fixed, that is, whenever this formula is copied and pasted, the lookup table always refers to the place where it is. I would put the appropriate $signs to make sure that the referencing for this table remains fixed. We had talked about this dollar signs in one of the previous lessons, or how do we fix referencing versus how do we do a relative referencing when copying and pasting formulas. My next input is the column number which I wish to access in my lookup table once I have matched my lookup value in the very first column of the lookup table. So in this case, once I've matched it in the very first column, I wish to access the next column, which is column 2. So I put a value 2 there because my star ratings are given in the second column of the lookup table. My last input is an optional input where I need to put in either the word true or false. So putting the word false instructs the vlookup function that I need an exact match. That is, if exactly the word low is not found in the lookup table, the function would return an error. Alternatively, if I put a true there, Excel would look for an approximate match in the very first column of the lookup table. So in this case, I wish to do an exact match. So I'll put the word false there and close parenthesis. So that completes my vlookup function. As I press enter, I get a single star priority rating. Why? Because the vlookup function has looked up the low order priority, matched it in the lookup table, and picked up the corresponding star rating. Now I can copy and paste this formula all the way down. Before doing that, let me change the formatting of this column to a center aligned format. So I select this column, go to home, choose a center alignment. Now as I copy and paste this formula in the next cell, I get 2 stars. Why? Because the order priority high as per my lookup table has a 2-star priority. And I can copy and paste it all the way down. So what I've done is I've implemented a priority star rating using the vlookup function in the same manner as it was done in an earlier lesson using the nested if structure.
We further explored the use of vlookup function of Excel and apply it in a situation where we need to look up data in a table not in terms of an exact match but an approximate match.
Another vlookup example. In an earlier lesson, we had studied the vlookup function and worked through an example. Here we will work through another example using vlookup but in a slightly different manner. So let us open the Excel spreadsheet and then open the file store sales. So in our earlier example of vlookup, we had worked on this column order priority where we had recategorized the order priority into a priority star rating. We'll now implement vlookup in a slightly different manner. This file also has a variable called order quantity, which is the number of units that a customer orders. For example, the very first order, order ID 928, the customer ordered 26 units. So now the store has come up with a quantity discount scheme. I'll insert a few empty columns to put down the scheme. The scheme is as follows. For any sales from 1 quantity up to 10 not included, the store would give a discount of 1%. For quantities 10 through 20 not included, store would give a discount of 2%. 20 to 30, a discount of 3%, again 30 not included. 30 to 40, a discount of 4%. 40 to 50, a discount of 5%, and any quantity either 50 or in excess of 50, a discount of 6%. So this is the quantity discount scheme. Now we wish to implement this scheme. So we create another column and call it discount. And what we need to put in this column is an appropriate discount percentage. For example, for the very first entry, since the order quantity is 26, as per our quantity discount rule, this order quantity or this particular order is eligible for a discount rate of 3%. So we need to put in a 3% there. So we'll make use of the vlookup command and putting these discount percentages is equal to vlookup open parenthesis. The very first value is the lookup value. So I need to look up the order quantity, which in this case is 26. So I do a cell reference, cell D2, comma. Where do I look up this order quantity? I go to this order quantity discount table, the lookup table. Select this entire table. This is my lookup table. I need to look up the order quantity in the very first column of this lookup table. And based on finding that quantity in the first column of the lookup table, I need to output the appropriate discount percentage. So my column index number here would be column 2, because the number that I wish to output, the discount percentage, is in the second column of the lookup table, comma. And now I need to put a true or false. The default option, if I do not put any option, the default option is true. So what a false does is it tries to match 26, which is my order quantity, and do an exact match in the first column of the lookup table. And if it does not find an exact match, it would output an error. So clearly false, I do not want to put a false there. What does a true do? If I put a true there, it does an approximate match. What does an approximate match mean? It looks at the number 26, tries to find 26, it does not find 26. So the number that it finds is the number which is less than 26, closest to 26. So in this case, that is 20. So it would select 20, match it up with 20, and then output the corresponding number, which is 3%. Remember, it is important that this lookup table is sorted in an ascending manner based on the very first column. So that is what we want. When the order quantity is 26, it should be outputting the number 3.03%. So I put a value true there and close parenthesis. And that's what it does. It gives a discount of 3%. To be able to copy and paste this formula appropriately, I would put $signs in front of the table reference so that the table reference is fixed. When I copy and paste this formula, it always refers to that particular lookup table. Now I can copy and paste this formula all the way down. Notice, for example, this highlighted cells, the order quantity is 33, and as per our lookup table, the discount percentage should be 4, and that is what the case is. The advantage of such an implementation is, now let's say if the company decides to do some changes in the discount policy. So specifically for any orders between 20 and 30, rather than giving a discount percentage of 3%, the company decides to give a discount of 3.5%. So all I need to do is make a change in the lookup table, and correspondingly everywhere in the data file, the changes would automatically be updated. So that's the advantage of implementing this kind of a process using vlookup function.
This lesson introduces the hlookup function, also known as the horizontal lookup in Excel. We see its similarity with the vlookup function in terms of syntax, and we also see the difference in terms of looking up a table horizontally versus vertically. The function is illustrated using an example.
The hlookup function in Excel is very similar to the vlookup function. The only difference is that the vlookup looks up a table in a vertical manner, while an hlookup looks up a table in a horizontal manner. The syntax are also very similar. The syntax of an hlookup begins with a is equal to hlookup, takes in 4 inputs, which are exactly the same as the vlookup function. The only difference being that now, instead of a column index number, we have a row index number, which indicates the number of the row which needs to be accessed in the lookup table. Let's again see this by way of an example. Let's open our spreadsheet, the file store sales. This file we had in an earlier lesson used to illustrate the vlookup command, where we had recategorized the order priority into a priority star rating. So let's do that again, but now using the hlookup command. I'll insert an empty column. Give it a name priority star rating. And then I'll insert a few more empty columns to put in my lookup table. Insert. I'll reduce the column widths. And put my lookup table. Low, medium, so these are the order priority values. High, critical, and not specified. And the corresponding star ratings are, I give a 3-star whenever the order is critical, a 2-star whenever it's high, and in all other cases a single star. So this is my lookup table. Notice this lookup table is organized in a horizontal fashion. Why? Because we'll be using an hlookup command to look up this table. So let's put in the hlookup command is equal to hlookup, open parenthesis, what is my lookup value? I wish to look up the order priority, so I put the cell reference there, C2, comma, where is my lookup table? It's a horizontal lookup table. I select the entire table, and since I'll be copying and pasting this formula, I give a fixed referencing for the table by putting appropriate $signs. Row index number. So the hlookup command will access this lookup table, would access the very first row and try to match the order priority. Whenever it finds a match, which particular row do I need to access? So I need to access the second row from there because my priority star ratings are given in the second row. So put a number 2 there, comma, and I want an exact match. I do not want an approximate match. So put a false there. Close parenthesis, enter. So notice the priority star rating when the order priority is low is a single star. I copy and paste it down. I get 2 stars for a high order priority. The same can be copied all the way down. So now I have implemented the priority star rating using an hlookup command which looks up a table in a horizontal manner.
In the following session, we build a fun simulation for Professor Know-It-All using the vlookup function. The simulation enables the professor to call on students in her class at random.
Professor Know-It-All, who teaches an elective course, has approached us for help. She has a class of 20 students and needs an Excel-based simulation for her class. The names of those 20 students is in an Excel file, student names. Let us open that file. The name of the file is student names. So this file consists of 20 students who are attending Professor Know-It-All's elective course. So what she wants is, she wants a system whereby on a press of a button, she is able to call upon a student at random. So that she presses a button, the name of a student at random pops up in the spreadsheet. So then she can call on that student to come in front of the class and present the lesson. So we'll implement the system for her using the vlookup command. In conjunction with the vlookup command, we'll use yet another command called the ran_between command. This command takes in 2 inputs The first input is called bottom, the other top. So what this command does is, it generates a random number between the two numbers, the bottom and the top. We'll use this command inside a vlookup command to implement Professor Know-it-all's request. So we begin with an is equal to vlookup, open parenthesis, what is my lookup value? Now this is where we'll use the rand between command. My rand between command will generate a lookup value. Rand between, and rand between what two numbers? A random number between what two numbers? Since I have 20 students, serial number 1 all the way to 20, so my bottom and top numbers are 1 and 20. 1, 20. So my lookup value is a random number, an integer random number between 1 and 20. So that's the number that will generate. Then where do I need to look this value? My lookup table is this table here, the student name along with their serial numbers. So my vlookup command will generate a random number between 1 and 20 and go to this table. In the very first column of this table, match up the number generated, which is between 1 and 20, and then I wish to output the name which is in the second column of my lookup table. So I give a number 2 there. My column index number is 2. And it really doesn't matter whether I put a false or a true after that. So let me just put false, which is an exact match. And I close parenthesis. So once again, we look up a random number between 1 and 20, which generates the lookup value for this table. Now when I press enter, the vlookup command in conjunction with the rand between command picks up a name at random from the list of 20 names. And if I wish to generate further names at random, all I need to do is press the key F9 on my keyboard. So every time I press the key F9, the system would generate yet another name at random from the list of students in Professor Know-it-all's class. So what we have done is we have helped Professor Know-it-all implement what she wanted to do.
The business world is becoming more and more reliant on data, and data sets are becoming larger and larger. Being able to organize that data in a readable way is the first step in really understanding not just that data, but kind of the underlying important aspects of the business itself. Now there's a very big difference between just collecting lots of data and actually using that data in a meaningful way. And I think that's why there's been such a big focus on data organization at the business level and at the employee level as well.
In this lesson, we will read in a data file and prepare it for its use in subsequent lessons, where we will get to learn the filtering and pivot table functionality of Excel.
We go to File and open the file Summer Olympic Medals 1976 to 2008. So this file consists of all the medals received from the Montreal 1976 Olympics to Beijing 2008 Olympics. So the very first column, column A, is the city where the Summer Olympics were held, the year they were held in, the particular sport to which the medal belongs to, the discipline within the sport. For example, the sport aquatics may consist of diving, swimming, water polo, and so on. The specific event for the medal, the person who won the medal, the gender of the person who won the medal, the country to which the person belongs. The country is given in terms of 3-letter codes. The event gender, that is, that particular sport, that particular event, was it a men's event, a women's event, or was it a gender neutral event? And finally, the medal one, gold, silver, bronze. If you would notice, this file is not sorted in any particular order. So let's begin by sorting this file in an appropriate manner. So I select the entire first row, then do a Shift Control down arrow, and it selects the entire file. Notice this is a big file spanning across 15,317 rows. I go to Data, Sort, and then I'll sort by, notice I have headers as my first row, so I make sure my data has headers boxes checked. So I sort by year, that will be my first level of sorting, smallest to largest year. Then I'll add a level to the sorting. So add level, and after year I'll sort it by the sport. And within sport I'll sort it by discipline. So I'll add another level, discipline, and all from lower to higher order. I do an OK. And the file is now properly sorted. Year, then sport, and then discipline. This file, if you look at the bottom left-hand side, has more than one worksheet. Worksheets in a file can be thought of as pages. Just as you have many pages in a book, you can have many worksheets in an Excel file. This particular file has two worksheets. One worksheet, which is currently open and I'm looking at, is called middle list. The other worksheet is country codes. The advantage of having multiple worksheets is that it helps organize your data. For example, if you run a business, one worksheet could have all your sales data, the other worksheet could have your inventory data, the third worksheet could have your cost data, and so on. You could add more worksheets to the file by going to the worksheet tab and then doing a left click. So notice another worksheet has been added, sheet 3. If I do another left click, another worksheet has been added. I could also rename these worksheets by doing a right click and going to rename. I could rename it as my worksheet and so on. So that's how I could add worksheets. I could also delete worksheets. So for example, if I don't want sheet 4, I do a right click, delete. That worksheet is deleted. I could also delete my worksheet, which I have created. Right click, delete. So the second worksheet that this file has is called country codes. And this worksheet contains the country code, the 3-letter country code, and the corresponding country. We'll use this data to update data in our first worksheet, which is called middle list. Remember, with multiple worksheets, you could do calculations across worksheets. That is, a function or a command in one particular worksheet can access data in another worksheet. So let's go to middle list. And what we wish to do is, we wish to replace this country code with the actual country. So I insert a column here and call it country. Next, I'll use a vlookup function in Excel to look up the corresponding country which corresponds to this 3-letter code. And the lookup table is in the next worksheet, which is country codes. So I do a is equal to vlookup, open parenthesis, I wish to look up the country code, comma, where do I want to look it up? It's in my next worksheet. Remember, as I mentioned, functions and commands can work across worksheets. So I go to country codes, I select this data. So I select this data, which is the first column is the 3-letter country code. Next column is the corresponding country. Then I do a comma. So once my 3-letter code from the worksheet middle list is matched up to this lookup table, the very first column of the lookup table, I wish to read the next column. So I give a number 2 there because the second column from the very first column needs to be accessed. And I want a fixed reference, that is an exact match. Hence I give a false there, close parenthesis. And also, since I'll be copying and pasting this formula, I want a fixed referencing to this lookup table. So I insert dollar signs in my range reference. And now my formula is all ready. I do an enter. And the very first country is East Germany. I can now copy and paste it all the way down. So all the countries are now put in that column. This file is now ready for further analysis using the filters and pivot tables functionality of Excel.
This lesson introduces the data filtering capability of Excel. We will learn how to apply filters to a data file, and we will also learn how to then use those filters to selectively view data.
Data filtering capabilities of Excel, though very useful, are often underutilized. Here we will see how to use this facility in Excel. We will be using the Excel file that we used in the previous lesson, the file that contained data on Olympic medal winners. So let's go to Excel and open the file Summer Olympic Medals 1976 to 2008. So in an earlier lesson, we had used this file and inserted the country column in this file. Now we'll see how to apply filters to this file. So to do so, I put my cursor anywhere in my spreadsheet, then I go to data and click on this filter icon. This will enable filtering of the selected cells, or if no particular cell is selected, it will select the entire worksheet and filter the worksheet. So notice when I click on that icon, drop down boxes have been placed in the columns. So all the columns now have these drop down boxes. And what these drop down boxes are, for example, if you click on the drop down box for the column year, it contains all possible values of years that occur in that column. Similarly, if you click on the drop down box against city, all possible cities that occur in that column. And if you click on sport, all possible sports that occur in that column, and so on. So now I have applied filters to my spreadsheet. How do I use these filters? For example, let's say if I wish to see all the medals won by Japan. That is, I want to filter the spreadsheet so that only the medals won by Japan are shown. So I go to the country column, click on the drop down box there, click on the select all cell there, it deselects all the countries. Now I'll select Japan, scroll down and select Japan, do an OK. So notice a small icon appears here next to country, which tells me that some filter has been applied to this particular column, and the filter in this case is all medals won by Japan across these various summer Olympics have been listed there. Further, if I want to filter and I wish to see the medals won by Japan in the Sydney Olympics, which was year 2000. So I go to year and I deselect all the years and then select year 2000, which was the Sydney Olympics. Do an OK. So now this has been further filtered, all medals won by Japan in the Sydney 2000 Olympics. Further, if I wish to look at only the gold medals won by Japan in the Sydney 2000 Olympics. So yet another filter I'll apply. I'll go to the medal column, click on the drop down box, deselect all, and then select only the gold medal. Do an OK. So these were the gold medals won by Japan in the Sydney 2000 Olympics. So there were a total of 5 gold medals won by Japan. Even further filtering, if I want to find out the women who won gold medals for Japan in the Sydney 2000 Olympics, I click on the gender, deselect all and select only women. So there were 2 women who won gold medals for Japan in the Sydney 2000 Olympics. Note that it's not as if the data has been deleted. The data is still there, it's just that it has been filtered. And this is evidenced by looking at the row numbers here. The row numbers, there are big gaps in row numbers, which tells us that the data is still there, Simply, it's been hidden. If we want to unhide the data, if we want to unfilter the data, all we do is we go to data and we can click on clear. So it will clear all filtering that have been done to the data, and we get back our data in its original format. Another quick example, if we wish to find out which country won the maximum gold medals in boxing in the Sydney 2000 Olympics. So once again, what we do is we go to year, filter out all the years, select year 2000, do an OK, go to discipline, unselect all disciplines, select the boxing discipline, do an OK, go to medals, unselect all the medals, click on gold, do an OK, and these are all the gold medals won in the Sydney 2000 Olympics. And if you look at the countries, it seems Cuba has won the maximum number of gold medals in the Sydney 2000 Olympics. One final point, if we wish to remove the filtering capability from our spreadsheet, that is, if we wish to turn off the filtering mechanism, what we do is we go to data, and this filter icon currently which is turned on, we click it again, and this will turn off filtering from our spreadsheet. So now notice none of these columns have the drop down boxes next to them.
In the following lesson, we introduce pivot tables, a very powerful data summarization tool. We get an understanding of what a pivot table is and begin to construct one in Excel.
Use of pivot tables in Excel. So what are pivot tables? It is a data summarization tool which makes summarization and reporting of data flexible and easy. You can view data summaries in different formats, sliced and diced as per your requirements. Pivot tables are easy to create and use, and they are also dynamic. That is, as the data changes in your data file, the summary in the pivot tables automatically get updated. We will illustrate the use of pivot tables using examples. So let's open our Excel file. We'll open the Summer Olympic Medals 1976 to 2008 file. This is a file that we created in an earlier lesson. This file contains all the Summer Olympic medals and their winners from 1976 Montreal Olympics to 2008 Beijing Olympics. This is a big file. It has an excess of 15,000 rows. So given this big file, we'll use pivot tables to draw some useful summaries from this data. For example, one useful and simple summary could be, if I wish to find out how many medals, bronze, silver, gold medals, have these countries, each of these countries, won across these years. So in this summary, my vertical axis would be the country and horizontal axis would be the bronze, silver and gold medals won by that country. We'll now use pivot tables to create such a summary. We begin by inserting a pivot table template. We go to Insert, Pivot Table, insert a pivot table. So Excel will ask you where is the data for which you wish to create a pivot table. So I'll select my data. My data is in cell A1 through all the way down, cell A1 through cell K15317. That's my data. Then Excel asks you, choose where you want the pivot table report to be placed. Let me place it in a new worksheet so that my data summary is in a separate worksheet. You can also, if you wish, create the data summary in the same existing worksheet that you're working on. I do an OK. So Excel creates an additional worksheet here, and I can rename this worksheet if I want. I'll do a right click, rename, pivot table. I'm calling it pivot table. So this worksheet has been renamed as pivot table. And in this area, Excel has produced a template for a pivot table. And if you notice on the right hand side, these are the fields, the various columns that are there in my data file. And if I click anywhere on my spreadsheet other than the pivot table, those fields or those column listings go away. If I click on the pivot table, those fields reappear. And at the bottom area, I have certain tools that will allow me to organize my pivot table. Since I wish to create a data summary of various countries and the number of medals received by those countries across these Olympics, what I'll do is on my vertical axis, I'll put the name of the country, and on my horizontal axis, I'll put the medals, the bronze, silver, gold medal. I do this by clicking on the country field and dragging it all the way where it says row labels. So I have my countries organized in these rows on my vertical axis, all the way from Afghanistan to Zimbabwe. On my horizontal axis, I wish to put the medals, the bronze, silver, gold medals. So I'll grab the medal field and drag it to where it says column labels. So now I have these medals, bronze, gold, silver on my horizontal axis. So this creates a template for my data summary table. Next, what I wish to put inside this table is the number of medals won by these countries. So to do that, I again grab my medal field or the medal row and drag it to where it says values. So what Excel has done is it has put the total number of medals in this table, broken across bronze, gold, silver medals. For example, Canada has won a total of 304 medals over this period of time, broken up into bronze, gold, silver as per the numbers given there. One thing to keep in mind is that if there is a team sport and that team sport consists of, let's say, 11 members, 10 members and so on, and if a country wants a medal in that team sport, then all the individual members of the team are listed as medal winners in this file. So that completes our basic pivot table, and in a subsequent lesson we'll continue with our study of pivot tables.
This lesson continues with the construction of a pivot table which we introduced in the previous lesson. We further explore various options available to summarize data and present it in a pivot table, also known as a summary table.
Continuing with our study of pivot tables, we are working on a file that contains all Summer Olympic medal winners from 1976 Montreal Olympics to the 2008 Beijing Olympics. In an earlier lesson, we had used this file and created a pivot table in a separate worksheet where we created a table where the vertical axis consisted of all the countries and the horizontal axis consisted of the medal tally, broken up across the three categories of medals. Whenever I click anywhere on the pivot table, on the right hand side, I see the pivot table field list, which contains the various columns in my data and the tools to create the pivot table. And whenever I click anywhere other than the pivot table on my spreadsheet, the right hand side field list vanishes. The pivot table that we have, we can do further processing on it. For example, if I wish to sort the column labels, I could click on the pull down menu next to column labels and then choose a particular sorting option. Let's say I choose a reverse sorting option. So notice my column labels now are sorted in a reverse alphabetical manner. In this case, though, it makes more sense to have the bronze medal, then the silver, and then the gold. So I could manually sort it also. So I select the bronze column label, take my cursor to the edge of the cell, and then drag it and place it in front of silver. So now I have manually sorted it, and now I have my bronze medal, the silver medal, and the gold medal. This pivot table contains all the medals received by these countries across all the years 1976 through 2008. What if I wish to see only the medal tally for the Sydney Olympics in year 2000? I can do that by using the report filter option on the right hand side. So I wish to filter this pivot table using the year. So I select the year variable, drag it and place it in the report filter area. So on the top of the pivot table, now I see year there, and this allows me to now filter the pivot table according to a particular year. So if I click on the drop down box next to year, I can select the year 2000. Click on 2000. I can also select multiple years if I want, but in this case I'm interested only in the medal tally in the Sydney 2000 Olympics. So select 2000, do an OK. So now my report has been filtered, the pivot table has been filtered, and now I have got a medal tally only for the 2000 Sydney Olympics. Further, if I wish to see within the Sydney Olympics a medal tally only for the sport of boxing, I could add yet another filter to my report by dragging the sport on the right hand side, the sport field, and placing it in the report filter area. So now I have an option to filter my pivot table on yet another column, which is sport. So I go to sport, I click the drop down menu and select boxing. First I unselect all and then select boxing. So now I am filtering my pivot table by filtering my medal tally by year as well as sport. So I'll get a medal tally for the 2000 Sydney Olympics for boxing. I do an OK. So this is my medal tally for the countries which won some medal in Sydney 2000 Olympics in the sport of boxing. If on the other hand I want the medal tally broken up across all the sports, in that case I'll first remove the sport filter. I could do that either by clicking on the drop down box next to sport and selecting all the sports, doing an OK, so that I get a tally for all the sports, or I could also remove the sport from the report filter area. So I drag sport and place it back in the pivot table field list. This removes the filter on sport. Next, since I want the medal tally broken up across all the sports, so what I can do is I can select the sport column and add it as yet another row label. So I select sport, drag it and place it where it says row labels. So now I have two sets of row labels, the country and then the sport. And notice in my pivot table, I have the country and all the sports in which the country won some medals in the 2000 Sydney Olympics. And I also get the subtotals of the country's total medal tally. And at the very end of the pivot table, I get the grand total of all the medals.
Extending our study of the pivot tables, we now apply it to numeric data as contrasted to categorical data used in previous lessons. The use of numeric data allows us to do a lot more arithmetic manipulations in our pivot table. We demonstrate it using sales data from a store in Canada.
We will now be applying pivot tables to numeric data as contrasted to categorical data to which we had applied these tables to in earlier lessons when we used the data from the Summer Olympics medal tally. Numeric data as contrasted to categorical data is a data on which you can do various arithmetic calculations, such as you could add them, divide them, multiply them, can calculate the averages and so on. The example that we'll use is from the file store sales, which we have been using across various lessons. So let's open this file. You go to file and open the file store sales. So once again, this file contains sales data from a store in Canada that sells online office supplies. we wish to summarize sales data based on the province to which it is shipped. To do so, we'll introduce a pivot table. So we go to insert a pivot table, select my entire data, which in this case has already been selected, cells A1 through M8400. I'll put the pivot table report in a new worksheet and then I click OK. So a new worksheet is created and the pivot table is put inside that. I could rename this sheet. Pivot table. So I have my pivot table here. Now since I wish to put sales as per the provinces, I would select my province and drop it where it says row labels. So my vertical axis consists of all the provinces in Canada to which the store ships its products. Since I wish to organize my sales data as per the province to which it is shipped, I will select the province as my row label. So I'll drag province and place it under row labels. And as values, I'll select my sales. Select my sales and drag it and place it in values. So now my pivot table consists of the various provinces to which the store ships its products and the sum of sales across these provinces in my data set. My data consists of 4 years of sale from January 2009 till December 2012. So this is the aggregate of sales across these provinces. The province that sells the most is British Columbia, where the aggregate sales across the 4 years close to $1.89 million. Now, if instead of summing the sales, I wish to calculate the average sales in these provinces. So what I do is I click anywhere in this column sum of sales, do a right click, go to value field settings, and now instead of sum, I could select any of these options. I could count the number of observations across these provinces, calculate the average, calculate the maximum sales, minimum sales. So if I wish to calculate average, I select average, do an OK. Now in the pivot table, instead of having the sum of sales, I get the average sales. I could do similarly a minimum sales, do a right click, go to value field settings, minimum sales, and now I get the minimum amount of sales that has occurred across these 4 years across the 4 provinces. By minimum, I mean any particular order, the minimum specific order that has been received across these provinces. Next, if I wish to see the sales across provinces and across various years. So to do that, let me first revert back to sales being shown as the actual sum of sales. So I do right click, value field settings, sum. So this is the sum total of sales. Next, I'll insert the order date as my column label. So I drag order date, place it in column labels. And now what has happened is the sales in the pivot table are displayed across provinces, and as row labels I have those individual days. But I do not wish to have individual days. I want sales to be displayed as per year. Let me first hide the pivot table field list. I do that by going to the pivot table, anywhere in the pivot table, do a right click, hide field list. So what it will do is it will hide the pivot table list on the right hand side. I can also increase the viewing size of the spreadsheet by increasing it to, let's say, 120%. And now what I do is to view the sales across years, I click anywhere on this column label, do a right click, go to group, click on group, and since I want to group this in years, I select years. So right now both years and months are selected, so it would group it in years. as well as in months within those years. I don't want that. I just want years. So I click on months and deselect months and then do an OK. So now my sales across the various provinces have been grouped across the 4 years: 2009, 2010, 2011 and 2012. Now if I wish to see the sales across the provinces, across the years, and also across product categories. So this stores sales across 3 different product categories. So to do that, I will introduce the product category as an additional row label. So let me first begin by unhiding my pivot table field list. I do a right click anywhere on the pivot table, show field list. So my field list is shown on the right hand side. Now I'll select my product category and drag it and place it under row labels. So I have 2 row labels now. In addition to province, I have a product category also. So in the pivot table now, for every province, I have the 3 product categories. And then the sales are shown across product categories for various years in that particular province. And also the sum totals, the subtotals are also shown for various product categories, various years, various provinces. If I wish to look at sales for specific years, I could do that by going to column labels, clicking the drop down menu and selecting the years I want to see sales for. Let's say if I wish to see sales for the year 2010 and 2011. So first I deselect everything and then select 2010, 2011 and then do an OK. So now my sales in my pivot table are shown for these 2 specific years across provinces, across various product categories.
This lesson begins to explore the charting and graphing feature of Excel. Here we introduce the popular graphs available in Excel and start to learn how to plot a line graph.
We'll now be looking at some basic charting techniques in Excel. Charts, also known as graphs, are a very useful way of visualizing data in Excel. And some of the popular charts used are the line charts, the column charts, and the pie charts. We'll illustrate them using data from our store sales data file. So let's open that file. Store sales. So what we'll do is we'll first use pivot tables to quickly create some data summaries and then visualize those data summaries using these various kinds of graphs. We'll summarize sales across different provinces in different time periods. So to do that, first let's insert a pivot table. Insert pivot table. My data gets selected, my entire data. I'll create a pivot table in a new worksheet, do an OK. So my pivot table is created on the left hand side. On the right hand side, I have my field list, which contains my various columns, the title of columns that I have in my data. So I'll organize my data such that my vertical axis is the time period and my horizontal axis is the particular province. So I select the province and drag it and place it in column labels. So notice my horizontal axis are the different provinces. Then I select my order date, my time period, and drag it and place it where it says row labels. And since my order date is a particular date, that's why you see a whole lot of dates in my vertical axis. I will collapse them by putting my cursor anywhere on the vertical axis, doing a right click, group, and I'll group them by months and years. So years, and then within those years, particular months. Doing OK. So my structure gets prepared where I have the 4 years, 2009 to 2012, and the months within those years. Next, I will fill in my data in this data summary. So I would take sales, and drag it to where it says values. So now my data summary is complete, where I've organized the sales data across different territories, across years, and within those years, the particular months. Next, we'll use some charting techniques to visualize this data. Let's begin by using the line charts. Specifically, I'm interested in plotting the sales for the year 2010 across different months for a few provinces. First, I go to any empty part of my worksheet where I'll be putting my line chart. And then I go to Insert, and notice in this area where it says Charts, there are various options available. So I choose the line chart, click on that, and choose the very first option, which is the most commonly used option. So I get a blank slate. Now I'll be drawing my line chart in this blank slate. Before doing that, since I'm interested in plotting only the 2010 data, let me collapse the data for other years. So I do that simply by clicking the minus sign in front of the years. I collapse 2012, I collapse 2011, and I collapse 2009. Also, I'll hide the pivot table field list on the right side by clicking on the cross sign there. And let me also increase the viewing size of the spreadsheet to 120%. So let me drag my line graph slate up, and now I'll be placing my line graph in this area. I do a right click, select data, add. So what I'll be doing is I'll be plotting the monthly sales in the year 2010 for the province of Alberta. So I'll give series a name, Alberta, and in the series values area, I'll select the sales data for Alberta, the monthly sales data for that year, January through December. And then do an OK. And another OK. So a line plot is drawn whereby I have sales on the vertical axis, I have the dollar sales volume, and on the horizontal axis, I have the months labeled 1 through 12. I can also change this numbering of months. Rather than having it 1 through 12, I would prefer January through December. So I do a right click once again, select data, and on the right hand side where it says horizontal category axis labels, I click on edit, and axis label range, I select January through December and do an OK. Another OK. So now my horizontal axis has been labeled January through December. So that completes my line graph for the province of Alberta, the monthly sales in the year 2010. Notice the highest sales happen in the month of April. I'll now add a few more provinces to this plot. Namely, I'll add the sales in the province British Columbia as well as the province Ontario. So once again, I do a right click on my line chart, select data. I already have the sales data for Alberta there. I'll click on add. I will now also add data for the province of British Columbia. So I'll give the series a name, British Columbia, and in the series values, I'll select the sales data for British Columbia, January through December. And I'll do OK. And then once again, since I also need to add the sales data for Ontario, I'll do another add there. Series name Ontario. And I'll select the sales data for Ontario, January through December. And do an OK. And another OK. And if I want, I can extend this graph. I can stretch it across. And so that is a line graph of sales in the year 2010, January to December, for 3 provinces, Alberta, British Columbia, Ontario. Notice, generally speaking, Ontario has higher sales than the other 2 provinces. In a subsequent lesson, we'll see how to give a chart title and axis titles to this plot, and we'll also see how to plot the other popular charts in Excel, namely the column charts and the pie chart.
A pivot table is one of the most powerful tools you can use in Excel, and one of my favorites just because it's so easy to use and so quick to implement. You just highlight your data, click a button, and already you're digging through your data from multiple different perspectives and learning a lot. Now, from my experience, and kind of surprisingly, although lots of people use pivot tables, many of them seem to just scratch the surface of the capabilities, and a lot of them don't seem to use it at all. Given how important data is to businesses today, pivot tables really have become one of the most important tools to use to go through your data and to understand what's going on. And it's certainly important for you to use as someone interested in business.
In the lesson that follows, we continue with our plot of a line graph which was introduced in the previous lesson, and now we explore and extend it further.
At the end of the previous lesson, we started constructing a line graph. We used data from the file store sales and visualized the monthly sales in the year 2010 across the provinces of Alberta, British Columbia, and Ontario. So this visualization is what is shown in this line graph. Now we'll continue with this line graph and add things like a chart title, axis titles, modify the axis, and so on. Before we do that, notice there does not seem to be a clear trend across the monthly sales in these three provinces. Though one could say that over the period of these 12 months, the trend of sales in Ontario tends to be a bit increasing trend. Those things apart, let us now insert chart titles and axis titles in this line graph. To insert a chart title, we select the graph, then go to Layout, Chart Title, and notice we have a couple of options there. So let us choose the option which says I want to insert my chart title above chart. I click on that, a box opens up. I can put in my chart title here. So I can put in monthly sales, year 2010. If I want, I can also change the font of this title by selecting the title, going to Home, and choosing a different font size. I'll now insert the Y and X axis. To insert the Y axis, I select the Y axis, put my cursor anywhere on the Y axis, do a right click, then go to Layout, Axis Titles, click on that, Primary Vertical Axis Title. Again, I have a few options there. I could either have a rotated title, a vertical title, or a horizontal title. Let me put a rotated title. Click on rotated title and then type in dollars. Enter. So my y-axis has been labeled dollars. If I want, I can also change the way my y-axis looks. For example, if I wish to have, rather than the units ranging from 20,000 to 40,000, 60,000, if I wanted them to increment in units of $10,000. So I select my y-axis, do a right click, format axis, axis options, the major unit, I check on the fixed box and change the major unit from 20,000 to 10,000 and do a close there. So my major unit, or the increment on my y-axis, has gotten changed from $20,000 to $10,000. I'll add titles to my horizontal axis. I select my horizontal axis, go to Layout, Axis Titles, Primary Horizontal Axis Title. I'll put the title below axis and type in months. So that's the title for my x-axis or the horizontal axis. I can also change the way my horizontal axis looks. So once again, I select my horizontal axis, do a right click, format axis, go to alignment, text direction. If I want text to be displayed vertically, I could select a vertical alignment. I could also select a stacked alignment. I could also select a inclined alignment. For example, if I wish to incline the way the months look, I could select a custom angle. For example, a negative 45 degrees. So my axis, my horizontal axis is now inclined at a 45 degrees angle. So a variety of ways the axis can be formatted. The legend, which is shown on the right hand side, that too can be formatted. So for example, I select my legend, do a right click, format legend. I can have the legend on the right hand side. I can have it at the bottom. The legend goes to the bottom. I can have it at the top. I can have it at the top right, and so on. So a variety of ways the legend can be formatted. I can also format the way the line in the line graph looks. So I select the line. Let's say if I wish to change the formatting of the line for Ontario, I do a right click on the line, make sure the line gets selected, do a format data series, go to line color. I can change the color of the line. If I want different colors, I can change the color. Line style, the style of the line can be changed here. I can change the thickness of the line by changing the width. I can change the type of line. For example, instead of a solid line, if I wanted a dotted line, I could select a dotted line and the line changes to a dotted line. Let me revert back, and so on. So these lines could also be changed.
The following lesson introduces the other two popular graphs and charts in Excel, namely the column charts and the pie charts.
We'll now introduce the other two popular charts, the column charts and the pie charts. We'll illustrate them using the same data that we use to illustrate the line charts, that is the data on store sales from a store in Canada selling office products online. So let us go to the Excel file. So we are interested in plotting the monthly sales for the year 2010 for three provinces: Alberta, British Columbia, and Ontario. So in an earlier lesson, we had plotted them using a line graph. We'll now plot them using a column graph. So the process we follow is, again, put your cursor somewhere in an empty cell in your spreadsheet. Go to Insert, and now insert a column chart. Let's select the most commonly used, the very first option. So once again, a blank slate is produced. We'll be putting a column chart in this blank slate. We do a right click, select data, add series name. The first province we wish to plot is Alberta. Call it Alberta. Where is my data for Alberta that I wish to plot? So I wish to plot the monthly sales in year 2010. So I select the monthly sales January to December, year 2010. Do an OK. I wish to add two more provinces. So I click on Add. Call it British Columbia. Select the sales data for British Columbia, the monthly sales data in year 2010. And similarly, do it for Ontario. Add. Ontario, and select the monthly sales for Ontario, January through December, and do an OK. I'll change my horizontal axis. Rather than having a numbered horizontal axis 1 through 12, I'll give it the names January to December. So I click on Edit, the horizontal category, axis labels, Edit. I'll select my axis label range, January through December, do an OK, and do another OK. I could spread out the graph. So this is my column graph produced, which shows the same information that was shown using the line chart, namely the monthly sales in year 2010 across 3 provinces, Alberta, British Columbia, Ontario. I could also add a chart title, label my horizontal axis, put a label to my vertical axis, just as I did in a line graph. Another interesting thing, I could also change the orientation of this column graph. So if I go to this column chart, anywhere in the column chart, click on it, do a right click, change chart type. So if I want a horizontal chart rather than a vertical column, I go down, select this horizontal bar and do an OK. So now the orientation has changed, and on my vertical axis I have the months, and the horizontal axis I have the dollar amounts. I could also change it to a line graph if I want. Again, I go anywhere in the chart area, do a right click, change chart type, select line, do an OK. So now I have gotten my line graph. I've changed the information to a line graph. The same line graph that we had plotted earlier. We'll now plot a pie chart using this data. To begin, let us delete this existing line chart. A pie chart is a circle divided into sections or pie slices representing a proportion of the whole pie. To plot a pie chart, we go to Insert, Pie, select the pie option. Let's go by the very first option, which is the most popular. Again, a blank slate is produced. I'll put my pie chart in this blank slate. I do a right click, select data, add. Now remember, a pie chart is data represented in a pie format. I select the series values. I'll plot a pie chart for Alberta first. So monthly sales January through December in the year 2010 for the province of Alberta. I select my series values, give series a name, Alberta. Do an OK. And I would like to name my months rather than naming them 1, 2, 3, 4. I would like to give them names January, February, and so on. So the horizontal category axis labels, I do an edit and select the name of months January through December. Do an OK. Do another OK. All the months do not show here. That simply means I need to select the legend and stretch it a little bit. Now all months show up January through December. So notice in this pie chart, these individual pie slices represent the proportion of sales in that particular month to the overall sales in 2010 for the province of Alberta. For example, in Alberta, maximum sales occurred in the month of April and the minimum sales occurred in the month of August. Maximum sales were $91,495 and about 17 cents, and the minimum sales in August were $7,805.22. Now, if we wish to plot similar pie charts for the other 2 provinces, British Columbia and Ontario, what we would need to do is plot separate pie charts for those 2 provinces. To create space, I'll compress the pie chart a little bit. Move it to the side. And since I would prefer to have similar size pie charts for the other 2 provinces, what I'll do is I'll copy this pie chart, paste it 2 times. So I have these 3 pie charts. Now what I'll do is I'll take the second pie chart and replace the Alberta data with British Columbia. So I click anywhere on the pie chart, do a right click, select data, go to the series titled Alberta 2010, do an edit, change the name of the series from Alberta to British Columbia, change the values for the pie chart by selecting the sales for British Columbia January through December. Do an OK and another OK. So a pie chart for British Columbia sales in 2010 is produced, and notice the maximum sales for British Columbia in that year occurred in the month of June, and the minimum sales occurred in the month of March. So June and March. Let us do the same for Ontario. So I do a right click on this third pie chart, select data, edit, change Alberta to Ontario, change the data and select the sales for Ontario January through December, do an OK, another OK. And now this is the pie chart for Ontario, the sales from January through December in the year 2010. The maximum sales, you would notice, occur in the month of September and minimum in May.
We now make charting in Excel a lot more interactive by introducing something called pivot charts, which, as the name suggests, are based off a pivot table.
Pivot charts in Excel. So what is a pivot chart? A pivot chart plots data just as a regular chart does. A line chart, a column chart, a pie chart, and so on. However, the difference is that a pivot chart is based off a pivot table. And why this is different is because it gives you interactive filtering controls on the chart itself, so that you can quickly analyze a subset of your data and change the way your chart looks at the data and plots the data. Let's look at it by way of an example. We'll use the same data file, the store sales data file, and introduce the pivot chart. In an earlier lesson, we had created a pivot table out of this store sales. The store sales are given in the worksheet store sales, and when we created the pivot table, we created the pivot table in a separate worksheet which Excel named sheet 1. So this is the pivot table that we had created in an earlier lesson. So if you click anywhere in the pivot table, it tells you the structure of this pivot table. So the column label is the province, Alberta, British Columbia, Manitoba, and so on. The row labels, we created two levels of row labels. The first is the year, 2009, 2010, 11, 12. The second layer for the row labels is order date. Further, if you click anywhere on the order date, do a right click, click on group, we had grouped the order dates by months and then years. And that's how we had gotten this structure. And since we were interested in year 2010, we had minimized all the other years. And then given this structure, we had then constructed line graphs, column graphs, pie charts for the sales in 2010, January through December, for the provinces of Alberta, British Columbia, and Ontario. Now we'll do the same thing, but by introducing pivot charts. To construct a pivot chart, what is important is you begin by placing your cursor somewhere on the pivot table and not in an empty cell in your worksheet. So the cursor should be placed anywhere on a cell which is inside the pivot table. Now once you've done that, then you follow the process of creating a regular chart, which is insert. And let's say if I wish to create a line graph or a line chart, I go to line, choose the very first option. A template gets produced here. Now notice the difference. This is an interactive chart. Why is it interactive? Because it gives you these interactive controls here. You can choose the province, you can choose the order date, you can choose the year, and so on. So since we were interested only in 3 provinces, let's reduce the provinces to those 3 provinces. So I click on the drop down menu box against province. I first deselect all, then select Alberta, British Columbia and Ontario, do an OK. So the graph now displays information only for Alberta, British Columbia, Ontario. Further, year. I'll select the year, so I click on the drop down box against year, and since I'm only interested in year 2010, I would deselect all and then select year 2010, do an OK. So this is year 2010, and clicking on order date, I make sure that only January to December is selected, do an OK. So notice this gives us the same line chart that we had produced earlier when we had discussed line charts. But the advantage now is this is a highly interactive chart. So for example, if I wish to add yet another province to this line chart, all I need to do is go to the interactive menu for province, select the new province. For example, if I wish to include New Brunswick, I select New Brunswick, do an OK, and this new province now gets introduced in the chart. If I also wish to include the year 2011 in this plot, what I do is I go to the interactive menu or the pull down menu against years, select 2011, do an OK. In my pivot table, year 2011 occurs, so I expand it by clicking on the plus sign. And now notice in my line chart, the pivot chart which I have used to plot a line graph, I have information for 2011 as well. I can expand that graph by stretching it, and I have my sales plotted for those 4 provinces, monthly sales for the year 2010 as well as year 2011.
This lesson visually investigates the relationship between 2 variables by introducing the scatter chart, also known as the XY plot. We will learn how to plot and interpret a scatter chart in Excel.
Scatter charts in Excel. A scatter chart, also known as an XY plot, is a visual representation of the relationship between 2 variables. It shows how are the 2 variables related. Is the relationship a positive relationship, a negative relationship, or is there no relationship? The 2 axes in a scatter chart represent the 2 variables, and the coordinates of every point on the chart are the values of the 2 variables. We will see this by way of an example. We'll open an Excel file. The file that we'll use is named height and weight. So this file contains the names of certain Olympic athletes from a recent Olympic Games. Specifically, what is contained is the name of the athlete, the second name, the first name, the height of the athlete in centimeters, the weight of the athlete in kilograms, the country, and the gender of the athlete. So now what we are interested, given this file, is in studying the relationship between the 2 variables, height and weight. And we'll do this by plotting a scatter plot between the 2 variables. To do that, first we go to any empty place in our worksheet, put our cursor there, and go to insert. This is where we'll insert a scatter chart or a scatter plot. In the charts area, earlier when we had plotted various charts, we had used the column option, the line option, the pie option. There's also a scatter option. So we'll choose the scatter option and choose the very first, which is the most popular option. So a template is produced, a blank template. We can move it a little bit to the side. Now we'll be plotting our scatter plot in this template. So we click anywhere in this blank template or slate, do a right click, select data, click on add, I need to specify what would go in my horizontal axis and what would go in my vertical axis. So let me choose height to be used for the horizontal axis and weight to be used for the vertical axis. So for my horizontal axis, I choose the data in the height column from the first data point to the very end. We'll also select our vertical axis values, which is the weight values. So again, we select the very first weight to the very end. Do an OK. Do another OK. So what is produced is a scatter plot between the height of the athlete and the weight of the athlete. The height is on the horizontal axis and the weight of the athlete in kilograms is on the vertical axis. Notice the scatter plot shows the relationship between the two variables. To make the presentation a bit more visually appealing, we'll do some minor modifications to this chart. We'll begin by adding the horizontal axis labels, vertical axis labels, and a chart title to this scatter plot. So select my horizontal axis, go to layout, axis titles, primary horizontal axis title, below axis, and since these are the heights, I'll call them height in centimeters. Similarly, I'll add a vertical axis title, go to layout, axis titles, a rotated title, this is the weight in kilograms. I can get rid of this series 1 there, the notation series 1. If I want, I can give it a name, but I really don't need it here. I delete that. I'll add a chart title. I'll select this chart area, layout, chart title, above chart, heights and weights of athletes. I could change the font for this. Another modification I'll do is in this plot, all of these points, these individual points are these individual athletes. Every athlete is represented by a particular point. They are clustered together. So I could change the formatting of my horizontal axis so that I get a better visual representation. None of the athletes has a height less than 125 centimeters. So let me begin my horizontal axis with 125 centimeters. I do that by selecting my axis, right click, format axis, the minimum rather than an automatic selection of the minimum value, which in this case is 0. I would choose my minimum value to be, let's say, 125 centimeters and do an OK. So now this gives me a slightly better visual representation of the relationship between heights and weights. I can expand it further by dragging it down. And what does this trend indicate? As expected, greater the height of an athlete, we also see that the weight also increases. So there, this visual representation of this scatter plot tells me that there is a positive relationship between the height of an athlete and his or her weight. How strong is this relationship is a subject matter of a later lesson. Also, as an exercise, I'll leave it to you to figure out whether a similar pattern is seen across the two genders, male athletes, female athletes. Remember, this current scatter plot is a plot between all athletes irrespective of their gender. So you could do a similar exercise by segregating all the male athletes, the female athletes, and seeing whether similar patterns are observed across both genders.
This lesson introduces an interesting and important charting tool in Excel, namely the histogram. We begin by understanding what a histogram is, and then in a subsequent lesson we start constructing one.
Histograms in Excel. We'll be spending some time in this lesson and a subsequent lesson trying to understand what a histogram is and how to construct one in Excel. The reason we'll spend some time on a histogram plot is, firstly, it is a little less intuitive than column charts and other graphs. The other graphs that we have been studying, such as the column graphs, the line graphs, the pie charts, and so on. Second, a histogram plot is not as easy to create using Excel as some of these other charts. And thirdly, perhaps more importantly, a histogram is very similar to statistical distributions, which we will talk about in a subsequent course in the specializations. When we introduce certain distributions, the knowledge of a histogram would be very handy. The easiest way to explain a histogram is to actually look at one and talk about it. Consider the following histogram of a list of CEO salaries of small businesses. The basic idea of this histogram is to pictorially show how many salaries are low, high, and in between. The horizontal axis gives the salaries, and the vertical axis tells how many salaries were approximately equal to those on the horizontal axis. For instance, it appears that there were 2 salaries around $75,000, 2 around $150,000, 8 around $225,000, and so on. Now, when I say there were 2 salaries around $75,000, what does that mean? Excel here shows boundaries of ranges. The first range or bin goes from 0 to $75,000. That is, there were 2 CEOs with salaries between 0 and $75,000. Similarly, there were 2 CEOs between $75,000 and $150,000. Now, when I say 2 CEOs having salaries between $75,000 and $150,000, what I mean is 2 CEOs having salaries greater than $75,000 and less than equal to $150,000. And similarly, 8 CEOs with salaries greater than $150,000 but less than or equal to $225,000. So now that we have seen a histogram, we can give a formal definition. A histogram shows relative frequencies of observations that fall into set bins, also known as classes or ranges. Look again at this histogram of incomes. It is quite typical of income histograms. Some CEOs have very high salaries, but no CEO has an extremely low salary. This is very similar to income histograms. This histogram is an example of a skewed distribution, skewed to the right distribution. It is not symmetric. A symmetric distribution has roughly the same number of observations on either side of the mean. Here is an example of a symmetric distribution. If I were to slice this distribution somewhere in the center, I would get approximately 2 mirror images on both sides of that center. The way I constructed this histogram was that I took 2000 random draws from a symmetric distribution. This histogram does not consist of real data. I made up the data for the purposes of illustrating a symmetric histogram. Now, with the background of histogram, a good understanding of a histogram, we are ready to construct a histogram in Excel. And that is what our next lesson will consist of.
Here in this lesson, we construct a histogram using data on salaries. The data analysis toolbox in Excel is introduced, which will often be used across various courses in this specialization.
We begin constructing a histogram in Excel by opening the data file in Excel that contains the salaries of CEOs. The file is named CEO Salary Small Forms. This file contains the salary is in units of $1,000 and we wish to create a histogram plot for this salary column. We begin doing that by clicking on data and then data analysis. However, before that, if you do not see the icon data analysis when you click on data, you need to make sure that the icon is added to your spreadsheet. And this is how you do it. You go to File, Options, Add-ins. At the bottom, you go to Manage Excel Add-ins, click on Go, and make sure that the Analysis Toolpack and the Analysis Toolpack VBA both are checked, and then do an OK. After that, you may have to close your worksheet and open it again. And now when you click on Data, you should be able to see the icon Data Analysis. However, before I click Data Analysis, I need to set up my bins. Remember, a histogram shows the relative frequency of observations across a set of bins. So let me introduce my bins by labeling a particular column as bins, and now I'll put down my bins in this column. The bins should be so set up that all the data gets represented under one bin or another. So I begin by putting in a 0 there. My bin interval I'll choose to be $75,000. So the next number I put for my bins is 75. So my first bin goes from 0 to 75, and I'll use the same bin interval, a spread of $75,000 in the salary. So I can copy and paste it all the way down. I select it and keep dragging it. Notice my bins are increasing to 525, 675. Let me drag it and stop at 1050, $1.05 million. So this is my set of bins. Why did I stop at 1050? No particular reason. I could have gone further. Next, I go to Data Analysis. So Data Analysis. Scroll up and down till I find histogram. Do an OK. So I'm instructing Excel to construct a histogram using this dialog box, using this Data Analysis dialog box. I do an OK. I need to specify where my input range is, the data that I wish to plot in a histogram. So I wish to plot the salary data. So my input range is in column B, and notice Excel gives you an option of choosing labels. So if I choose this option, what I'm instructing Excel is that the very first data point in my range, in my input range, is a label. So I've chosen, it's a good practice to choose labels whenever an option is provided. So I put my cursor in the input range, select my data including the very first observation, which is a label, salary in $1,000, and select my entire column there all the way to B60. Next, I need to specify my bin range. Where are my bins? And once again, since I have made an option, I've chosen the option of using labels, the bin range also should begin with a label. And that is the reason why we labeled our bins with the word bins. So I select my bin range, cell D1 through D16. Output options, you have a couple of output options. You can either put the output in a empty cell within the existing worksheet, or you could also put it in a new worksheet. Let us choose the current worksheet, an empty cell in the current worksheet. So I put my cursor there and then select any empty cell on the worksheet. F2. And then important thing, you need to make sure that you check the chart output box. If you do not check that box, a histogram will not be plotted. And once you've done that, now let's do an OK. So Excel has now produced a histogram. I could stretch this histogram up a little bit. Maybe get rid of this legend title frequency. Add a title for my horizontal axis. CEO salaries in thousands. And I get back the histogram that we had seen earlier. A few observations before we close this lesson. The table that gets produced next to the histogram is also known as a frequency table. It tells me the distribution of the number of observations across those spends. For example, there are 2 CEOs with salaries in excess of $0 and less than equal to $75,000. Similarly, there are 9 CEOs with a salary greater than $300,000 but less than or equal to $375,000. And there is a single CEO with salary in excess of $1.05 million. One final point about setting up your bins. How big a bin interval should I choose? In this example, I chose a bin interval of $75,000, but as a general practice, there is no one particular rule in choosing your bin interval. However, you should choose bins such that you get a good visual representation of the data. Too many bins lead to bad histograms. Too few bins also lead to bad histograms. So try out a different set of bins and go along with the bin interval or the set of bins that gives you the best visual representation.
People love charts because they allow you to visualize and really tell a story with your data. Now, in a business setting, decisions are made every single day, and these decisions are based on lots of information in a very short amount of time. Now, I was a project manager, and I was responsible for actually presenting to these business decision makers. And I can honestly say that I could not have done that without the use of charts. Charts allowed me to really summarize that data in a very meaningful way, but also a very concise way to keep that time much shorter. Anyone who's interested in business absolutely has to understand how to use and create charts.
Hi there, welcome to the course. My name is Sharad Bodle, and I'm a faculty of management at the Jones Graduate School of Business at Rice University in Houston, Texas. The course is a part of the Business Statistics and Analysis Specialization, and this specialization through these various courses aims to develop a robust and practical understanding of various aspects of business statistics using the popular software Excel. The spreadsheet software Excel is an industry standard, and getting to apply all these skills, the business statistics skills using the software, would go a long way in its applicability to the industry. It is a great source of pride and joy when students come back and tell me how they were able to apply these courses at their workplace. It also helps in iterating these courses and making them relevant to today's business. The course that you're taking will give you ample opportunities in applying these various statistical tools to a variety of business applications. I'm very passionate about teaching these courses. My own academic background is a very quantitative one. An undergraduate in engineering, an MBA in quantitative techniques, and finally a PhD from the Carnegie Mellon University in Pittsburgh. My own research deals with application of various statistical tools and quantitative methods to various issues and problems faced in the industry. In this lesson, we will introduce the notion of descriptive statistics for data. We will talk about the two categories of descriptive statistics: measures of central tendency or averages, and measures of dispersion or spread in data. We will then begin introducing measures of central tendency. So, what are descriptive statistics? These are a set of numbers that describe a data. A data may have many observations, and a summary set of numbers that describe those multiple observations is called descriptive statistics. For example, a descriptive statistic we all are aware of is the average. We keep hearing things like the average rainfall during this time of the year is so and so, or the average salary increase at my organization was, say for example, 3%. This average is nothing but one of the more popular descriptive statistics used to describe data. You could, if possible, take a look at the salary increases of all people working in your organization. However, the average 3% is still a summary descriptor of the same data. Similarly, there are many other descriptive statistics. The more important and commonly used amongst them can be categorized broadly into two categories: measures of central tendency, also known as various averages of data, and secondly, measures of dispersion. The former tries to capture some central aspect of the data, while measures of dispersion summarize how spread out or dispersed the data is. We will first study measures of central tendency. There are three important averages or measures of central tendency used to summarize data: the mean, the median, and the mode. When we talk about the mean, we will be referring to the arithmetic mean as contrasted to some other means, such as the geometric mean or the harmonic mean, which we will not be using in this course. The mean of a set of data is simply the sum of data observations divided by the total number of observations. Let us illustrate the Excel command to calculate mean using the data file onlineorders.xlsx. This file consists of dollar value of orders received at an online grocery store in the US during a particular month, and we will be using this file to illustrate calculation of various descriptive statistics.
The very first column of this data set is a running serial number. So we have a total of 11,121 observations. The second column is some internal identification mark given to these orders. And the third column is the actual dollar value of the grocery order. So for example, the very first order in that month was worth $52.05. The 10th order in that month was worth $63.95, and so on. So to calculate the mean, we do a is equal to average, open parenthesis, and then select the dollar values, cell C2 all the way to cell C 11,122, close parenthesis, enter. So that's the average order value or the mean order value at this grocery store in that month, $102.84.
The median of a set of ordered observations is a middle number that divides the data into two parts. The Excel command for median is median and then the set of numbers for which the median needs to be calculated. In our online orders data, the median of all orders received by the online grocery store is $91.02.
So to calculate the median, you simply do is equal to median, open parenthesis, and then select the entire column and close parenthesis. So that gives you the median order, $91.02.
When should you report the median and when should you report the mean? Consider a 7-employee small firm where the annual salaries of employees are as shown: $28,000, $33,000, $33,000, $34,000, $37,000, $40,000, and one employee earns an annual salary of $400,000. If we ask the question, what is the typical salary in this small firm? In response, if you calculate the mean, we get $86,000. Now notice that no one gets a salary even close to $86,000. On the other hand, if you calculate the median, you get $34,000, which is a more appropriate answer to the question posed. So in this case, median is a better summary statistic to report. The mean is influenced to a greater extent by extreme observations. So, if you notice extreme observations in your data, then perhaps a median is a better summary of data than a mean. Income and price data generally follow this pattern, and that is why you notice typically the census organizations, when they report data, they report the median incomes and median prices. For example, median house prices. Continuing with our descriptive statistic measures, in this lesson we will look at the relationship between mean and median as it relates to skewness of data. We will then introduce the mode statistic and move on to measures of dispersion or spread in data, introducing the range and the interquartile range measures and their associated Excel commands. Another interesting relationship between the mean and the median relates to the skewness of data for which the mean and median are being calculated. In an earlier course, while introducing histograms, we had briefly talked about skewness of data. For example, we had constructed a histogram plot of CEO salaries of small firms and saw that this plot was skewed to the right. That is, it had a longer tail on the right hand side as compared to the left hand side. There were fewer CEOs with really large salaries. If you calculate the mean and median for this data, it turns out to be $404.17 thousand and $350,000 respectively. The mean is greater than the median, and this is what makes the data distribution skewed to the right. On the other hand, if we have a left skewed data, for example, student scores out of a maximum of 100 obtained on an exam as shown in the histogram plot. Then in this case, if we were to calculate the mean and median, it would be a score of 74 and 79 respectively, the median being greater than the mean, thus making the data skewed to the left. The last measure of central tendency that we will study is the mode. The mode is the most frequently occurring value in a set of data, and the Excel command to calculate mode is mode.sngl. The SNGL in the command stands for a single mode. A mode is not a very relevant statistic when the data is essentially continuous. For example, consider the daily exchange rate between the US dollar and euro in a particular month. The mode is not very relevant because the nature of data is such that no value occurs more than once. Even if it occurs more than once, the likelihood of such occurrence would be low. Thus, little information is gained knowing the mode. So, that was first of the two categories of descriptive statistics, measures of averages or central tendency, the mean, median and mode. Next, let us introduce the second category of descriptive statistics, namely measures of dispersion or spread in the data. To motivate these measures, let us consider two sets of salaries in two different small firms of 7 employees each. The mean and median salaries in both firms are exactly the same. Yet, if you eyeball the salaries, the spread of salaries in firm 2 is much more than in firm 1. The visual shows these two sets of salaries plotted together, and it is clearly seen that the spread of salaries in firm 2 is greater than that in firm 1. So, how does one translate this difference in spread into some meaningful descriptive statistic? One way to do so is to calculate the range of data, which simply is the difference between maximum and minimum values in the data. The maximum salary in firm 1 is $36,000 and the minimum is $30,700, giving us a range of $5,300. Similarly, the range of salaries in firm 2 is $16,200, a higher range implying greater dispersion or spread in the data. The range measure of dispersion leads into yet another similar measure, namely the interquartile range, or IQR. This defines the middle 50% of data, leaving 25% of the data to the right and 25% to the left. The first quartile is a number such that 25% of the observations are less than or equal to this number. Similarly, the third quartile is a number such that 75% of the observations are less than or equal to that number. The median, incidentally, is the second quartile. The minimum number in the range is the 0th quartile, and the maximum number in the range is the 4th quartile. Finally, the interquartile range, or IQR, is the third quartile minus the first quartile. Why do we prefer the interquartile range measure over the range measure? Because, as we will see later in this business statistics and analysis specialization, almost always we will be dealing with a sample of data, and our effort will be to make some inferences about the population from which the sample comes. In that context, the range of a sample is not indicative of the range of population from where it comes, while on the other hand, an interquartile range of a sample is indicative of interquartile range of the population. How do you calculate the various quartiles in Excel? We use the quartile.inc function. This function takes in two inputs, your data array and the particular quartile, 0th, 1st, 2nd, 3rd, or the 4th that you wish to calculate. The interquartile range can then be calculated in Excel as the difference between the 3rd and the 1st quartiles. Let us illustrate this calculation in our online orders.xlsx file.
So we wish to calculate the interquartile range of the dollar value of all the orders received at this grocery store during the month. So interquartile range is the third quartile minus the first quartile. So we do a is equal to quartile.inc open parenthesis, then we select our data range, C2 through C11,122, comma, the third quartile, number 3 there, close parenthesis, so that is a third quartile, minus the first quartile, quartile.inc, open parenthesis, our data range C2 through C11122, comma, the first quartile, 1, close parenthesis, enter. And this gives us our interquartile range, $63.32.
In the following lesson, we will see a useful plot to visualize the various descriptive statistics, the box plot. We will then introduce the most commonly used measure of dispersion in data, the standard deviation. We will conceptually understand the measure and see Excel commands to calculate it. A box plot is a nice visual representation of these various descriptive measures that we have studied till now. First, let us look at the definitional figure for a box plot. A box plot is also known as a box and whisker plot. The two whiskers on the top and bottom are the maximum and minimum of your data. The vertical line on the left hand side is the scale of measurement. The rectangular box is your interquartile range. bounded by the first and third quartiles. The horizontal line inside the box is the median and the dot represents the mean. So, in one visual you get a good summarization of data. Such a visual becomes particularly useful when you are comparing two data sets. For example, if you consider the earnings of Hollywood stars from acting in their movies and you wish to compare the earnings across male and female stars, a side-by-side box plot comparison is very helpful. The earnings are in $1 million, and as per the plot, the highest paid female star earns almost the same as the highest paid male star. However, clearly the dispersion or spread in the earnings of female stars is more than the male stars, as evidenced by the range, which is the difference between the maximum and minimum, and also the interquartile range, the height of the rectangular box. Another interesting observation is that the mean earning is greater than the median earning for female stars, while for the male stars the mean earning is less than the median earning, implying that the distribution of earnings for female stars tends to be much more right skewed as compared to the male stars. There are a few female stars that are very high earners, pushing the overall mean to be in excess of the median earning. One final point about box plots. Excel in its native form is not adept at producing a box plot. Nevertheless, learning to interpret data in terms of a box plot is a very useful skill to have. So, we have covered two measures of dispersion in data, the range and the interquartile range. We will now introduce the standard deviation measure, which is much more commonly used descriptive statistic for dispersion or spread in data. First, let us understand conceptually how this measure differs from the range and interquartile range measures. Consider salaries at a small firm consisting of 7 employees. This is the same firm too used in an earlier lesson. The same information can also be visually displayed. The range and interquartile range measures describe dispersion or spread in data in terms of difference between some high value and some low value. For example, the range is the difference between the maximum value and the minimum value in data. The interquartile range is the difference between a high value, the third quartile, and a low value, which is the first quartile. On the other hand, the standard deviation first calculates the mean of the data and then computes differences between each of the data points and the mean. It then combines these differences to give the standard deviation measure. Uppercase N in this formula is the total number of observations. The standard deviation formula sums the square of differences, divides it by n, and then takes the square root of the result. Anyway, you need not remember the formula, as we will be using Excel to calculate the standard deviation. In this case, since we are considering the entire set of employees in the firm, or in other words the population of employees in the firm, we use the Excel command stdev.p to calculate standard deviation. If we had data which was a sample from some larger population of data, which by the way typically would be the case in a majority of business applications, we would use the Excel command stdev.s to calculate the standard deviation rather than stdev.p. The P and S standing for population and sample. There is a minor difference in the formulas for the two calculations. However, we will not concern ourselves with that, and for sake of uniformity and simplicity, we will be using the sample standard deviation formula throughout the course. Your Excel spreadsheet contains many other variants of this command. However, the stdev.s is the command that we will be using. Let us calculate the standard deviation of dollar orders in our grocery data file.
We wish to calculate the standard deviation of orders received at this grocery store. Or in other words, we wish to assess the dispersion or spread in this data. So let's calculate standard deviation. Remember, the Excel formula that we'll use is stdev.s, open parenthesis, we select this entire column, shift control down arrow, close parenthesis, enter. So that gives us our standard deviation measure, 57.67. The units of standard deviation are the same as the data. So in this case, it would be $57.67. This is the spread of my data. Now, how do I intuitively make sense of this number? That will be subject of a subsequent lesson.
We will now introduce the rule of thumb, a useful tool to intuitively make sense of the standard deviation measure, and in the next lesson demonstrate it using our Excel data file. In the previous lesson, we introduced the standard deviation measure to assess dispersion or spread in data. As mentioned in that lesson, the standard deviation is the most common measure of dispersion in data, and the Excel command that we will use throughout the course is stdev.s. Yet another measure of dispersion is the variance, which is nothing but the square of standard deviation. You may hear the term variance, but remember there is a direct one-to-one relationship between the variance and standard deviation. We calculated the standard deviation of orders received during a month at the online grocery store using our file onlineorders.xlsx and found it to be $57.67. Now, how do I intuitively understand this number? That is, as a grocery store owner or manager, how do I translate this number $57.67 into some meaningful and useful interpretation? This is where something known as the rule of thumb comes in handy. It says that approximately 68% of data lie within one standard deviation and approximately 95% lie within two standard deviations of the mean. Let us explore this a little bit more. So, I calculated my mean and if I go to the right hand side of the mean, if I go one standard deviation, I get a number mean plus one standard deviation. I get this number. Similarly, if I go on the left hand side of the mean, one standard deviation, I get this number mean minus one standard deviation. Now, the rule of thumb says that approximately 68% of all observations in my data would fall between these two numbers, plus minus one standard deviation from the mean. Similarly, if I go two standard deviations from the mean, so on the right hand side, if I go mean plus two standard deviations, I get a number. Similarly, on the left hand side, if I go mean minus two standard deviation, I get another number. The rule of thumb says that between these two numbers, approximately 95% of all observations in my data fall. In this lesson, we will see how the rule of thumb works on our online orders data set.
The rule of thumb states that approximately 68% of these grocery orders would be within plus minus 1 standard deviation from the mean, and approximately 95% of these grocery orders would be within plus minus 2 standard deviations from the mean. So in this file, we already have calculated the mean and standard deviation. So next, let us now put in those upper and lower limits. So we do a mean plus 1 standard deviation and mean minus 1 standard deviation. So this is equal to our mean value, which is 102.84, plus 1 multiplied by our standard deviation value, which is 57.67. So that gives me the upper limit. The lower limit is equal to mean minus 1 multiplied by the standard deviation. So that gives me the lower limit. Mean plus 1 standard deviation, mean minus 1 standard deviation. Next, I need to count the number of observations that fall within this lower and upper limit. So I would use a COUNTIF function for that. And once I count those number of observations, I need to find the ratio of those observations to the total observations in the file. And that will give me the percentage of all values, all dollar orders that fall within plus minus 1 standard deviation from the mean. So I'll count the observations now. Count of observations. I'll use the COUNTIF function. So is equal to COUNTIF open parenthesis. I need to put in my range, which is C2 through C11122. Next, I need to put in my criteria. So I wish to count the number of observations that fall between $45.17 and $160.51, including those two numbers. So I do a quotation mark, greater than, equal to, close quotation. Then I do an ampersand sign and pick up this lower limit 45.17 from this particular cell F13. Close parenthesis. So what this will count is, it will go to my database, my column C, and count the number of observations that are in excess of 45.17, including 45.17. However, from this count, I wish to subtract the count of observations which are in excess of the upper limit, which is $160.51. So I'll do a minus COUNTIF open parenthesis. My range is C2 through C11122, comma, open quotation marks, greater than, close quotation marks, my ampersand sign, and then I select my cell F12, 160.51, close parenthesis. The second expression here, the second COUNTIF, counts the number of observations in excess of 160.51. So the two COUNTIFs combined would count the number of observations that fall within $45.17 and $160.51, including the two outer limits. Press enter. So there are a total of 8,591 observations that fall within plus minus 1 standard deviation from the mean. And the total number of observations is simply a count of my entire range, count C2 through C11122, a total of 11,121 observations, and now a ratio of 8,591 to 11,121 will give me my desired answer, which is the proportion of values or the percentage of total values that lie within plus minus 1 standard deviation. Percentage of observations is equal to that number 8591 divided by the total number of observations. And this is my desired answer. There are a total of 77% observations that fall within plus minus 1 standard deviation from the mean in my data. Now, how close is it to 68% as predicted by the rule of thumb? Well, not very close, but still not very far too. We can also check the other statement of the rule of thumb, which says that approximately 95% of observations fall within plus minus 2 standard deviations. So all we need to do is change this 1 standard deviation to 2 standard deviations. 2 standard deviations, change the formula here. So mean plus 2 times standard deviation, and change this formula to mean minus 2 times standard deviation. And the count of observations automatically gets updated, and we get a new percentage of observations, which is 96%, which is quite close to that predicted by the rule of thumb, which says that about 95% of observations fall within plus minus 2 standard deviation from the mean.
In the lesson that follows, we will conclude our discussion of the rule of thumb, a useful tool to understand the standard deviation measure, and also introduce yet another similar tool, the Chebyshevs theorem. Some final points about the rule of thumb discussed in the last lesson. Note that this rule of thumb is based on an assumption that your data is approximately bell shaped. That is, if you plot a histogram of your data, it would approximately look like a bell, or in more technical language, it follows a normal distribution, a distribution that we will study in a later lesson. When there is significant deviation from this assumption, another theorem becomes helpful in interpreting the standard deviation measure. The Chebyshevs theorem states that at least 1 minus 1 over k square of data lies within plus minus k standard deviations from the mean, regardless of shape of the distribution, the data histogram. K needs to be greater than 1 here, and when we consider an interval of plus minus 2 standard deviations from the mean, the Chebyshevs theorem states that at least 75% of all data would fall in that interval. Remember, it says at least 75%. Note that the Chebyshevs theorem is a theorem, that is, it is always true, it holds. However, the rule of thumb is just that, an approximate rule, though a very useful one.
Hi, my name is Young, and I did my PhD here at Rice University in quantitative marketing. And before I did the switch to academia, I used to work in the hotel industry. And I just want to tell you a little bit about this course and how it relates to the real world. Right, so some of the topics we'll be covering in this course are about central tendency or dispersion in data. While these seem like very academic topics, they're actually used quite a lot in the real world. Right? So central tendency is something that every business uses. Right, when you want to summarize any kind of data. So for example, in the hotel industry, we often use average daily rates. Right? And what that just means is what is the rate that we tended to use in a particular window for a particular night. So this concept comes up all the time. And the second concept that is really important is about dispersion. Right? So while an average rate gives you a good idea about what typically happens, it doesn't tell you, well, how wide or how accurate is this rate in representing all the days of our data. So this is when concepts of high and low ranges, interquartile ranges, standard deviations all come into play.
In this lesson and the next lesson, we will introduce descriptive measures of association between two variables, the covariance and the correlation measures. Understand them and introduce their Excel commands. In the past lessons, we studied two categories of descriptive statistics, measures of central tendency and measures of dispersion. To recap, descriptive statistics or measures are a summary set of numbers that describe the multiple observations in a data. The descriptive statistics on central tendency that we covered were the mean, median, and the mode, while the descriptive measures of dispersion or spread in the data were the range, interquartile range, standard deviation, and variance. These are the two primary measures of descriptive statistics. These measures summarize the multiple observations on a single variable. For example, what is the mean height of men in your neighborhood? What is the median house price in your city? What is the standard deviation of dollar order received at the online grocery store, data from which we have used in past lessons, and so on. All these examples consider multiple observations on a single variable, the height of men, the house price, the dollar order. Another set of descriptive measure of data, rather than looking at a single variable, considers the covariation amongst two variables. That is, how do the two variables vary together or co-vary. These measures are called measures of association, and they describe in a set of numbers the relationship between two or more variables. We will now introduce and understand these measures. Let us take another look at the scatter plot constructed in one of the lessons in the first course in this specialization on business statistics and analysis. The first course introduced the use of Excel for analyzing data, and in a particular lesson we constructed a scatter chart, also known as a XY plot. A scatter chart is a visual representation of the relationship between two variables, and we analyze the relationship between the height and weight of certain Olympic athletes from a recent Olympic Games. Heights being represented on the horizontal axis and weights on the vertical axis. Not surprisingly, the pattern of the scatter plot visually indicates that there is a positive relationship between the height and weight of an athlete. That is, as height increases, so does weight. A descriptive measure of association attempts to numerically quantify this relationship. That is, in a set of numbers, describe this relationship. We will study two such measures, which are closely related, the covariance and the correlation. First, let us look at the covariance, the formula for which is as shown. Uppercase X and Y are the two variables for which the covariance needs to be calculated. Lowercase n is the total number of observations on each of the two variables. Subscript I indexes each of those n observations. The horizontal bar on top of the variables indicates the mean value for that variable. As mentioned in one of the previous lessons, there is a slight variation in formula depending on whether you are considering the entire population of data or a sample of data from some population. For sake of simplicity and uniformity, throughout this specialization, we will use the sample formulas. Accordingly, the Excel formula that we use is covariance.s open parenthesis, and then we type in the two data ranges for the two variables. Remember, you need to have the same number of observations in the two data ranges. Let us calculate the covariance between the height and weight of these athletes in Excel using the file heightandweight.xlsx.
The first two columns of the file are the name of the athlete, then you have the height of the athlete in centimeter, then the weight in kilogram, the country to which the athlete belongs, and the gender of the athlete. So given this data, what we are interested in is in calculating the covariance between the heights and weights across these athletes. So covariance between height and weight, and we'll calculate that using the covariance.s command in Excel. So is equal to covariance.s open parenthesis, then I select the two data ranges, height and weight. It does not matter whether I select height first or weight first, we'll get the same answer. So I begin by selecting the height data range, C2 all the way to shift control down arrow, which gives me C1588, comma. Now I enter the second data range, the weight of the athlete, D2 through D1588, close parenthesis. So that completes my covariance formula. Covariance.s, the first data range, height, the second comma, the second data range, weight. I give an enter, and the answer I get is 139.9856. The unit of this covariance is the product of the units of the two data ranges. In this case, centimeter times kilogram. And the important thing to note about this covariance measure is that the sign of this measure is positive. It indicates that there is a positive relationship between height and weight of the athlete. As heights increase, so does the weight, and as heights decrease, so does the weight decrease.
Continuing with our descriptive measures of association, we will in this lesson explore in detail the correlation measure and contrast it to the covariance measure. In the last lesson, we introduced a measure of association, namely the covariance, to describe the relationship between two variables. In this lesson, we will further explore the covariance measure and then introduce the second descriptive measure of association, the correlation. Let us again open the Excel file from last lesson, heightandweight.xlsx.
In the earlier lesson, we had calculated the covariance between height and weight of the various athletes. Let's quickly do it again. Covariance, height, weight, and the formula we used was is equal to covariance.s open parenthesis, the first data range height, shift control down arrow, comma, the second data range D2 through D1588, close parenthesis. So this number 139.9856, we told ourselves that this has a positive sign indicating that there's a positive relationship between heights and weights of athletes. Now next, how do I interpret the magnitude 139.98? But before we interpret the magnitude, let us see what happens to this magnitude, this 139.98, if I change the units of measurement of these variables. Let us change the units of height from centimeter to meters. So I'll insert a column and create another variable there, height, but now measured in meters. is equal to, all I do is I divide the original height, which is in column C, by 100. So height in centimeter divided by 100. This gives me the height of the athlete in meters, 1.7 meter. And I copy and paste this formula all the way down. So now what I have is, I have measured the height of the athlete in meters. Notice I have not brought in new information. I have neither taken out any information. So no new data has been added and no data has been taken out. All that has been done is the units of measurement have been changed. So now let us measure the covariance between height in meters and weight. So notice the earlier covariance we measured was between height in centimeters and weight in kgs, and the covariance was 139.9856. Now we'll be measuring the covariance between height in meters and the weight in kilograms. Covariance dot S open parenthesis, the height measured in meters comma, and then the weight in kilograms, E2 through E1588, close parenthesis, and I press an enter. So notice the covariance now has been reduced by a factor of 100 from 139.98, which we had originally calculated. The new covariance is 1.3998. So this tells me that the covariance measure is affected by change in units of variables.
As we just saw, the covariance measure is susceptible to the unit of measurement. We can arbitrarily inflate or deflate the covariance by choice of units. Hence, the covariance measure is not very appropriate if one needs to assess the strength of relationship between two variables. The measure is fine as long as we need to know the direction of relationship. That is, when one variable increases or decreases, what happens to the other variable. However, the covariance cannot be directly interpreted in terms of how strong is the relationship. For that, we introduced another measure of association between two variables, the correlation measure. Notice the formula for the correlation scales the covariance by dividing it by the product of the two standard deviations. In terms of Excel formula, we use the is equal to correl function with the inputs being the two data ranges. Before we demonstrate the function in Excel, a few observations on the covariance and correlation measures. The covariance measure can theoretically vary between negative infinity and positive infinity. A positive value for the covariance indicating a positive relationship between the two variables, that is, if one increases, the other increases. If one decreases, the other decreases. A negative value indicating a relationship where when one variable increases, the other decreases, and vice versa. As mentioned, the magnitude of the covariance cannot directly be interpreted as the strength of relationship between the two variables, because the covariance is affected by the units of measurement. Coming to the correlation measure, the correlation is not affected by change of units and is always bound between -1 and +1, with positive value of correlation indicating a positive relationship and negative value indicating a negative relationship. Further, closer the correlation is to a +1 or -1, stronger is the positive or negative relationship between the two variables. Loosely speaking, a correlation in excess of positive 0.5 is considered a strong positive relationship, and a correlation less than -0.5 is considered a strong negative relationship between the two variables. With this, let us demonstrate the correlation calculation in Excel using the same height and weight file.
We wish to calculate the correlation between height of the athlete in centimeters and the weight in kilograms. Correlation between height and weight. And the function we'll use is the correl command in Excel is equal to correl open parenthesis C2 through C1588, which is the height of the athlete in centimeters, comma E2 through E1588, the weight of the athletes in kilograms. Press an enter. I get a number 0.774625. As per my rule of thumb, this indicates that there is a strong positive relationship between heights and weights of athletes, because this number 0.77 is in excess of a positive 0.5. Now I leave it as an exercise for you to confirm that change in units does not alter the correlation measure. Or in other words, the correlation can be interpreted as a measure of strength of relationship between the two variables.
In the following lesson, we discuss the notion of causation and how it is different from correlation or covariation. We will point out the important contrasts between correlation and causation and briefly outline how causation is established. In the last lesson, we covered two measures of association, the covariance and correlation. It is important to understand that these measures tell us how two variables vary with respect to each other. That is, if one variable increases or decreases, how is that related to the increase or decrease of the other variable? We looked at the height and weights of certain Olympic athletes and concluded that there was a strong positive correlation between the weight of an athlete and his or her height. This correlation, however, in no way proves that weight causes height or that height causes weight. This is where causation comes in, which is a distinct concept than correlation. However, unfortunately, many a times this distinction is glossed over. So, what is causation and how do we establish it? Usually, to establish causation, we need to have correlation and then a temporal distinction between the two variables. That is, the variable causing the other variable needs to precede or occur before the variable that it causes. Further, we need to rule out or control for other many variables that might be causing the variable in question. A good example is smoking and lung cancer. Sure enough, there is a high correlation between the incidence of smoking and the incidence of cancer. The chart shows data from a study carried out in the United Kingdom across men working in different kinds of occupations. The x axis or the horizontal axis is the smoking index, which is a ratio of the average number of cigarettes smoked per day by men in the particular occupational group to the average number of cigarettes smoked per day by all men. The y axis is the mortality index, a ratio of the rate of deaths from lung cancer among men in the particular occupational group to the rate of deaths from lung cancer among all men. This relationship shows a strong positive correlation of 0.72. This in itself does not imply that smoking causes cancer. However, over time, carefully conducted studies have shown that this positive association between smoking and cancer goes beyond correlation. It has firmly been established that smoking indeed causes cancer. To show this causal link, the studies would have controlled for many other factors that may cause cancer, and then establish a strong causal link between smoking and cancer. This is in fact what happens in clinical trials of medicines, because before the Food and Drug Administration in the United States approves a medicine, it requires proof that the medication actually makes people better. That is, it causes people to be better. Establishing causation is a big subject of study in itself, and in this course we will not be venturing further in that direction. However, being sensitized towards the difference between covariation or correlation on one hand and causation is a big step in our interpretation of association between variables. We will now introduce some basic concepts in probability, specifically what is probability and the notion of a random experiment and an associated random variable. We will now be introducing some basic concepts in probability that will be a foundation to much of what we will be doing in the remaining part of this specialization on business statistics and analysis. Understanding these concepts will go a long way in our grasp of various business statistics tools and their applications. First, what is probability? We all have some notions about probability, such as what is the chance or probability that it will rain today, what is the likelihood of my favorite team winning the competition, and so on. Let us now formalize this a little bit more. There are some very different schools of thought as to the definition of probability. For simplicity and convenience, we will stick to the long run frequencies notion of probability. For example, how do we know that when a fair coin is tossed, the chance or probability of getting heads is 50% or 0.5? The long run frequency notion of probability implies that if we were to toss the coin multiple times, the long range frequency of a head turning up will be 50% of tosses. Similarly, if a fair die is repeatedly rolled, the long run frequency of the number 6 turning up will be 1/6 of the number of rolls. Hence, the probability of a 6 turning up on a roll of a die is 1/6. A formal definition of probability would be as follows. Probability is a numerical measure of the frequency of occurrence of an event. It is measured on a scale from 0 to 1. An event of probability 0 will definitely not occur. An event with probability 1 will occur with certainty. For example, what are the chances or probability that you pick out a red ball from a bag full of white balls? It is a 0 chance or 0 probability event. That is, it will never happen. Similarly, probability of picking out a white ball from a bag full of white balls is a certainty or an event with probability 1. Some more concepts around probability. The notion of a random experiment and an associated random variable. One of the important concepts of probability is that of a random experiment. A random experiment is simply any situation wherein a process leads to more than one possible outcome. For example, a coin toss is a random experiment. Why? Because it is a process that leads to more than one possible outcome. Either a tail turns up or a head turns up. A roll of a die is a random experiment. A company declaring its earnings, the closing value of the stock market tomorrow, the bonus that you get at the end of the year are all examples of a random experiment, because once again these are processes that can have more than one possible outcome. The point here is that the concept of a random experiment is a very wide concept, and a lot of business situations can be characterized as random experiments. An associated concept is that of a random variable. A random variable is a variable that takes on values determined by the outcome of a random experiment. For example, the random variable associated with a coin toss or roll of a die can be termed as the outcome, and this random variable, the outcome, can take on 2 possible values in the case of a coin toss and 6 possible values in the case of rolling a die. Similarly, the random variable associated with a company about to declare its earnings can be termed as EPS, or earnings per share, and in this case the random variable, the EPS, can take on multiple possible values. Viewing business processes as a random experiment with an associated random variable is helpful, because next we can think about trying to characterize the variations in the random variable by using something called statistical distributions, which we will introduce in the next lesson. The better we can characterize the variations in the random variable, the greater is the benefit. Think about the stock market volatility and the associated random variable, which we can term as the stock index. If we are able to characterize the movements in this random variable, the stock index, to a reasonable degree of accuracy, the better would be our predictions on the movement of this index in the future. The better our prediction, the more money we may be able to make off the stock market. In the lesson that follows, we begin introducing statistical distributions. We discuss what a statistical distribution is and why is it useful. We also introduce the notion of discrete and continuous data and talk about the differences. In the last lesson, we introduced the concept of a random experiment and an associated random variable. We also told ourselves that viewing business processes as random experiments with an associated random variable is helpful in characterizing them and making predictions about their outcomes. To do this, we need to introduce statistical distributions and then use them to characterize or model the random variable in question. Let us understand what a statistical distribution is. In course 1 of the specialization, which covered topics in using Excel for data analysis, we also studied constructing histograms in Excel. In that context, one of the histograms we constructed was that for the salaries of CEOs from certain small businesses. This histogram tells us how the data on salaries for these CEOs varies. Some CEOs have very high salary, while a majority of them have a salary around $200,000 to $500,000. A few CEOs have much lower salaries. So, this is how salaries are distributed. We can view this as a random experiment, because as we saw in the last lesson, a random experiment is any situation wherein a process leads to more than one possible outcome. Here, different CEOs have different salaries, or in other words, there are multiple outcomes for salary. The associated random variable for this random experiment becomes the salary. We wish to now characterize the variations, that is movements in this random variable, the salary. This will then allow us to understand how CEO salaries would occur, perhaps across a different set of small firms, or maybe how they would occur in some different country, and so on. This is where a statistical distribution comes in. It is a tool that will help us model the salary for CEOs across small firms. The benefit of doing so would be that then we can make predictions about CEO salaries for small firms across a different set of firms not included in the data from which the histogram is created. The better we are able to model the salary, the better would be our predictions. Business statistics has a handful of statistical distributions to choose from, and the aim is to choose the most appropriate distribution to approximate or model the random variable in question. As we will see shortly in a subsequent lesson, one of the most important and popular statistical distributions is the normal distribution, also known as the bell curve. But before that, these various statistical distributions are broadly characterized in two categories: discrete distributions and continuous distributions. Discrete distributions, as the name suggests, is used to approximate random variables which are discrete in nature, or in other words, discrete distributions use discrete data, and continuous distributions are appropriate when the data is continuous. So, what is the difference between discrete data and continuous data? Let us illustrate it by way of an example. The number of students in a class, the number of patients admitted to a hospital in a day, the number of companies with revenue greater than $1 billion are all examples of discrete data. The test of discreteness is that if we take any two possible realizations of the random variable and ask ourselves how many possible values exist between the two realizations, if the answer is finite, then the data is discrete. If the answer is infinite, the data is continuous. For example, the number of students in a class, two possible numbers out of many possibilities could be 50 students or 60 students. Applying the test of discreteness, there are a finite number of possibilities between 50 students and 60 students, a total of 9 possibilities. You could either have 51 students, 52 students, 53 students, all the way till 59 students. The important point is that the possibilities are finite. This is what makes the data discrete. On the other hand, consider the heights of men and women in your neighborhood. Two possible heights out of the many possibilities are 150 centimeters and 160 centimeters. There exists an infinite number of possibilities between these two heights. Someone may have a height of 150.1 centimeter, 150.11 centimeter, 150.1045 centimeter, and so on. We are limited only by the accuracy of a measuring instrument. This is what makes the data continuous. Remember, the test of discreteness is a finite number of possibilities between any two outcomes. So, even though the number of stars in the universe may be infinite, still the data is discrete, because if you pick any two possible numbers, the number of stars between those two numbers is finite. One last point about discrete and continuous data is that in business applications, many a times, even though the data may be strictly discrete, for example, annual salaries of employees, revenues earned by companies, etc., we still end up using a continuous distribution to model or characterize such data. The reason being that the most popular and well understood distribution, the normal distribution, happens to be a continuous distribution. This kind of approximation is widely used and, frankly speaking, is okay for a majority of applications. We will be introducing two continuous distributions in this specialization, the normal distribution and something called the T distribution. We will talk more about it when we cover these topics.
So one of the most commonly used and also misused concepts in statistical inference that we use in the business world is the concept of correlation. And for example, right, we know in the hotel industry that when prices are high, occupancy is generally high as well. Right? So this is just saying that the two concepts are correlated, but not necessarily saying that raising prices will cause more people to stay with you. Right? So as a real world practice, it's useful to take the concepts that we learn about correlation and really think about them critically, right? So is it the occupancy that's driving the prices, or prices driving the occupancy?
In the following lesson, we introduce an important concept related to statistical distributions, namely the probability density function. We also introduce the concept of using area under the curve as a measure of probability, and why in a continuous distribution the probability of a particular outcome is always 0. Before we introduce the normal distribution, we need to understand one more concept, that of probability density function, also known as the PDF. We will try to make the explanation as simple as possible. In a previous lesson, we had seen the difference between discrete data and continuous data. We also told ourselves that a statistical distribution dealing with discrete data is called a discrete distribution, and a statistical distribution dealing with continuous data is called a continuous distribution. One of the most popular statistical distribution which we have yet to introduce is the normal distribution, which importantly happens to be a continuous distribution. However, as was mentioned earlier, it is okay many a times in business applications to approximate even discrete data with a continuous distribution such as the normal. So, what is a probability density function? It is a rule that assigns probabilities to various possible values that a random variable takes when it is being approximated by a particular statistical distribution. Let us understand it in the context of discrete data, where instead of being called a probability density function, it is called a probability mass function, or PMF. For example, if we consider a coin toss, the table shown gives the probabilities associated with the outcome of the toss. Getting heads has a 0.5 probability and getting tails has a 0.5 probability, thus exhausting our total quota of probability, which is 1. This table is the rule that governs the probability of various outcomes of the random variable associated with the coin toss. The random variable can be termed as outcome of the toss. This table or the rule is also known as the probability mass function for outcome of a coin toss. Similarly, the probability mass function associated with the outcome of roll of a die is shown in the table. Here again, the random variable can be termed as the outcome. Note two important aspects of this probability mass function. Firstly, the probability associated with any particular outcome or realization of the random variable is always bound between 0 and 1. Secondly, and more importantly, the sum total of all probabilities is 1. That is, the function covers all possible values of the random variable. It is easy to write down the probability mass function for a coin toss or roll of a die. What about the probability mass function of a more complicated process? For example, the number of customers that will arrive at the checkout counter of a grocery store in 1 hour. Here, what is done is that we approximate this process with a statistical distribution and use the probability mass function of that distribution. The probability mass function will assign probabilities to different possible outcomes. 0 customers arriving at the checkout counter, 1 customer arriving, 2 customers arriving, 3, 4, 5 and so on. Note that here the number of customers arriving at the checkout counter in 1 hour is discrete data. That is, you cannot have, for example, 4.5 customers. It will either be 4 or 5, nothing in between. So, strictly speaking, you would use a discrete distribution to approximate this process of customers arriving at the checkout counter. The probability mass function of the discrete distribution would assign some probability to say 4 customers arriving, some other probability to 5 customers arriving and so on. There will be 0 probability attached to any number between, for example, 4 and 5 customers arriving. The situation is very similar when using a continuous distribution. However, there are some differences. Firstly, the probability mass function is now called the probability density function, or PDF. The definition remains the same, which is a PDF or probability distribution function is a rule that assigns probabilities to various possible values that a random variable takes. The second difference is more important and nuanced. The probability of a particular outcome for a continuous distribution is always 0. Let us expand on this notion a bit more. Take for example the possible heights of men and women in your neighborhood. This is continuous data as discussed in a previous lesson, because if you take any two heights, for example 5 feet and 6 feet, then the possible value of heights that can occur between 5 feet and 6 feet are infinite. If you then ask what is the probability of someone's height being 5 feet 2 inches, the answer is 0, because even if your friend has a height of 5 feet 2 inches, my response will be that you get a better measuring instrument and you will find that the height is not 5 feet 2 inches, but say 5 feet 2.01 inches. Such kind of argument can be given for any height that you come up with, thus implying that the probability of someone having a particular height is always 0. This is the reason why when using a continuous distribution we always consider ranges of outcomes. For example, what is the probability that someone's height is between 5 feet 2 inches and 5 feet 5 inches? Probability for a range of outcomes. What is the probability that someone's height is less than 5 feet? Again, a range of outcomes. What is the probability that someone's height is greater than 5 feet, and so on. This is explained in the visual. On the horizontal axis, you have various possible heights in feet and inches. The curve that you see is a continuous distribution used to approximate the way heights are distributed in your neighborhood. This curve is the plot of probability density function for that particular continuous distribution we are using to approximate the occurrence of the random variable height. The higher regions of the curve represent higher probabilities and the lower regions represent lower probabilities. So, what is the probability that someone's height is less than 5 feet? It is area under the curve to the left of 5 feet. What is the probability that someone's height is greater than 5 feet 10 inches? It is area under the curve to the right of 5 feet 10 inches. And similarly, the probability that someone's height is between 5 feet and 5 feet 6 inches is area under the curve between 5 feet and 5 feet 6 inches. How do we measure area under the curve? As we will see in a later lesson, this is where we make use of Excel formulas. Extending this area logic further, what is the probability that someone's height is exactly 5 feet? It is area under the curve at the point 5. This would be area of a straight line, which is 0. Hence the statement that probability of someone's height being exactly 5 feet is 0. That is, in a continuous distribution, the probability that the random variable takes a particular value is always 0. In this lesson, we introduce the normal distribution, one of the most important and popular distributions. We introduce the two parameters of the distribution and see the various shapes the distribution can take. Continuing with our previous lesson on the probability density function for a continuous distribution, we were looking at the distribution of heights of men and women in your neighborhood, or in other words, we were looking at the distribution of the random variable height. We approximated the distribution of these heights using a continuous distribution as shown. We told ourselves that in a continuous distribution, it is pointless talking about the probability of a particular outcome, because that is always 0. Let us say that a particular outcome is denoted by lowercase x with a subscript 0. Thus, probability that height is equal to x0 is 0. Instead, we would consider the probability of a range of outcomes, such as the probability of heights being less than 5 feet, greater than 6 feet, between 5 feet and 5 feet 6 inches, and so on. In that context, we introduce the notion of area under the curve being a measure of probability. Further notice that since the probability cannot be greater than 1 and the distribution assigns probabilities to all possible outcomes of the random variable, thus the area under the entire curve necessarily has to be 1. With this background, let us introduce the normal distribution, also known as the bell curve. It is the most widely used distribution and also the most important. In fact, what we saw in the previous example in the last lesson was a particular normal distribution. The normal distribution is a symmetric distribution. That is, if we were to vertically slice this distribution, we will get 2 equal halves. Generally speaking, a distribution gets identified by where on the horizontal axis it is placed and how spread out or peaked it is. In the case of a normal distribution, you can get many forms of the distribution depending on where on the horizontal axis it is centered and how spread out or peaked it is. Accordingly, a particular normal distribution gets uniquely defined by 2 parameters: a location parameter, also known as the mean of the distribution, and secondly, a spread parameter, also known as the standard deviation of the normal distribution. Depending on the values of these 2 parameters, we can have a multitude of normal distributions. The mean can take any value from negative infinity to positive infinity, while the standard deviation can take on only positive values. The mean and the standard deviation numbers uniquely define a particular normal distribution, and this distribution is symmetric around the mean value. Let us see this in Excel. This is an example of a normal distribution, and as mentioned, a normal distribution is uniquely defined by 2 parameters, the mean and the standard deviation. So in this case, the mean is 2 and standard deviation is 1.2. Also notice the distribution is symmetric about the mean value. That is, if I slice the distribution at the mean value, I'll get 2 equal halves. Now let us see what happens if I change the mean or the first parameter of the distribution. So if I change it to 3, notice the distribution shifts towards the right. Change it to 4, maybe 6, and so on. So the distribution is shifting towards the right. What if I reduce the mean? 5, 4, maybe 2, 1. I can also go negative, -1, -2. So the distribution is shifting towards the left. And that is the reason why the mean or the first parameter is also called the location parameter. It locates the distribution. So let me revert it back to 2. Now let's change the second parameter, the standard deviation, and see how the distribution changes. So if I reduce the standard deviation to, let's say, 1.1, maybe 1. So notice the distribution is getting more peaked. If I increase the standard deviation, maybe 1.2, 1.3, 1.5, 1.7, and so on. So the distribution gets more
spread out or flattened. The distribution remains at the same place, that is, it is centered at the mean value. And that is why the standard deviation, or the second parameter of the normal distribution, is sometimes also referred to as the spread parameter.
Another thing to note is that in a normal distribution, all outcomes from negative infinity to positive infinity are possible, or in other words, the two tails, the left tail and the right tail, go all the way to negative and positive infinity respectively. It is another matter that the probabilities beyond a certain range get so small that they are insignificant. The probability density function of the normal, which is a rule that assigns probabilities to various possible outcomes, can be written in an equation form as shown. This formula is then used to calculate probabilities for various ranges of the random variable, as we had visually seen earlier in terms of area under the curve. The area under the curve between 2 points, say A and B, or in other words, the probability that the random variable, a continuous random variable, will lie between points A and B, is nothing but an integral of this probability density function between those 2 points. The lowercase x in the formula represents these various points. This equation and calculating its integral looks complicated. However, things are made simpler because any integration calculation based on this equation can easily be performed using Excel functions for the normal distribution, which we will introduce in the following lessons. In the following lesson, we introduce some standard notations for the normal distribution and then use a business example to introduce the first Excel function associated with the normal, the norm.dist function. We will now begin introducing Excel functions for the normal distribution. But before that, let us see some standard notations that textbooks typically use. The random variable typically is denoted by an uppercase letter such as an uppercase X, uppercase Y, or uppercase Z. This is certainly not a rule, but a convention popularly followed. Of course, you could continue to denote the random variable by more meaningful terms such as the height, weight, a company's earnings, and so on. So, when you are using the normal distribution to approximate how heights are distributed, or in other words, the random variable height follows a normal distribution with some particular mean and standard deviation, you would write it as height and then the tilde character followed by normal, open parenthesis, the mean, and then the standard deviation, close parenthesis. This is how you represent the random variable height following a normal distribution with some particular mean and standard deviation. We will now introduce the Excel function norm.dist for the normal distribution. Let us motivate this function using an example. A bread producing company produces whole wheat loaves of bread in its factory situated on the outskirts of Houston. The company meticulously maintains data on the production process and observes that on average every day 85 loaves of bread get discarded on account of being defective. They could be defective on account of various reasons such as defective packaging, spoilages, etc. When I say average, I mean that the number of defective loaves vary day to day. However, the mean value or the average value is 85 loaves. The standard deviation is 9 loaves. This standard deviation indicates the spread in the number of defective loaves day to day around the mean value of 85. Given this data, the company wishes to predict that in the production run tomorrow, what are the chances or probability that less than 70 loaves of bread will get discarded on being defective. Note here the random variable of interest is the number of defective loaves, and we wish to predict the probability that this random variable takes a value less than 70. We could approximate this process using a normal distribution and then use the formulas for the normal distribution to predict our required probability. Since the mean and standard deviation of the defective loaves is 85 and 9 respectively, we can approximate this process of defective loaves by using a normal distribution with mean 85 and standard deviation 9. In other words, the random variable defective follows a normal distribution with mean 85, standard deviation 9, and we wish to calculate the probability that this random variable is less than 70. Looking at the plot of probability density function of the normal, we are interested in calculating area under the curve to the left of 70. In more technical terms, we wish to integrate the probability density function of the normal between negative infinity and 70. Remember, the range of normal distribution varies from a negative infinity to positive infinity. Some of you may wonder that this data is discrete because you cannot have half a loaf discarded, or for example 2/3 of the loaf discarded. You are right that this data is indeed discrete. However, as mentioned in earlier lessons, it is okay to approximate such discrete data with a continuous distribution like the normal. The error introduced is minimal. To calculate this integral or area under the curve, we use the norm.dist function in Excel. The syntax of the function is equal to norm.dist open parenthesis. The first input is the number to the left of which you wish to calculate the probability, in terms of notation typically denoted by lowercase x, and in our case the value of x would be 70. Then in the syntax you give the mean and standard deviation, which in this example is 85 and 9 respectively, and finally the word true. This function calculates the area to the left of the very first number in the syntax. So, for this example, the function would be norm.dist open parenthesis 70 comma 85 comma 9 comma true close parenthesis. Let us calculate this in Excel.
What we are given is that the number of defectives, the random variable defective, follows a normal distribution with mean 85 and standard deviation 9, and given this information we wish to calculate what is the probability that in a day's production, tomorrow's production run, the number of defectives is less than 70. So we will use the norm.dist command for that. We do a is equal to norm.dist open parenthesis. The first input is the number to the left of which you wish to calculate the probability. In this case this is 70, comma, the second input is the mean of the normal distribution, which is 85. The third input is the standard deviation of the normal distribution, which is 9, and the last input is, we will put in the word true. In a later lesson we will also talk about what does false and true mean. So the word true and close parenthesis, and when I press enter, the answer is 0.04779, or in other words, there is a 4.779% chance that in tomorrow's production run the number of defective loaves would be less than 70.
Let us pose another question. What is the probability that the number of defective loaves produced tomorrow are in excess of 95? Here, if we use the is equal to norm.dist 95 comma 85 comma 9 comma true command, we will get the probability to the left of 95. That is the probability that number of defective loaves produced is less than 95. We do not want that probability. Rather, we wish to calculate area under the curve to the right of 95. Here we use our knowledge that area under the entire curve is 1. Thus, area to the right of 95 is 1 minus area to the left of 95. That is, in Excel we will use is equal to 1 minus norm dot dist 95, 85, 9, true.
So, to find the probability that the number of defectives is in excess of 95, we do is equal to 1 minus norm dot dist open parenthesis 95, 85, 9, and then the word true. And we press enter. The answer is 0.13326 or approximately 13.33% chance that the number of defectives are in excess of 95.
We will continue with this example in the next lesson. Continuing from the previous lesson, we will look at further applications of the norm.dist Excel function to calculate probabilities in a normal distribution. We also highlight some common confusion that arises while applying the function to business applications. Continuing with the example from previous lesson of a bread producing company that every day on average produces 85 defective loaves with a standard deviation of 9 loaves. Another question that could be posed is, what is the probability that in tomorrow's production run the number of defective loaves produced is between 75 and 80? Here the answer is area under the curve between 75 and 80, and using the norm.dist command it is calculated as shown. The first part of the expression norm.dist 80, 85, 9, true calculates the probability of number of defectives being less than 80, that is area under the curve to the left of 80. However, we do not want this entire probability. We only want the probability of the random variable, the number of defectives, being less than 80 but greater than 75. So, the second expression subtracts out the probability of the random variable being less than 75, resulting in our desired probability. We will see this calculation in Excel.
Given that the number of defective loaves produced follows a normal distribution with mean 85 and standard deviation 9, we wish to calculate the probability that the number of defective loaves produced is less than 80 but greater than 75. So what we do is equal to, first we will calculate the probability that the number of defective loaves is less than 80, and then from that subtract out the probability that the number of defective loaves is less than 75. So norm.dist open parenthesis 80, comma, the mean of the normal distribution 85, comma, the standard deviation of the normal distribution 9, comma, and then the word true, close parenthesis. So this expression would give us the probability that the number of defective loaves produced is less than 80. But that is not what we want. So we subtract from this the probability that the number of defective loaves produced is less than 75. So we do another norm.dist open parenthesis 75, comma, the mean 85, comma, standard deviation 9, comma, true. So this expression when executed would give us our required probability. The probability that the number of defective loaves produced is less than 80 but greater than 75. And that probability is equal to 0.1560, or in other words, there is a 15.6% chance that the number of defective loaves produced is less than 80 but greater than 75.
Let us illustrate a common confusion that arises in using the norm.dist function, using the bread loaves production as an example. Let us say we wish to calculate the two probabilities as shown. The first is the probability that number of defectives is less than 75, and the second is the probability that number of defectives is less than or equal to 75. In the case of bread loaves, less than 75 would imply 74 loaves, 73 loaves, 72 loaves, and so on, while less than or equal to 75 would also include 75 loaves. So, the two probabilities do seem different. However, here is a critical distinction to note. We are approximating a process which is discrete using a normal distribution, which is a continuous distribution. One of the important properties of a continuous distribution is that between any two possible outcomes of the random variable, an infinite possibility for that random variable exists. In our example, it means that between 74 defective loaves and 75 defective loaves, we can have an infinite number of possible outcomes. That is, we could have 74.1 loaves being defective, we could have 74.25 loaves being defective, and so on. This kind of an anomaly arises because we are using a continuous distribution for a process which is essentially discrete. So, how do we reconcile this anomaly? We do so simply by understanding the anomaly, why it exists, and then keeping that in mind in our business decision making. As for the calculation of various probabilities, an important thing to note is that we should adhere to the properties of a continuous distribution, and an important property is that probability of the random variable taking a particular value is always 0. This brings us to our question on the distinction between the two probabilities: probability of defective loaves being less than 75 and the probability that the number of defective loaves is less than or equal to 75. The answer is that they are one and the same, because the probability that number of defective loaves is exactly equal to 75 is 0, which is a property of a continuous distribution. For both calculations, we will use the exact same Excel syntax, which is equal to norm.dist 75, 85, 9, true. One concluding observation on the use of norm.dist command to calculate probabilities under a normal distribution. In the syntax, the last input would always be true. Excel also provides an option for using false. However, the result that you get when using false is the value of probability density function evaluated at that particular number, the very first input in the syntax. Importantly, this result is not to be interpreted as probability for the random variable. The bottom line being that we will never use the function with the false option. The lesson introduces the second of the two Excel functions for the normal distribution, the norm.inv function. We contrast this function with the earlier introduced norm.dist function and understand the function using applied examples. We will now introduce the second Excel function associated with the normal distribution, the norm.inv command. As the name suggests, this function does an inverse of what a norm.dist function does. Recollect that the norm.dist function calculates the probability to the left of any particular point in a normal distribution. For example, in the visual shown, which is the normal distribution of men and women heights in a particular neighborhood, the mean being 5.5 feet and standard deviation being 0.4 feet, the probability of someone's height being less than 5 feet, or for that matter less than or equal to 5 feet, would be given by norm dot dist 5, 5.5, 0.4, true, which if you calculate in Excel is equal to 0.1056 or a 10.56% chance. This can also be viewed as saying that 10.56% of the adult population in the neighborhood has a height less than or equal to 5 feet. Notice that while using the norm dot dist function, you know the number to the left of which the probability is to be calculated. In this case, it is 5 feet. Now consider an inverse situation. You are given a probability value 0.1056 or 10.56% and you are required to find out that particular height such that 10.56% of the adult population will have their heights less than that particular height. Here you know the probability 0.1056 and knowing this probability you wish to calculate the value in the normal distribution that cuts off this probability to its left. This is where the norm dot inv function gets used. The syntax is as shown, is equal to norm dot inv open parenthesis, then the probability to the left, the mean of the normal and the standard deviation, close parenthesis.
Doing the calculation in Excel, what we are given is that the heights of men and women are being approximated by a normal distribution with mean 5.5 feet and a standard deviation of 0.4 feet, and given this, the question asked is find out that height, and let's call that height as x0, such that the probability of someone's height being less than x0 or that particular height is equal to 0.1056. Or in other words, the question is asking find out the height such that 10.56% of men and women have their heights less than that particular height. And for notation's sake, we are calling that particular height as x0. So the answer here would be x0 is equal to, we'll use the norm.inv command, is equal to norm.inv open parenthesis, we'll put in the probability which is 0.1056 comma the mean of the normal distribution 5.5 feet comma the standard deviation of the normal distribution 0.4 feet and close parenthesis. So this will give us the required value of x0 or that particular height, and that height is 5 feet. Let us do one more quick calculation. So let me erase this answer and I'll change the question a little bit. So find out that height, again let's call it x0, such that the probability of someone's height being less than that particular height x0, now instead of 0.1056 probability, I'll change the probability to 0.50. And now we wish to find out x0. Some of you may immediately recognize that the answer has to be 5.5 feet because normal is a symmetric distribution, symmetric about the mean. There's a 50% probability to the left of the mean and 50% probability to the right of the mean. Hence, the answer has to be 5.5 feet. Nevertheless, let us also do the calculation using the norm.inv function. So I do a is equal to norm.inv open parenthesis, the probability value now is 0.50 comma the mean which is 5.5 comma the standard deviation 0.4 close parenthesis, and the answer is 5.5 feet.
Consider another situation. You wish to find out the height such that top 15% of the tallest people in the neighborhood have their heights greater than that particular height. In other words, you wish to find out a height such that the probability someone's height is greater than this particular height is 0.15. Once again, this is an inverse of the norm.dist function, since we know the probability and we wish to calculate the number that cuts this probability. However, notice the difference. We are given the probability to the right and not to the left, while the syntax of the norm.inv function needs probability to the left. Once again, we use our knowledge that the entire probability under the distribution is 1. Hence, if the probability to the right of the desired height is 0.15, then the probability to the left of that height has to be 1 minus 0.15, which is 0.85. That is, the required green shaded probability has to be 0.85. Thus, the norm.inv function would be is equal to norm.inv open parenthesis 0.85 comma 5.5 comma 0.4 close parenthesis.
Doing the calculation, the answer would be is equal to norm.inv open parenthesis 0.85 comma the mean, which is 5.5 comma the standard deviation, which is 0.4 close parenthesis 5.9 feet, or in other words 15% of the tallest people in the neighborhood have their heights greater than 5.9 feet.
In this lesson, we work out applied problems using the normal distribution. We make use of the Excel functions norm.dist and norm.inv for calculations. We also introduce the standard normal distribution, which is a special form of the normal distribution. We will use this lesson to get more acquainted with applying the normal distribution to some applications. We will work out some problems where we need to apply the norm.dist and the norm.inv functions. We begin by the problem faced by a fast food restaurant that sells falafel sandwiches. On a typical weekday, the demand for those sandwiches can be approximated by a normal distribution with a mean of 313 sandwiches and a standard deviation of 57 sandwiches. The restaurant wishes to find out the probability that on a particular day the demand for falafel sandwiches is less than 300 sandwiches. Here, the problem says that the demand for sandwiches is being approximated by a normal distribution with mean 313 and standard deviation 57. Further, the random variable of interest is the demand for sandwiches. So, we can write that random variable as demand follows a normal distribution with mean 313 and a standard deviation of 57. Given this, answer to this part of the question simply becomes an application of the norm.dist function.
The demand for falafel sandwiches is being approximated by a normal distribution with mean of 313 sandwiches and a standard deviation of 57 sandwiches. Given this, we wish to find out the probability that the demand for sandwiches on a particular day is less than 300, or in other words, we wish to find out the area under a normal distribution to the left of 300. We do this by using the norm.dist command. So, is equal to norm.dist open parenthesis the number to the left of which we wish to calculate the probability, in this case it is 300, comma the mean of the normal distribution 313, comma the standard deviation of the normal distribution 57, comma then the word true close parenthesis. The answer is 0.4098 probability or 40.98% chance that the demand for falafel sandwiches on a particular day is less than 300.
Another question posed by the fast food restaurant: if the restaurant stocks 400 falafel sandwiches for a given day, what is the probability that it will run out of these sandwiches on that particular day? That is, there will be a stock out of sandwiches.
The restaurant will run out of sandwiches if the demand that materializes is greater than 400 sandwiches on that day. In other words, the probability that the restaurant runs out of sandwiches is equal to the probability or chance that the demand is greater than 400. This is area to the right of 400 under the normal distribution with mean 313 and standard deviation 57. We calculate this using the is equal to 1 minus and then the norm dist. Notice why we need to do 1 minus norm dist is that we wish to calculate area to the right of 400, not left of 400. So 1 minus norm dot dist, open parenthesis, 400, comma, the mean 313, comma, the standard deviation 57, comma, and then the word true, close parenthesis. So the answer is 0.0635 or a 6.35% chance. So this is the probability that the restaurant will run out of falafel sandwiches on a particular day, a chance of 6.35%.
Yet another question posed by the same fast food restaurant: how many sandwiches must the restaurant stock to be at least 98% sure of not running out of sandwiches on a given day?
The problem can also be stated in terms of find out the number of sandwiches, and let's call it x0, such that the probability that the demand is less than x0 is at least 0.98. So notice in this case we know the probability and we wish to find out the number under the normal distribution to the left of which that probability occurs. So this is an inverse of what a norm.dist does, and we'll be using the norm.inv command for this. So to calculate x0, we do is equal to norm.inv, open parenthesis, the probability is 0.98, comma, the mean is 313, standard deviation is 57, close parenthesis. So the answer got as 430.0637. So this is the answer in response of the number of sandwiches such that the demand is less than that number of sandwiches is at least 0.98.
So how many sandwiches should the restaurant stock? The answer is 431, because if you round the number 430.0637 to 430, then remember that if the restaurant stocks 430 sandwiches, then probability that demand is less than 430 will drop below 98%. Hence, in this case, when you round the number 430.0637, you need to round it up to the next integer to tell the restaurant how many sandwiches to stock, so that it is at least 98% sure of not running out of sandwiches. Another problem: John can take either of two roads to the airport from his home, road A or road B. Owing to varying traffic conditions, the travel times on the two roads are not fixed. Rather, on a Friday around midday, the travel times across these roads, across these two roads, can be well approximated per normal distributions as follows. Road A mean time of 54 minutes with a standard deviation of 3 minutes. Road B, it takes a mean time of 60 minutes with a standard deviation of 10 minutes. Which road should he choose if on midday Friday he must be at the airport within 50 minutes to pick up his spouse. If he takes road A, the probability of reaching the airport in 50 minutes is equal to norm.dist 50, 54, 3, true. The answer being 0.0912 probability. If he takes road B, the probability of reaching the airport in 50 minutes is equal to norm.dist 50, 60, 10, true. The answer being 0.1586 probability. So there is a greater probability of making it in 50 minutes if he takes road B. One last topic before we end this lesson is the standard normal distribution. A standard normal distribution is a normal distribution with mean equal to 0 and standard deviation equal to 1. That is, a normal distribution which has a mean 0 and standard deviation 1, we choose to call as standard normal. This distribution is symmetric about 0, and half the probability, that is 50% of the probability, lies to the left of 0, and the remaining half, the remaining 50%, to the right of 0. An important property relating to the standard normal is that any normal distribution of a random variable can be converted into a standard normal by subtracting the mean value from the random variable and dividing it by the standard deviation. As shown, if uppercase X is a random variable that follows a normal distribution with some mean and some standard deviation, then if we transform this random variable into another random variable, uppercase Z, by subtracting the mean and dividing by the standard deviation, this newly created random variable Z follows a standard normal distribution. That is, a normal distribution with mean 0 and standard deviation 1. We will see applications of the standard normal in our next course in this specialization. In the following lesson, we introduce the notion of a population data and a sample from that population data, some very important concepts in business statistics. We talk about the linkages between a sample and population. What are some of the properties that a good sample should have? The concept of a population and a sample from that population are central in business statistics. So let us understand these concepts. In common usage, the word population implies a collection of people. However, in statistics, when we say population, we imply a collection of people, collection of items, group of measurements, set of events, etc. The common theme is that we wish to make some inference about the population. A formal definition that can be given is that a population is the complete set of numerical information on a particular quantity in which we as an analyst are interested. For example, if you wish to find out the percentage of votes that a particular candidate will get in the upcoming mayor's election in your city, then your population of interest, or the relevant population, is the set of all voting people in the city. If you wish to make the same inference for a national election, then the population of interest would be the set of voting people in the entire country. If McDonald's wishes to study how sales have been impacted by menu changes in its offering across its restaurants in the state of Texas, then all the franchisee McDonald's restaurants in Texas become the relevant population for this study. Food and Drug Administration of the United States needs to test and clear food items being imported inside the United States. In this case, all the food items being imported become the relevant population for purposes of testing by the FDA, the Food and Drug Administration. A sample, on the other hand, is a subset of the relevant population, and it is a sample that you actually use to make inferences about the population. For example, the pollsters before elections make predictions about the outcome of elections based on interviewing a sample of voting population. They do not interview the entire voting population. The Food and Drug Administration may not inspect the entire set of food products imported, but rather may inspect a sample from the entire population of food items. Similarly, McDonald's may simply analyze the change in sales in response to menu changes in offering only for a sample of restaurants rather than the entire set of restaurants. The aim is still the same, to understand how sales have been impacted across all restaurants. So, why do we take a sample? The biggest reason is that accessing the entire population may not be practical, may not be cost effective, or may not even be possible. For example, if you wish to count the number of black spots on oranges picked at a large orange farm, then it may not be feasible to count the spots on every orange picked. Rather, you may want to use a sample of oranges and count the number of black spots in that sample. An important thing to keep in mind is that what is a population and what is a sample are very context driven questions. Something which is a sample in one situation may be a population in some other situation. For example, the set of voting people in Houston can be considered a sample when analyzing the voting behavior in the presidential election across the United States. The same set of voting people in Houston would be a population when analyzing voting behavior for Houston's mayor elections. So, what allows us to use a sample rather than an entire population in making inferences about the population? Two important things. Firstly, a sample should be a subset of the population, and secondly, and more importantly, the sample should be representative of the population. Representative sample means that the sample should accurately reflect the entire population. It should be an unbiased representation of what the population is like. Example of a non-representative sample would be one where, for example, in a study to ascertain eating habits of students on a university campus, we use a sample consisting only of male students. This sample probably may not be representative of the entire student body on the campus, which consists of both male students and female students. How does one get a representative sample? There is a whole field within marketing research that deals with sampling and different ways of generating a representative sample. However, in short, the most common method of obtaining a representative sample is to randomly select a sample from the population. Apart from being a subset of and representative of the population, before we start making inferences about the population based on the sample, we need to introduce some more statistical concepts. One of the very important concepts that allows inference about a population based on a sample is a theorem called central limit theorem, which we will introduce in the next lesson. This lesson introduces a very important theorem in statistics, the central limit theorem. In simple language, we introduce and understand the theorem and its importance for various business applications. One very important concept in statistics that allows inference about a population based on a sample is the central limit theorem, which we will introduce now. But before that, let us talk about some terminology. In the last lesson, we discussed what a population is and what a sample is, how they are context dependent. That is, the same set of data in one case can be considered a population, while in some other context it may be a sample. We also mentioned that a sample should be subset of the population and representative of the population. Any set of data has some mean and some standard deviation. The convention amongst textbooks is to denote the mean of data when referring to the population data to be the Greek letter mu, and the standard deviation for the population data is denoted by Greek letter sigma. For the sample, the mean of the sample is denoted by x bar. a horizontal bar over lowercase x, and the standard deviation of the sample is denoted by lowercase s. As an example, let us say you wish to find out the average starting salary of all business students who graduated last year in a big city like New York City. The relevant population in this case is all students in New York City who finished their business education last year. Clearly, this is a large set of people, and since in this context it is the population, hence in terms of standard notation the mean starting salary will be denoted by the Greek letter mu. The variation in the starting salary in this population, or in other words the standard deviation of starting salaries in this population, will be denoted by Greek letter sigma. Since you wish to find out the average starting salary of all business graduates, hence your interest is in finding out mu, the population mean starting salary. If you had all the resources, you could go to each and every business student who graduated last year in New York City and ask them their starting salary. You could then accurately calculate the population mean starting salary by taking an average of all those numbers. However, clearly this is an onerous task. Instead, what you do is you select a random sample of say 100 students from this population and calculate the mean starting salary in this sample. Let us say that the mean annual salary in this sample is $61,400. In terms of standard notation, this is denoted by x bar. Thus, x bar is equal to 61,400, and there is some standard deviation s for this sample, which we will talk about later in the next course. Your aim is to somehow assess what the population mean salary is after observing this sample mean salary of $61,400. In other words, you wish to make some assessment about mu based on your observing x bar. This is where the central limit theorem is helpful. This is what the theorem states. Consider a random sample of n observations from a population. N could be any number. The mean of the population is mu and the standard deviation is sigma. Recollect, mu and sigma are standard notation for population parameters. Let x bar be the sample mean. Then the theorem states that the distribution of x bar is itself approximately normal, with the mean equal to the population mean and a standard deviation equal to the population standard deviation divided by square root of sample size. And this approximation gets better and better as the size of the sample increases, or in other words as n increases. What this means in our example is that the sample mean salary x bar that we observed to be $61,400 has itself a distribution with a mean equal to mu, the population mean salary you are interested in, and a standard deviation equal to sigma over square root of 100, where sigma is the population standard deviation and 100 is our sample size. This is how the sample is statistically linked to the population, and this link is the basis of all inferences that we make using a sample. Let us further understand this. What does it imply by saying that the sample mean x bar has a normal distribution? You took a sample of 100 students and found the sample mean to be $61,400. If your friend were also to take a random sample of 100 from the same population, the sample mean in your friend's sample is likely to be different, not exactly same as your sample mean. Let us say it is $62,200. Similarly, if a third friend were to take a random sample of 100 from the same population, he or she is likely to get yet another number, say $65,500. A fourth friend will get yet another number, and so on. Even though these various sample means are different from each other, yet they all are from the same population, which has a single population mean mu, which we do not know, and a population standard deviation sigma, which we also do not know. The statement that sample mean x bar has a normal distribution implies that there is a method to these various sample means that your friends are calculating. They all follow the same normal distribution. That is, if you were to plot a histogram of these various sample means, you will get a histogram in the shape of a bell curve. This histogram will be centered at the population mean mu, which you are interested in finding out. What this means is that with greater probability, you would get a sample mean closer to the population mean you are interested in, and with progressively lesser probabilities, these sample means will occur further away from the actual population mean. However, typically you do not take multiple samples. You will have to make inference about the population mean salary based on a single sample. This is where tools like the confidence interval estimation and hypothesis testing come handy. These will be introduced in the next course in this specialization on business statistics and analysis. The engine driving these tools though is the same, which is the central limit theorem. One final point about the central limit theorem. You may have noticed that the central limit theorem does not place any restriction on how the population data is distributed. Thus, irrespective of how the population data is distributed, whether it is continuous data, discrete data, irrespective of whether it is symmetric data or non-symmetric data, whether the population has a single mode or has multiple modes. No matter how the population data is distributed, the mean of a random sample from that population always has a normal distribution. In plain language, sample averages are normally distributed irrespective of where the sample came from. Not only are they normally distributed, but more importantly, they are normally distributed with mean equal to the population mean. The binomial distribution along with its Excel function is introduced in this lesson. This distribution is one of the two popular discrete distributions used across industries. The other distribution being the Poisson distribution, which we will introduce in a later lesson in this course. In the following 3 lessons of this course, we will introduce 2 more statistical distributions, the binomial and the Poisson distribution. These 2 distributions, though not as popular as the normal distribution, still are important because they represent 2 of the most popular discrete distributions. Recollect, we had mentioned that because of popularity of the normal distribution, it is often also used to approximate data which is discrete, even though the normal is a continuous distribution. That approximation is okay in a majority of cases. However, if greater accuracy is required, it is better to use a discrete distribution for discrete data. And the 2 often used discrete distributions are the binomial and the Poisson. We will begin by understanding the binomial distribution. We first need to understand something called a Bernoulli process. A Bernoulli process is any situation where the random variable has only 2 mutually exclusive outcomes. If an examination has only a pass or a fail grade, then that is a Bernoulli process. A coin toss is a Bernoulli process. Winning a lottery is a Bernoulli process. You either win it or you do not win it, and so on. It is often useful to consider multiple occurrences, also known as trials of the Bernoulli process. For example, consider a game of die where you win if you roll a 6. In all other cases, you lose. Thus, this game is a Bernoulli process because it has only 2 outcomes. Either you win, which is rolling a 6, or you lose. The probability of winning the game is 1 by 6 or 0.1667. That is a 16.67% chance that you will win the game. Of course, the assumption is that it is a fair die that you are rolling. You will be playing this game 10 times and you wish to assess your chances of winning. In particular, you wish to assess the probability that you will win at least 4 out of the 10 times you roll that die. Or you may be interested in finding out the probability that you win at least once. or maybe the probability that you win exactly 3 times out of 10, and so on. In this situation, you have a Bernoulli process which is winning or losing on one roll of a die, and you are considering 10 occurrences or trials of this Bernoulli process. The random variable now, instead of being winning on a single roll of a die, is rather the number of times you win when you roll the die 10 times, and this random variable is said to have a binomial distribution. So, repeated trials of a Bernoulli process gives rise to the binomial distribution. Binomial is a discrete distribution. When you roll the die 10 times, you can only win 0 times, 1 time, 2 times, 3, 4, 5, 6, 7, 8, 9 or 10 times, no number in between or beyond. For example, you cannot win 6.5 times, neither can you win 11 times when you roll the die only 10 times. A formal definition is as follows. Consider a situation where there are n independent trials, where the probability of success on each trial is p and the probability of failure is 1 minus p. Define the random variable uppercase X to denote the number of successes in n trials. Then this random variable is said to have a binomial distribution. In our example, n, the number of trials is 10, p, the probability of success in one trial is 0.1667. Note that the word success is how you define it. It could be any of the 2 outcomes of the Bernoulli process that you are interested in. In our example, we have defined success as getting a 6 on a roll. The random variable x here is the number of times you get a 6 when the die is to be rolled 10 times. The probability mass function for the binomial distribution is as shown. Recollect that this is a rule that assigns probabilities to various possible outcomes of the random variable in a binomial distribution. In the case of continuous distributions such as the normal, it is called the probability density function. However, here, since binomial is a discrete distribution, we call it the probability mass function. Uppercase X is the random variable, lowercase x represents various possible values that the random variable can take. In a binomial distribution, the random variable can take positive integer values ranging from a 0 till the number of trials. N and p are as defined earlier, the number of trials and the probability of success in a trial. The exclamation mark is the factorial calculation. We have a specific function in Excel that will calculate these various binomial probabilities. It is the binom.dist function. The syntax takes in 4 inputs. The first input is the number of successes for which you wish to calculate probability. The second input in the syntax is the number of trials that you have. The third input is the probability of success in one trial, and the last input is either false or true. You use false when you wish to calculate the probability that number of successes will be exactly equal to the first input in the syntax, and you use true when you wish to calculate the probability that number of successes will be less than or equal to the first input in the syntax. So, the probability that you win 3 times in 10 rolls of a die will be given by binom.dist open parenthesis 3, 10, 0.1667 false close parenthesis, which is equal to 0.1551. Note that here we do use the false option in the binom.dist function, unlike the case in the norm.dist function where we told ourselves that we will not be using the false option. The reason is that binomial is a discrete distribution, and hence talking about a situation such as the probability of random variable being exactly equal to 3 makes sense. Unlike the normal distribution, which is a continuous distribution, and the probability of a random variable being exactly equal to some number in a continuous distribution is always 0. The probability that you will win at most 5 times is equal to the probability that the random variable is less than or equal to 5, which is binom.dist 5, 10, 0.1667 true, a probability of 0.9976. Probability that you will win less than 5 times is the same as probability that you will win less than or equal to 4 times. Note that in the case of discrete distributions, probability of being less than equal to 5 is not the same as probability of being less than 5. They are different. So, our answer is binom.dist 4, 10, 0.1667 true, a probability of 0.9845 that you will win less than 5 times. But the same logic, probability of winning at least thrice is 1 minus the probability of winning at most 2 times, which is 1 minus binom.dist 2, 10, 0.1667 true, a probability 0.2249 or 22.49%. Continuing with our study of the binomial distribution, we work out a business application using Excel functions in this lesson. There are many business applications of the binomial distribution. Let us look at one such application. In the current tax year, IRS, the Internal Revenue Service of the United States, estimates that 5% of the many high net worth individual tax returns would be fraudulent. That is, they will contain errors that are purposely made to cheat the government. Although these errors are often well concealed, let us suppose that a thorough IRS audit will uncover them. Given this information, if a random 100 such tax returns are audited, what is the probability that exactly 5 fraudulent returns will be uncovered? Here n, the number of trials, is equal to 100, and p, the probability of a tax return being fraudulent, is 5% or 0.05. Thus, the probability that 5 fraudulent returns would be uncovered when IRS audits 100 returns is equal to binom.dist 5, 100, 0.05 false, a probability of 0.1800. Question 2. If a random 250 high net worth tax returns are audited, what is the probability that the IRS will uncover at least 15 fraudulent errors? N, the number of trials in this case is 250, p is still 0.05. Since the binom.dist function in Excel calculates the probability to the left, hence our required probability will be calculated as 1 minus probability that number of fraudulent returns uncovered is less than equal to 14, which is 1 minus binom.dist 14, 250, 0.05 true, the answer being 0.2712 or a 27.12% chance. Question 3. If a random 250 high net worth tax returns are audited, what is the probability that the IRS will uncover at least 15 fraudulent returns, but at most 20 fraudulent returns? We need to calculate the probability of number of fraudulent returns uncovered being less than equal to 20, but greater than equal to 15. This can be calculated using the binom.dist functions as follows: binom.dist 20, 250, 0.05 true minus binom.dist 14, 250, 0.05 true, a probability of 0.2563. The last question, what is the probability that out of the 250 randomly selected high net worth tax returns, no fraudulent return is uncovered? The answer here is binom.dist 0, 250, 0.05 false, which is a very small probability. In various applications of the binomial distribution, an important issue is to figure out the so called probability of success, which is an input in the binomial formula. Typically, this is where your past experience and data come in handy on the process which you are modeling as a binomial distribution. You could approximate the probability of success from your past data so that you can then make predictions for the future. The mean of the binomial distribution is n times p, the product of number of trials and the probability of success. The standard deviation is given by square root of n times p times 1 minus p. So, in our IRS tax returns example, the mean number of fraudulent tax returns that the IRS is likely to uncover when it randomly audits 250 high net worth individual tax returns is n times p, which is 250 multiplied by 0.05 equal to 12.5 returns. Notice that we get a fractional answer as the mean, which is okay. Means of discrete data can be fractional. For example, a family cannot have 3.14 members. However, on average an American family does have 3.14 members. After the binomial distribution, the second popular discrete distribution, the Poisson distribution, is introduced in this lesson. We get to know the Excel function for the Poisson and apply them to a business situation. We will now introduce the second popular discrete distribution commonly used in some business applications, the Poisson distribution. Some examples where the underlying random variable can be well approximated by the Poisson distribution. The number of fatal traffic accidents in a city in a particular week. The number of customers arriving at the store checkout line during a given hour. The number of defective items produced in a day on the assembly line of a farm equipment manufacturer. All these examples have a notion of discrete events occurring during some unit of time. The number of times they occur can be viewed as a random variable, and this random variable can be approximated by the Poisson distribution. There are some more assumptions which, if satisfied, make the approximation more accurate. I will leave that for you to explore on your own. The probability mass function for the Poisson distribution is as shown. Uppercase x is the random variable, lowercase x represents various possible values that the random variable can take. In a Poisson distribution, the random variable can take integer values ranging from 0 to infinity. So, that is one distinction from the binomial distribution, where recollect that the random variable takes values ranging from 0 till the number of trials n. The Greek letter lambda is the mean value of the random variable. It is also known as the parameter of the Poisson distribution, as it uniquely defines the distribution. It can take any positive value including fractions and decimals. Lambda, by the way, is also the variance of the Poisson distribution. Finally, the letter E is a constant equal to approximately 2.718. Actually, it is the base of the natural logarithm system. The function in Excel that will calculate these various Poisson probabilities is the Poisson.dist function. The syntax has three inputs. The first input is the discrete outcome at which you wish to calculate the probability. The second input in the syntax is the mean value of the random variable, the lambda value, and the last input is either false or true, depending on whether you wish to calculate the probability of the random variable being exactly equal to lowercase x or being less than or equal to that. Let us work out an example. A local convenience store uses a Poisson distribution to approximate the number of customers arriving each hour during weeknights at the only checkout counter at the store. From past data, it knows that on average 30.5 customers arrive per hour at the checkout counter during weeknights. What is the probability that 25 customers arrive at this checkout counter in a given hour during a weeknight? Here the value of lambda, the Poisson parameter, is equal to 30.5, since lambda is also the mean of the Poisson distribution. Thus, the probability of 25 customers arriving is given by Poisson.dist 25, 30.5, false, which is 0.0469 or 4.69%. What is the probability that fewer than 33 customers arrive at this checkout counter in a given hour during a weeknight? Probability that fewer than 33 customers arrive is the same as probability that less than or equal to 32 customers arrive. This is because Poisson is a discrete distribution and no value between 33 and 32 is possible. Thus, the answer is Poisson.dist 32, 30.5 true, which is a probability of 0.6511. What is the probability that the number of customers who arrive at this checkout counter in a given hour during a weeknight will be greater than 35? This is simply 1 minus the probability that less than equal to 35 customers arrive, which is given by 1 minus Poisson.dist 35, 30.5 true, a probability of 0.1810. So, this is how you can solve a variety of Poisson distribution applications using Excel.
So the final two sections of this course, we cover a lot of material that's fundamental to more sophisticated statistical analysis. And this material covers distributions, and in particular, we talk about the normal distribution. Right? And the reason why the normal distribution is such an important concept is that by using another concept that we learned, the central limit theorem, we can show that the normal distribution occurs all the time, anytime you want to summarize lots of repeated samples of data. And this is a concept that's used in regression analysis that's applied in pretty much every business setting where you want to do forecasting or you want to explain one outcome with another. For example, in the hotel industry, we did a lot of regression analysis to try to predict demand for a particular day. And this is really important when you want to decide what prices to set, how much inventory to release.
Hi there, welcome to the course. My name is Sharad Bodle and I am a faculty of management at the Jones Graduate School of Business at Rice University in Houston, Texas. The course is a part of the Business Statistics and Analysis Specialization, and this specialization through these various courses aims to develop a robust and practical understanding of various aspects of business statistics using the popular software Excel. The spreadsheet software Excel is an industry standard, and getting to apply all these skills, the business statistics skills using the software, would go a long way in its applicability to the industry. It is a great source of pride and joy when students come back and tell me how they were able to apply these courses at their workplace. It also helps in iterating these courses and making them relevant to today's business. The course that you are taking will give you ample opportunities in applying these various statistical tools to a variety of business applications. I am very passionate about teaching these courses. My own academic background is a very quantitative one. An undergraduate in engineering, an MBA in quantitative techniques, and finally a PhD from the Carnegie Mellon University in Pittsburgh. My own research deals with application of various statistical tools and quantitative methods to various issues and problems faced in the industry. In the following lesson, we introduce the t distribution, which is very similar to the standard normal distribution and has business applications in constructing confidence intervals and hypothesis testing, which are topics to be covered in later lessons in this course. We demonstrate the Excel functions associated with the t distribution, namely the t dot dist function. Before we introduce the confidence intervals and hypothesis testing, some very important business statistics tools, we need to introduce yet another continuous distribution, the t distribution. We introduced in course 2 of the specialization the most popular continuous distribution, namely the normal distribution. The normal is a symmetric continuous distribution with two parameters, the mean and the standard deviation. We also introduced the standard normal distribution, which simply is a normal distribution with a mean fixed at 0 and standard deviation fixed at 1. That is, it is a symmetric distribution centered at 0 with a fixed standard deviation. Another continuous distribution similar to the standard normal is the t distribution, also known as the student's t distribution. This distribution, just like the standard normal, is also a symmetric distribution centered at 0. That is, it has a mean equal to 0. However, the spread or the standard deviation of this distribution depends on a single parameter called the degree of freedom, commonly denoted by df. As this degree of freedom increases, the t distribution becomes closer and closer to the standard normal distribution. Accordingly, the t distribution is uniquely identified by this single parameter, the degrees of freedom. Let us take a look.
In this spreadsheet, we have two distributions. The dotted blue line is the standard normal distribution, that is a normal distribution with mean 0 and standard deviation 1. The graph with the red line is a t distribution, and in this case a t distribution with degrees of freedom 2. Let's see what happens if I change the degrees of freedom of this t distribution. So if I change it from 2 to 3 to 4 to 5, notice that the t distribution is getting closer and closer to the standard normal distribution. If I change it further, increase it further to 10, the degrees of freedom 10, maybe 15, maybe 20, it gets further close to the standard normal distribution. 25, if I increase it to 50, even more close to the standard normal. If I increase it to 100, so as you see, beyond certain point, the t distribution, as the degrees of freedom increase, is indistinguishable from the standard normal distribution.
The t distribution, unlike the normal distribution, does not have any standalone business applications. Rather, it is used as an interim tool for the calculations used in coming up with confidence intervals and hypothesis testing, which we will be introducing in subsequent lessons. Just like any statistical distribution, the t distribution also has an associated probability density function, a continuous density function. However, we will not be introducing the same in this lesson. You may look it up in any textbook or internet references. What we will introduce is the associated Excel functions to calculate various probabilities and outcomes using the t distribution. These are the t dot dist and the t dot inv functions. These functions are analogous to the norm dot dist and the norm dot inv functions we introduced in course 2 with reference to the normal distribution. The t dot dist function calculates the area under the curve or the probability in a t distribution to the left of a number. The syntax of the function is t dot dist, and it takes in 3 inputs. T dot dist, open parenthesis, the first input is the number to the left of which you wish to calculate the probability, in terms of notation typically denoted by lowercase x. Then you give the degrees of freedom and finally the word true. This would calculate the probability or area under the curve to the left of x. As with the normal distribution, in the t distribution, the possible values that the random variable which follows the t distribution can take ranges from negative infinity to positive infinity. So, if you wish to calculate the probability to the left of 1.3 in a t distribution with 21 degrees of freedom, you would use the syntax is equal to t dot dist 1.3 21 true. Let us illustrate this in Excel.
In the spreadsheet, we would type is equal to t dot dist open parenthesis 1.3 comma the degrees of freedom 21 comma true close parenthesis. So this would give us the probability to the left of 1.3 in a t distribution with degrees of freedom 21. And the answer is a probability of 0.8962 or a chance of 89.62%.
Similarly, if you wish to calculate the probability to the right of 1.3 in the same distribution, you would do a 1 minus t dot dist 1.3 21 true, using the fact that the area under the entire curve is always equal to 1, the answer being 0.1038. Extending the same logic, probability in the t distribution which has 21 degrees of freedom between -1 and 1.3 is the area under the curve between -1 and 1.3, which is calculated as is equal to t dot dist 1.3 21 true minus t dot dist -1 21 true, the answer being 0.7318. Remember, as with the usage of norm dot dist function, we will not be using the t dot dist function with the false option in the syntax. Some of you may wonder what are degrees of freedom. One way to understand it is to simply tell yourself that it is the parameter of the t distribution that uniquely identifies one t distribution from another. Just like in the case of a normal distribution, the combination of two parameters, the mean and standard deviation, uniquely identify one normal distribution from another. Another way to understand the degrees of freedom is to think of it as a mathematical constraint imposed by the data based on what we are trying to estimate from the data. This notion will become apparent when we put to use the t distribution as an interim calculation in subsequent lessons to come up with confidence intervals and hypothesis testing. Using this notion, the degrees of freedom get linked to the size of data being used. So, a t distribution using a larger set of data would have a greater degree of freedom than a t distribution using a smaller set of data. And as we have seen in this lesson, as the degrees of freedom increase, the t distribution becomes closer and closer to the standard normal distribution. So, this is the first Excel function associated with the t distribution, the t dot dist function. In the next lesson, we will introduce the second function, the t dot inv function. In this lesson, continuing from our previous lesson, we introduced and demonstrate the second Excel function associated with the t distribution. the t.inv function. We get to know its syntax and usage by way of examples. In the previous lesson, we introduced the t distribution, also known as the student's t distribution. We saw that it is a symmetric continuous distribution centered at 0 and has a single parameter called the degrees of freedom. As the degrees of freedom increase, the t distribution becomes closer and closer to the standard normal distribution. The standard normal distribution is a normal distribution with mean equal to 0 and standard deviation equal to 1. We also introduced the t.dist function in Excel to calculate probabilities to the left of any point in the t distribution. The t.dist function is analogous to the norm.dist function in Excel to calculate probabilities to the left of a point in the normal distribution. We will now introduce the second Excel function associated with the t distribution, the t.inv function, which is similar to the norm.inv function of Excel for the normal distribution. The t.inv function for the t distribution calculates an inverse of what a t.dist function does. As mentioned earlier, the t.dist function calculates a probability to the left of any particular point in a t distribution. In using the t.dist function, you know the point in the t distribution and wish to calculate the probability to the left of that point. An inverse situation would be when you are given the probability and you wish to calculate the point which cuts off that probability to its left. This is where the t.inv function gets used. The syntax is as shown, is equal to t.inv open parenthesis, then the probability to the left, comma, and the degrees of freedom close parenthesis. For example, to calculate the point that cuts off 0.05 probability to the left of a t distribution with 15 degrees of freedom, you would use is equal to t.inv 0.05 15.
So, in the spreadsheet you will type this command is equal to t.inv open parenthesis 0.05 comma 15. So, this would give you the number, the outcome in a t distribution with 15 degrees of freedom that cuts off 0.05 probability to the left of it, and that number is a negative 1.753.
Similarly, if you wish to find out the point in the same t distribution that cuts off 0.05 probability to the right, you would use the syntax as shown, is equal to t.inv 1 minus 0.05 15.
So, in the spreadsheet you will type in is equal to t.inv open parenthesis 1 minus 0.05. You could also have typed in 0.95 comma the degrees of freedom 15 close parenthesis. So, this would give you the outcome in a t distribution with 15 degrees of freedom that cuts off 0.95 probability to the left of it, or in other words the number that cuts off 0.05 probability to the right of it, and that number is a positive 1.7531. Notice this is a mirror image of the number that cuts off 0.05 probability to the left of it, which was a negative 1.7531.
A few more pointers before we close the lesson on the t distribution. A t distribution is symmetric about the value 0. Half of the distribution is to the right of 0 and the other mirror half to the left of 0. This means the probability cut off to the left of any negative number is exactly equal to the probability cut off to the right of its positive mirror image. For example, in a t distribution with 11 degrees of freedom, the probability cut off to the left of negative 2.1 is exactly equal to the probability cutoff to the right of positive 2.1. In the same vein, in any t distribution, the probability cutoff to the left or right of 0 is 0.5, since the t distribution is symmetric about 0. So, to conclude, these two functions t dot dist and t dot inv will allow us to use the t distribution in various business applications where the distribution is used as an interim calculation. This lesson introduces the confidence interval, a very useful way of incorporating uncertainty in business predictions. The confidence interval is introduced by way of examples, and we get a conceptual understanding of the confidence interval, a necessary step before we can construct our own confidence intervals. Let us start with a conceptual understanding of what a confidence interval is. The name consists of two words, confidence and interval. So, simply put, a confidence interval is an interval with some confidence or probability attached to it. What is this interval for? It is for some unknown characteristic of the population data which may be of interest to us. For example, before the US presidential polls, there are many pollsters who, based on surveying a sample of voters, would like to predict the actual share of votes for a particular candidate. This actual share of votes is a population characteristic unknown to us before the election actually happens. Yet we are interested in knowing something about it. Let us say candidate A and candidate B are the only two candidates for the US presidential polls, and a pollster is interested in making a prediction about the percentage of votes that candidate A is likely to get. The pollster surveys a random selection of 500 potential voters and asks them their voting preference between candidate A and candidate B. An implicit assumption, of course, is that the voters are truthful and they are not lying. Let us say 300 potential voters say that they will vote for candidate A and the remaining 200 say that they will vote for candidate B. That means 60% of surveyed voters favor candidate A. An important distinction here is that this 60% is from a sample of voters. Would this 60% be equally valid for the entire voting population? Will candidate A get 60% of all votes in the actual election? This is where the concept of a confidence interval comes in. Based on this example just given, a 95% confidence interval for the actual proportion of voters would be between 55.7% and 64.3%. We will get at how we did this calculation in a later lesson, but let us interpret this confidence interval for now. This confidence interval is for the population proportion, that is the proportion of the entire voting population that will vote for candidate A. What it tells us is that if we repeatedly did this exercise of sampling 500 potential voters and asking them about their voting preference between candidates A and B, and every time we constructed the confidence interval, then 95% of the times the constructed confidence interval would have the actual proportion of the entire voting population that would vote for candidate A. This sometimes is loosely also interpreted as saying that there is a 95% or 0.95 probability that the actual vote share for candidate A will be between 55.7% and 64.3%. The interval that is shown, 55.7% through 64.3%, has 60% in the exact center. Adding 4.3% to 60% gives us the upper limit of the interval, which is 64.3%. And subtracting 4.3% from 60% gives us the lower limit of the interval, which is 55.7%. This 4.3% difference up and down from 60% is known as the margin of error for a 95% confidence interval. Many a times, and typically in textbooks, this is interpreted as saying that we are 95% sure that the true voting percentage in the entire population for candidate A is between 55.7% and 64.3%. You all must have seen such kind of poll predictions being made in various contexts. Though in the popular press and media, many a times the interval or the confidence level is not reported, and what gets reported is the single number. In our example, 60%. Clearly, a single number can be misleading, and a confidence interval gives us a much more relevant estimate of what the actual proportion of voters might be. Let us take a look at another example. We had used this example in a lesson in course 2 of the specialization in the context of introducing the central limit theorem, one of the foundational concepts in business statistics. In that problem, we wanted to find out the average starting salary across all business students who graduated last year in a big city like New York City. The relevant population in this case is large, the set of all students in New York City who finished their business education last year. Clearly, calculating the population average or mean would be very difficult, because to calculate the population mean, we will need to access the entire population. In terms of notation, the population mean is typically denoted by the Greek letter mu, and the standard deviation in the population data is denoted by Greek letter sigma. Our interest here is in getting to know something about this mu, or the population mean salary across the entire population of business students who graduated last year in New York City. Without accessing each and every member of this population, we cannot exactly calculate this population mean. However, what we can do is to probabilistically assess what the likely values of this population mean is by constructing a confidence interval. What we do is that we select a random sample of, say, 100 students from this population and note down their starting salaries. We then calculate the mean starting salary in this sample. Let us say that this mean annual salary in this sample is $61,400. In terms of standard notation, this is denoted by x bar. Thus, x bar is equal to 61,400. Also, in terms of notation, the standard deviation in the sample data is denoted by lowercase s. Our aim is to somehow assess what the population mean salary is after observing the sample mean salary across 100 students to be $61,400. This is where a confidence interval is useful. We could construct a confidence interval for this unknown population mean using the information we have from the sample. The confidence interval would have an upper limit, a lower limit, and some probability or confidence attached to the interval. The upper limit is the sample mean plus margin of error, and the lower limit is sample mean minus margin of error. We will see in a later lesson how do we calculate these margins of error. So, this is how a confidence interval is a way to incorporate uncertainty in our assessment of the population mean in which we are interested. In this lesson, we get to see yet another example of application of confidence intervals, a very different example from the hurricane season in Texas, the aim being to solidify our conceptual understanding of the confidence interval. In the previous lesson, we introduced the concept of confidence intervals using two examples. One example was the pollster trying to make prediction about the proportion of votes for a particular candidate, and the other example was trying to figure out the average starting salary across all business students who graduated last year in New York City. In the first example, confidence interval would be for a population proportion. since our quantity of interest is a proportion, the percentage or proportion of votes polled by a particular candidate. In the second case, the confidence interval would be for a population mean, because we are interested in assessing the population mean starting salary across all business graduates last year from New York City. This distinction between confidence interval for a population mean and confidence interval for a population proportion is made because, as we will see later in the course, the calculation for the two are slightly different. Let us look at one more example of a confidence interval, an example from the hurricane season. Every year, June through November is the hurricane season in Texas. Hurricanes develop in the Gulf of Mexico, and some of them gather strength and may strike or make a landfall at the Texas coastline. Hurricanes can cause great damage, and an impending hurricane is of intense interest not only to the meteorologist, the weather person, but also to the general population. One such hurricane, called Ike, struck Texas in the year 2008 and caused a lot of damage. The hurricane made landfall in Galveston, a small coastal town close to Houston in Texas. Galveston and parts of Houston were badly hit during the hurricane. While the hurricane was developing in the Gulf of Mexico and moving towards the Texas coastline, the weather people or meteorologists were constantly trying to predict where would the hurricane actually strike, or in other words, where would it make a landfall. This is important because then the state administration can take appropriate preventive measures in those areas to safeguard lives and property. Predicting the exact place where the hurricane will strike is fraught with uncertainty, as is the case with any business decision, which is also almost always made under some level of uncertainty. So, how do weather people or meteorologists incorporate this uncertainty in their prediction? This is done by giving out an interval prediction rather than a point prediction, and this interval prediction is nothing but another example of a confidence interval. Let me explain this. So, this is the Texas coastline. We have Houston somewhere here, and then a small coastal town close to Houston, Galveston, and then the sea out here is the Gulf of Mexico. So, every now and then during hurricane season, hurricanes develop in the Gulf of Mexico, and some of them may move towards the Texas coastline. So, let us take example of one such hurricane that struck Texas in 2008, Hurricane Ike. So, as Ike was moving towards the Texas coastline, there was intense interest in trying to predict exactly where the hurricane would make a landfall. This prediction, like any other prediction, is fraught with uncertainty. It is always very difficult to predict exactly where the hurricane would strike. So, rather than making a point prediction, the meteorologists or the weather people were making prediction in terms of an interval called the cone of prediction. So, rather than making a prediction in terms of a particular point, what they predicted was that the hurricane is likely to strike between points A and B on the coastline, and this entire region between A and B is nothing but an example of a confidence interval. In particular, a confidence interval for the exact point where Hurricane Ike would strike the Texas coastline. And of course, there is some probability or confidence level attached to this interval. So, that wraps up our conceptual understanding of what a confidence interval is. In a subsequent lesson, we will introduce the calculation required to construct confidence intervals. The z statistic and t statistic are introduced in this lesson. They are some of the basic building blocks of business statistics and are needed to construct confidence intervals. We talk about the calculation for these two statistics and the differences between them. Before we study the calculations for confidence intervals, we need to introduce some background stuff, namely two expressions known as the z statistic and the t statistic. When we covered the central limit theorem in the second course of the specialization, we learned that the central limit theorem is a very important link between a population and a sample. In particular, it says that if we have a population data with some unknown population mean mu and a population standard deviation sigma, and then if we draw a random sample of size n from this population data, then the sample mean of that random sample has a normal distribution with a mean equal to the population mean and a standard deviation equal to the population standard deviation divided by the square root of sample size. In terms of notation, it is as shown, where x bar is the sample mean, mu is the population mean, sigma is the population standard deviation, and n is the sample size. Further, this expression can be mathematically rearranged as shown. Recollect, this was discussed when we were studying the normal distribution and its properties in second course of this specialization. The resulting expression, which is circled, has a standard normal distribution, that is a normal distribution with mean equal to 0 and a standard deviation equal to 1. This expression is also known as the z statistic. So, a z statistic in the context of a population and a sample from that population, where we are interested in inferring something about the population mean, is calculated as shown, and this z statistic has a standard normal distribution, that is a normal distribution with mean 0 and standard deviation 1. This z statistic will form the basis of our calculation for a confidence interval for the population mean. Our quantity of interest is the population mean, which is unknown, and we wish to build a confidence interval for it. However, notice that in using this z statistic, we also have the population standard deviation sigma in the denominator. So, what it implies is that if we are going to use the z statistic to build a confidence interval for the unknown population mean, we need to know the population standard deviation. Now, if we do not know the mean of population data, it is highly likely that we would not know the standard deviation or variability of the population data also. However, if we are using the z statistic in our calculation, we do need a value for the population standard deviation, the sigma. So, a more realistic scenario is where we do not know the standard deviation or variability of the population data. In such cases, in the calculation for the z statistic, we replace the population standard deviation sigma with the sample standard deviation small case s. Remember, the sample data is something you have access to, and hence you can easily calculate the sample standard deviation in Excel using the stdev.s command. However, the problem comes that when we replace the population standard deviation in the expression for the z statistic with the sample standard deviation, the resultant expression, which is x bar minus mu divided by s by square root of n, no longer has a standard normal distribution. Rather, this new expression obtained by replacing population standard deviation by the sample standard deviation has a t distribution with n minus 1 degrees of freedom, where n is the sample size. There is a derivation behind it which we do not need to know in this course. This new expression is called the t statistic. So, a t statistic follows a t distribution, and in our case here a t distribution with n minus 1 degrees of freedom, where n is the sample size. Remember, a t distribution is a continuous symmetric distribution centered at 0 and has a single parameter known as the degrees of freedom. These two expressions, the z statistic and the t statistic, will be used in calculating confidence intervals. When do we use the z statistic and when do we use the t statistic? Whenever we somehow know the standard deviation of the population data, that is a numerical measure of the variability in population data, then we use the z statistic. Whenever we do not know the population standard deviation and are using the sample standard deviation instead, we use the t statistic. It may be noted that typically in most business applications we would not know the population standard deviation and hence end up using the t statistic to construct confidence intervals. This lesson gives us the calculations required for constructing confidence intervals for a population mean. The calculations are laid out using a simple stylized example. The results are interpreted and discussed. Now that we have introduced the z statistic and the t statistic, we will use them to construct confidence intervals. Let us do so by way of a stylized example. A random sample of 20 observations from a population data had a mean equal to 70. The standard deviation of the population data is 10. Find a 85% confidence interval for the population mean. In this problem, the sample mean is 70, the sample size is 20, and somehow magically we know the population standard deviation, which is equal to 10. Note that this is a stylized example and we are using it to introduce the calculation for confidence intervals. We will relax this assumption of knowing the population standard deviation in subsequent problems. Sometimes people interpret the problem as wanting to come up with an interval such that the probability of the population mean being in that interval is 85%. So, the probability outside the interval is 15% or 0.15, and this probability is referred to as Greek letter alpha. So, alpha is the probability outside the confidence interval, and we are wanting to construct a 1 minus alpha confidence interval for the population mean. Here, since we know the population standard deviation, we will be using the z statistic in our calculation, and the confidence interval is as shown. We have skipped the derivations and are straight away providing the calculation and the intuition behind the calculation. The unknown population mean mu lies between two numbers, a lower number on the left and an upper number on the right. These lower and upper limits are constructed by subtracting and adding the margin of error from the sample mean x bar. Let us examine this margin of error. It is a product of the absolute value of z subscript alpha by 2 times sigma over square root of n, where sigma is the population standard deviation and n is the sample size. Z subscript alpha by 2 is that value of the z statistic that cuts off alpha by 2 probability in a standard normal distribution. Recollect that the z statistic follows the standard normal distribution, a normal distribution with mean 0 and standard deviation 1. So, z subscript alpha by 2 is calculated as norm dot inv alpha by 2 0 1, In our case, alpha is equal to 0.15 because we want a 85% confidence interval, and alpha is the probability outside the confidence interval. So, the calculation becomes norm dot inv 0.15 divided by 2 comma 0 comma 1, which is equal to a negative 1.4395, and its absolute value is a positive 1.4395. The margin of error then becomes the absolute value of the z statistic, which is 1.4395 multiplied by 10 divided by square root of 20. 10 is the population standard deviation and 20 is the sample size. The margin of error calculation gives us the error to be 3.2189. Our 85% confidence interval for the population mean then becomes as shown. The lower limit is x bar minus the margin of error, and the upper limit is x bar plus the margin of error, giving us the interval 66.78 through 73.22. The correct interpretation of this interval vis-a-vis the population mean is that if this process of taking random samples of 20 from the population and then constructing a 85% confidence interval was repeated multiple times, then 85% of the times our interval would contain the actual population mean. However, another interpretation which many find useful is that there is an 85% chance that the actual population mean lies in the interval that we calculated, that is between 66.78 and 73.22. What happens if we wish to increase the confidence level of the interval? Say we wish to construct the interval for the population mean with a 95% confidence. In terms of calculations, all our calculations remain the same except that the value of the z subscript alpha by 2 changes. The new value for alpha, which is the probability outside the confidence interval, is 0.05 or 5%, and z alpha by 2 is now that value of the z statistic that cuts off 0.05 by 2 or 0.025 probability in a standard normal distribution. Calculating this gives us a value of z alpha by 2 to be a negative 1.96 and an absolute value of a positive 1.96. And going through the set of calculations results in the 95% confidence interval being 65.62 through 74.38. Similarly, if we wish to calculate a 99% confidence interval for the population mean from the same sample data, in this case alpha being equal to 0.01, the interval will turn out to be 64.24 through 75.76. Notice that using the same sample data, if we wish to construct intervals for the population mean with greater confidence levels, what happens is the interval keeps widening, or in other words there is a trade-off involved. We are trading off precision, the interval widens, with the gain in confidence level or reduction in uncertainty. In the extreme, if we want to be 100% confident or 100% sure of the interval, then the interval would turn out to be negative infinity through positive infinity, or in other words we are saying that we are certain that the population mean lies between negative infinity and positive infinity, which clearly is an interpretation without any use. A few more pointers about the confidence intervals. When we say that the 95% confidence interval for the population mean is from 65.62 to 74.38, does it imply that we have ruled out any values greater than 74.38 or less than 65.62? Certainly not. Those values are possible, though less likely. Further, are all values in the interval equally likely? Again, the answer is no. We have a bell-shaped distribution centered at the sample mean 70. So, values closer to the sample mean are more likely. If I were to bet on one particular number as being the population mean, I would bet on the sample mean.
Hi, my name is Catherine Butler, and I'm a student at Rice University's Jones Graduate School of Business. As we saw in the videos this week, confidence intervals are a useful business tool. They can help business people make decisions by removing uncertainty from some predictions. Let's say, for example, that you have a sample of sales from some of the restaurants that your company owns. With the information available to you, you can determine the amounts of products or ingredients that you want across the different restaurants to reach a certain level of certainty and to make sure you don't run out of these ingredients, whether you want to be 80% sure or 100% sure. By utilizing these confidence intervals, you can help your company remove some of the uncertainty involved with the decision making.
This lesson reviews the calculations required for constructing confidence intervals for a population mean and introduces the Excel functions confidence.norm and confidence.t, which are specially tailored for such calculations. We also work out an application involving the confidence interval for a population mean. In our study of the confidence interval, we have so far had a conceptual understanding of the confidence interval, looked at a few examples, and also solved a stylized problem in which we constructed the confidence interval for the unknown population mean. We use this example to introduce the calculation for the confidence interval for a population mean. This is as shown. Alpha is the probability outside the confidence interval. For example, alpha would be equal to 0.05 for a 0.95 or 95% confidence interval. Mu is the unknown population mean for which we wish to create a confidence interval. X bar is the sample mean obtained from a sample of data, and the dotted underlined expression is the margin of error, which itself is constructed of the absolute value of z alpha by 2, which is the value of the z statistic that cuts off alpha by 2 probability in a standard normal distribution. The Excel function for which is norm dot inv alpha by 2 0 1. This is then multiplied by sigma, the population standard deviation, and divided by the square root of sample size. There also happens to be an Excel function that calculates this margin of error. The function is confidence.norm, and it takes in 3 inputs: alpha, which is the probability outside the confidence interval, the population standard deviation sigma, and the sample size n. So, there are 2 ways of calculating the margin of error, either using this confidence.norm function or doing the calculation of z alpha by 2 multiplied by sigma by square root of sample size. So, x bar or sample mean minus the margin of error gives us the lower limit of the confidence interval, and x bar or sample mean plus margin of error gives us the upper limit. One thing to be noted here is that the calculation for confidence interval for the population mean uses the z statistic. This is because we have the population standard deviation in the calculation, implying that we need to know its value to calculate the confidence interval. In situations where we do not know the population standard deviation, we replace it with the sample standard deviation, and the z statistic, as was discussed in an earlier lesson, gets replaced by the t statistic. The calculation for the confidence interval then becomes as shown. where lowercase s is the sample standard deviation and t alpha by 2 is the value of the t statistic that cuts off alpha by 2 probability in a t distribution with n minus 1 degrees of freedom. The Excel function for t alpha by 2 being t dot inv alpha by 2 n minus 1. The margin of error now is the absolute value of t alpha by 2 times sample standard deviation by square root of sample size. And there is also an Excel function to directly calculate this margin of error, which is confidence dot t. And this function takes 3 inputs: alpha, the probability outside the confidence interval, s, the sample standard deviation, and n, the sample size. Note that this function is analogous to the confidence dot norm function used to calculate the margin of error when using the calculation with the z statistic. Let us work on an application. A person wishes to explore the size of single family houses that are typically available for purchase in a particular neighborhood of Houston in Texas. She manages to get hold of a list containing house sizes of a sample of 100 houses that were sold in the past 2 years in this particular neighborhood. The data is provided in the Excel data file homesizes.xlsx. And given this data, she wishes to assess the average size of houses typically available for purchase in this neighborhood. Let us take a look at this data.
This file homesizes.xlsx contains house sizes of a random selection of 100 houses sold in the past 2 years in a particular neighborhood of Houston in Texas. The units of measurement of home sizes are in square feet.
Note that she does not have an exhaustive list of houses and their sizes for this neighborhood, or in other words, she does not have the population data on house sizes. All she has is a sample of 100 house sizes from that population data, and based on this sample, she wishes to assess the average size of houses. Here, she could construct a confidence interval for the average house size, and we will shortly construct this confidence interval using a confidence level of 95%, which is typically used in industry applications. A confidence level of 95% implies our value of alpha, which is the probability outside the confidence interval, is 0.05 or 5%. In this application, there is no information on the variability of house sizes across the population of houses in this neighborhood, or in other words, we do not know the population standard deviation for house sizes in this neighborhood. However, we can calculate the variability in the sample of 100 houses, or in other words, we can calculate the sample standard deviation for the house sizes across this sample of 100 houses. Thus, in terms of calculating the confidence interval, we need to use the calculation that uses the t statistic rather than the z statistic. This is because we only know the sample standard deviation and not the population standard deviation. Let us demonstrate these calculations.
So this is the formula that we'll be using. Once again, we use the formula with the t statistic because we do not know the population standard deviation and instead would be using the sample standard deviation. To calculate this formula, we need to first calculate the following expressions. So let's do that. X bar is a sample mean. So we do a is equal to average, open parenthesis, we select the set of data A2 through A101, close parenthesis. So our sample average is 3238.24 square feet. Let's calculate the t statistic, the t alpha by 2. The formula for that is t dot inv open parenthesis. The first input is alpha by 2. So in our case, alpha is 0.05 because we wish to construct a 95% confidence interval, and alpha is the probability outside the confidence interval. So 0.05 divided by 2. The second input it takes is the degrees of freedom, which is sample size minus 1. So in our case, the sample size is 100, so 100 minus 1 is 99. So that's our t alpha by 2, or negative 1.98422. Our sample standard deviation, we can use the stdev dot s function in Excel. Select the data, the set of 100 data points that we have. So that's our sample standard deviation, 957.67 square feet. Our sample size, of course, is 100. Margin of error can now be calculated as the absolute value of the t statistic. So we could either simply put a positive 1.98, or we could use a function in Excel called ABS. So it calculates the absolute value of the number. So ABS, we select this calculated t statistic multiplied by sample standard deviation. We pick up the sample standard deviation divided by the square root of sample size. So you could either directly put in 10, which is the square root of 100, or you could use the sqrt function in Excel. Sqrt, the sample size, and close parenthesis. So that gives us the margin of error of 190.02 square feet. We could have also calculated the margin of error using the confidence dot t function in Excel. So this function, confidence dot t, takes in 3 inputs. The first input is alpha as it is, which in our case is 0.05. Second input is the sample standard deviation, which we have already calculated there. So we simply pick up that particular cell, in my case cell E14, comma. The third input is the sample size, which in our case is 100. So confidence.t, open parenthesis, alpha, then the sample standard deviation, and then the sample size. So this gives us the same margin of error, 190.0226. So you could use either of the two approaches to calculate the margin of error. Now with this margin of error, we'll calculate the confidence interval, the lower and the upper limits. So the lower limit is nothing but sample average x bar minus the margin of error. That gives us a lower limit of 3048.2 square feet. Upper limit similarly is calculated as x bar, which is my sample average, plus the margin of error. So my upper limit of the confidence interval is 3428.3, if you round it off, square feet.
Given this confidence interval, she concludes that there is a reasonable probability, a confidence level of 95%, that the average house size in this neighborhood falls in the interval 3048.2 square feet through 3428.3 square feet. This lesson introduces the calculations for constructing a confidence interval for a population proportion as contrasted to a population mean. The calculations are introduced and explained by way of an example. We will now work out an example of a confidence interval involving population proportion rather than the population mean. While introducing the topic of confidence intervals in a past lesson, we had given an example of polling percentage or proportion and a confidence interval for that. However, we did not introduce the calculations for that. What we did introduce were calculations for calculating a confidence interval for an unknown population mean. There were two variants of those calculations, one using the z statistic and the other using the t statistic. We use the variant with the z statistic when we know the population standard deviation, and we use the variant with the t statistic when we do not know the population standard deviation and are replacing it with the sample standard deviation. To introduce the calculations for a confidence interval involving a population proportion, let us use an example. A consultancy firm surveyed a randomly selected set of 210 CEOs of fast growing small companies in the US and Europe. Only 51% of these executives had a management succession plan in place. The remaining did not have one. Now, such succession plans are important because an unexpected exit of a corporate leader can disrupt and unfocus a company for long enough to cause it to lose its momentum. Use this information to compute a 90% confidence interval to estimate the proportion of all fast growing small companies that have a management succession plan. In this problem, we have information on the availability of a management succession plan from a random selection of 210 fast growing small companies. The population of these so called fast growing small companies is very large, and we have a sample of 210 from that. In this sample, 51% companies had a succession plan. This 51% is a sample proportion. Our interest in the sample proportion is only limited to the extent that it allows us to make some inference about the population proportion, which is of our real interest. Since we cannot access the entire population, we have to make some probabilistic assessments about the population proportion using sample information. This is where a confidence interval for the unknown population proportion comes in. The formula for this confidence interval is as shown. In terms of notation, lowercase p is the population proportion which is not known to us, and we are trying to make some probabilistic assessments about it. In this example, p would be the actual proportion of all fast growing small companies in the US and Europe who have a management succession plan. Since we do not have access to all such companies, hence this population proportion is unknown to us, and we wish to assess it using the sample information we have. Lowercase p with a hat on it is the sample proportion from our sample. In our example, it will be 0.51 for 51%. This is the proportion of fast growing small companies in our sample that have a succession plan. N is the size of our sample, in our case 210. And finally, z alpha by 2 is our familiar z statistic, that value of the z statistic that cuts off alpha by 2 probability in a standard normal distribution, alpha being the probability outside the confidence interval, which in this example would be 0.10 or 10%, since we need a confidence interval of 90%. The calculation of absolute value of z alpha by 2 times square root of p hat times 1 minus p hat divided by n is also the margin of error for this interval. Let us calculate this interval.
So this is the formula for a confidence interval for a population proportion, and to evaluate this confidence interval, to calculate it, we need to calculate these expressions first. So let's do that. P hat is the sample proportion In our case, the sample proportion is already given to us, which is 51% of 0.51. This is the sample of companies that have a management succession plan in the sample of 210, 51%. So p hat is 0.51. Our value of alpha is 10% or 0.1 because we need to build a 90% confidence interval for the population proportion. So our z statistic or z alpha by 2 becomes norm.inv open parenthesis alpha by 2. Alpha is 0.1. Alpha by 2 divided by 2, comma, the mean of the standard normal 0, comma, the standard deviation of the standard normal 1, close parenthesis. So that's the formula for the z alpha by 2. So our z statistic or z alpha by 2 is a negative 1.64485. Our sample size is already given to us. Sample size consists of 210 companies. The margin of error is calculated as per this formula shown here. So let's do that. Is equal to the absolute value of the z statistic. We can use the Excel function ABS, which stands for absolute value. Open parenthesis, we pick up the calculated z statistic multiplied by square root of an expression which is p cap times 1 minus p cap divided by sample size. So we once again we use the Excel function sqrt, which stands for square root, open parenthesis, p hat, we pick up the p hat value, times 1 minus p hat divided by the sample size. We pick up the sample size 210, close parenthesis. So that's the expression within the square root and enter. So our margin of error becomes 0.056741. Confidence interval calculation. So the lower limit of the confidence interval is nothing but p hat minus the margin of error, and the upper limit is p hat plus margin of error. So the lower limit is p hat minus the margin of error, which is 5.67%, and the upper limit is p hat plus the margin of error. So that gives us a confidence interval for the population proportion.
So the 90% confidence interval for the population proportion or percentage of all fast growing small companies in the US and Europe that have a management succession plan in place is from 0.453 to 0.567, or in other words from 45.3% to 56.7%. This wraps up our discussion of confidence intervals. To recap, we introduced 3 calculations for the confidence intervals. 2 of them are for the unknown population mean and the third for the unknown population proportion. The 2 confidence interval calculations for the population mean either use the z statistic or the t statistic depending on whether you know or do not know the population standard deviation. The confidence interval calculation for the population proportion does not need the population standard deviation and uses only the z statistic. This lesson and the next lesson consider an important question of how big a sample should be taken. This is an often asked question in the industry. We understand the science behind it and introduce calculations to find out an appropriate sample size for your application. A common question often asked is how big a sample should I take from the population data. For example, if a pollster needs to make a prediction about a particular candidate's vote share in the US presidential election, then how many voters should the pollster survey to make this prediction? Another example, a quality control manager at a battery manufacturer wanting to estimate the average number of defective batteries contained in a box shipped by the company. How many boxes does she need to open to figure out the average number of defective batteries contained in a box? Here again the question is of how big a sample should be taken, how many boxes should be opened and defectives noted to assess some population parameter. In this case, the population parameter being the average number of defective batteries in a box. Note that in the production process, some boxes may have no defectives, some boxes may have one defective battery, two defective batteries and so on. What we are interested in is the average number of defectives in a box. Typically, you would see some heuristic rules in the industry to determine sample sizes. Different industries may have different rule of thumb strategies for sample size selection. However, let us here try to understand the science behind sample size consideration. Our population parameter of interest in most of the cases is either the population mean or the population proportion, and in previous lessons we built confidence intervals for both of them. Sample size calculations use these confidence interval formulas, and these calculations depend on two important factors. They are the margin of error and the level of confidence. For example, the pollster, while predicting the proportion of votes for a particular candidate, may want to have a margin of error plus minus 3% with a confidence level of 95%. That is, the pollster wishes to be 95% confident that the prediction would be within plus minus 3% from the actual proportion of votes. Similarly, the quality control manager, while estimating the average number of defective batteries contained in a box, may want to assess this population parameter, the average number of defectives in a box with a margin of error of plus minus 0.3 batteries and a confidence level of 95%. That is, she wants the average number of defectives she observes using a sample of boxes, the sample mean, to be within plus minus 0.3 of the true average number of defective batteries in a box, the population mean, and she wants to be 95% confident of this. Let us work this problem. As mentioned, the quality control manager wants to estimate the average number of defective batteries contained in a box shipped by the company. How many boxes does she need to open to figure out the average number of defective batteries contained in a box? The manager has already determined that she wants a margin of error to be within plus minus 0.3 batteries from the true average number of defective batteries in a box, and she wants to be 95% sure of this. That is, she wants a confidence level of 95%. By the way, 95% is a typical level of confidence used in the industry. To calculate an appropriate sample size, she needs one more piece of information. She needs some assessment of variability in the number of defective batteries in a box across the manufacturer's entire production, or in other words, some knowledge about the population standard deviation for the number of defective batteries in a box. Note that it is unlikely you would know the standard deviation of a population. However, sample size calculations do require a number for the population standard deviation. A reasonable approximation may come from the manager's past experience with the production process and the defective rates. Some past samples may have been taken, and we could use that sample standard deviation as an approximate population standard deviation. Whatever we do, in the end we do need a number for the population standard deviation of number of defective batteries in a box, else we will not easily be able to calculate an appropriate sample size. So, in our example, the quality control manager, based on some past samples taken, arrives at the population standard deviation or the variability in the number of defective batteries per box to be 0.9 batteries. With these three information, firstly the margin of error, secondly the confidence level, and thirdly the population standard deviation, let us look at the confidence interval calculation. The margin of error, the circled expression, is equal to 0.3. This in turn is equal to the absolute value of z statistic times population standard deviation divided by square root of sample size. Since the confidence level is 95%, the alpha value becomes 5% or 0.05. Remember, alpha is the probability outside the confidence level. Knowing alpha, we can calculate the absolute value of z statistic in Excel as the absolute value of norm dot inv 0.05 divided by 2, 0, 1, which is equal to 1.96. We know the population standard deviation to be 0.9. Thus, the margin of error 0.3 is equal to 1.96 times 0.9 divided by the square root of sample size. The square root of sample size then becomes 1.96 times 0.9 by 0.3, which is 5.88, and finally the sample size is the square of 5.88, which when rounded up gives us the size as 35, implying that the manager needs to sample, that is open, a random selection of 35 boxes. That is the appropriate sample size for this application to assess the average number of defective batteries in a box. This lesson continues from the previous lesson and introduces sample size selection considerations and calculations when your interest is in some population proportion rather than the population mean. This is explained using an example. Continuing with our sample size calculations from the previous lesson, we will now calculate an appropriate sample size when the population parameter of interest is a proportion rather than a mean. The example we considered was a pollster making a prediction about a particular candidate's vote share in the US presidential election. The question was, how many voters should the pollster survey to make this prediction? The pollster, while predicting the proportion of votes for a particular candidate, wants to have a margin of error plus minus 3% with a confidence level of 95%. That is, the pollster wishes to be 95% sure or confident that the prediction would be within plus minus 3% from the actual proportion of votes. Let us look at the confidence interval calculation for a population proportion. The margin of error, the circled expression, is equal to 0.03. This in turn is equal to the absolute value of z statistic multiplied by square root of p hat times 1 minus p hat divided by square root of n. Our alpha value is 0.05 since the confidence level is 95% or 0.95. So, the absolute value of z statistic turns out to be the absolute value of norm dot inv 0.05 by 2, 0, 1, which is equal to 1.96. Rearranging the calculations, we get n, the sample size, to be equal to the square of 1.96 divided by the square of margin of error 0.03. This whole expression multiplied by p hat times 1 minus p hat. So, to calculate the sample size, we do need a value for p hat. There is a circular argument here, because p hat, which is the sample proportion or the percentage of voters in the sample who would vote for that particular candidate, can be got only after you take the sample, for which you need to know the sample size. The way out is to follow a conservative estimate for the sample size. The sample size n will be largest, and hence a conservative estimate in the calculation if the underlined expression p hat times 1 minus p hat is the maximum. And for this expression to be maximum, p hat has to be 0.5 or 50%, giving us a value of 0.25 for the expression. So, as a conservative estimate for the sample size, we will use a value of 0.5 for p hat. Substituting this in the calculation of sample size, the answer we get is 1067.11. Rounding this number up, the pollster needs to survey at least 1068 randomly selected voters. So, that concludes our lesson on sample size calculations. As I had mentioned in the previous lesson, there may be heuristics for sample sizes in the industry you work for or may be working for in the future. Those are fine to use. However, this lesson and the previous lesson provided you some basis for choosing an appropriate sample size. This lesson begins the study of an important topic in business statistics with wide industry application, namely the hypothesis test. In this lesson, in simple language and using simple examples, we introduce the notion behind hypothesis tests, what they can accomplish, and why they are needed. Hypothesis tests are an important tool to analyze data and make some inferences from it. Let us begin by getting some conceptual clarity on what a hypothesis test is. All hypothesis tests follow the same basic two-part logic. You make an assumption. If your data contradicts the assumption, you conclude that the assumption must be wrong. This is a simple logic. However, all hypothesis tests follow this two-part logic. For example, as I drove to work one day recently, I assumed that the road that I normally take to school would, as usual, take me to school. There is the assumption, part 1 of the hypothesis. But I reached a construction barricade and the road was closed. There is the data. It contradicts my assumption. So, my original assumption or hypothesis was wrong. Let us take a more concrete business example. You are the production manager at a beverage manufacturer and you receive a bottling unit that has been recently readjusted so that it puts 200 milliliter of beverage in disposable plastic bottles. There is the assumption. You assume that the unit actually puts 200 milliliter of beverage in the bottles. Next, rather than accepting this assumption, you decide to test it using data. You fill out 10 bottles using the unit at different times so as to obtain a random sample and very carefully measure the amount of beverage inside each bottle. This is your data, a random sample of 10 observations on the amount of beverage in the bottles. What would you conclude if the average amount of beverage per bottle across these 10 bottles, the sample mean, is 170 milliliter? Perhaps it is easy to conclude that the bottling unit is not properly adjusted based on this data, because an average of 170 milliliter seems much different from the stated 200 milliliter that the unit is supposed to fill inside every bottle. So, in this case it is easy to reject your assumption that the unit actually puts 200 milliliter of beverage in the bottles. What would you conclude if the average amount of beverage per bottle across these 10 bottles is 200 milliliter? Again, the conclusion seems easy given this evidence, since the bottling unit is supposed to put in 200 milliliter of beverage per bottle, and across a sample of 10 bottles you found out the average beverage per bottle to be indeed 200 milliliter. You would not reject your original assumption that the bottling unit puts in 200 milliliter of beverage per bottle. What would you conclude if the average amount per bottle is 199.9 milliliter, or for that matter 200.1 milliliter? Perhaps again you might not reject the original assumption, reasoning that the average you are obtaining is but from a sample of data, and given the inherent uncertainties involved in sampling, your evidence is not enough to reject your original assumption that the bottling unit puts in 200 milliliter of beverage. What would your conclusion be if the average amount per bottle in the sample turns out to be 199.1 milliliter, 198 milliliter, 202 milliliter, and so on? The question becomes, at what point would you start rejecting the assumption that the unit puts in 200 milliliter of beverage? When would you consider the difference between the average beverage quantity you obtained from the sample of 10 bottles and the stated quantity of 200 milliliter to be large enough for you to reject the assumption? One option is to simply follow your gut and reject or not reject the assumption based on your feel of whether the difference is large enough. A more scientific procedure is to use hypothesis testing. It is a statistical procedure that helps us make decisions of the kind we illustrated. It takes into account the size of the sample you have, the variability in the sample, the level of significance you want in your conclusion, and then tells you whether or not to reject the assumption. You as a production manager may still follow your gut feeling and either reject or not reject the 200 milliliter claim. However, hypothesis test provides you with a scientific tool to aid your decision making. It is a widely used procedure to test variety of claims. For example, how do you test the fuel efficiency claim of a car manufacturer? How does the government test the claims of efficacy made by a new drug introduced by a pharmaceutical company? As a quality control manager, how do you test the claim that the defective rate in your production process is greater than the acceptable limit? How do you test the claim by an educational website that enrolling in its courses leads to higher school scores? The list can be endless, and in subsequent lessons we will further explore and develop this procedure so that we can apply it to various situations.
As we learned from the videos this week, constructing confidence intervals is an important business tool, but how is the sample size determined? Different industries may have different rules of thumb that work for them, but we also learn to think critically about how to get the information you may not have readily available, like a population standard deviation. Thinking critically and creatively in today's business environment is a skill necessary for success. You may want to use past information or even numbers from a different but relevant industry. By thinking creatively, you may just find the number that you need.
This lesson builds on the understanding of hypothesis testing for a population mean, and we introduce certain mathematical terms and notions that will allow us to conduct hypothesis tests of our own. A greater conceptual clarity is built up on the logic behind hypothesis tests using the bottling unit example. Let us continue our beverage example from the last lesson. In that example, you were the production manager at a beverage manufacturer and you receive a bottling unit that has been recently readjusted so that it puts 200 milliliter of beverage in disposable plastic bottles. You need to test that indeed the bottling unit puts in 200 milliliter of beverage. For that, you fill out 10 bottles using the unit at different times so as to obtain a random sample and very carefully measure the amount of beverage inside each bottle. The 200 milliliter that the bottling unit claims to put inside each bottle can be thought of as the population mean, or to be more precise, the claimed population mean, which is being claimed by the bottling unit. Your aim as the production manager is to either reject this claim or not reject the claim, that is, agree with the claim. Let us solve this. Recollect that in course 2 of this specialization, we had introduced the central limit theorem, one of the fundamental concepts in statistics. This theorem states that if we take a random sample from any population data, then the mean of the sample, denoted by x bar, has a distribution that is normal with mean equal to the population mean from which the sample is taken, typically denoted by Greek letter mu, and a standard deviation equal to the population standard deviation sigma divided by the square root of sample size. In our example, it implies that the average amount of beverage per bottle in our sample of 10 bottles has a normal distribution with a mean equal to the population mean and the standard deviation equal to population standard deviation sigma divided by square root of 10. Now, here is the crux of hypothesis testing. If indeed the claim is correct, that is, the bottling unit does put in on average 200 milliliter of beverage in a bottle, then we would expect that the sample mean that we get from our sample of 10 carefully measured bottles would have a normal distribution centered at 200 milliliter as shown. The probabilities are highest around the mean 200 milliliter, and if indeed the true population mean is 200 milliliter, then the chance of getting a sample mean around 200 milliliter is much higher. The probabilities progressively decrease in the tails, implying that as we move away from 200 milliliter in either direction, the probability of getting a sample mean in that area decreases. This fact is used to come up with so-called rejection regions in the hypothesis tests. The rejection regions are as marked in the plot, and the logic is, if the sample mean that we get from a sample of 10 bottles falls in either of the rejection region, then we conclude that the sample could not have come from a population data with mean equal to 200 milliliter. Thus, we reject the claim that the bottling unit puts in 200 milliliter of beverage. If the sample mean that we get does not fall in any rejection region, then we would conclude that the sample could have come from a population data with mean equal to 200 milliliter, and we will not reject the claim. The rejection regions are so set that the total probability in the rejection region, the shaded portion in the plot, is equal to our familiar expression alpha. Alpha by 2 probability in the right tail and alpha by 2 probability in the left tail. So, this is how conceptually hypothesis tests are set up. You mark out the rejection regions and then see if the sample mean falls in the rejection region or not. However, a few more clarifications are required before we can conduct our own hypothesis tests. As mentioned, the sample mean x bar has a normal distribution with mean equal to population mean and standard deviation equal to population standard deviation divided by the square root of sample size. As we saw in course 2 of this specialization, any normal distribution can be turned into a standard normal distribution by doing a simple transformation as shown. Thus, x bar minus mu divided by sigma by square root of n has a standard normal distribution, that is a normal distribution with mean 0 and standard deviation 1. This expression x bar minus mu divided by sigma by square root of n, as we saw earlier in this course, is also called the z statistic. Thus, in a hypothesis test, trying to figure out whether the sample mean falls in a rejection region is equivalent to figuring out whether the z statistic falls in a rejection region. Further, if we do not know the population standard deviation, which is more likely the case, then we replace the population standard deviation with the sample standard deviation, and the z statistic changes to a t statistic with n minus 1 degrees of freedom, n being the sample size. Thus then, trying to figure out whether the sample mean is in a rejection region is equivalent to figuring out whether the t statistic is in the rejection region. In this course, we will follow this more realistic scenario, and in all hypothesis tests for a population mean, we will use the t statistic. In the following lesson, we lay down the 4-step procedure for conducting a hypothesis test for a population mean. We also discuss the notion of two-tail and single-tail hypothesis tests. The 4 steps are introduced and explained using an example. Let us now lay out the steps for conducting a hypothesis test. We will continue with the beverage bottle example from the last lesson. Let us say that the sample mean beverage per bottle you get across the set of 10 bottles is 199 milliliter, and the standard deviation or variability of these 10 observations, the sample standard deviation is 0.8 milliliter. Step 1 is to formulate your hypothesis. The claim that you wish to test is called the null hypothesis, denoted by H subscript 0. Whatever is not the null hypothesis then becomes the alternate hypothesis, denoted by H subscript A. In our example, the null hypothesis is mu, which is the population mean, equal to 200 milliliter, and the alternate hypothesis is mu not equal to 200 milliliter. Remember, the null and alternate hypotheses are always with respect to some population parameter, in this case the population mean, because a claim is being made about the unknown population mean and you wish to either substantiate that claim or not based on the sample information you have. Another thing about this null and alternate hypothesis is that it is a two-tailed test. There is a strict equality in the null hypothesis. The claim being made is that the population mean is equal to 200 milliliter. So, you would reject the claim if you get a sample mean way above 200 milliliter, and you would also reject the claim if the sample mean is way below 200 milliliter. We will shortly in these steps lay out what do we imply by way up and weigh below 200 milliliter. In contrast, you could also have a single tail hypothesis test, which we will cover in a subsequent lesson. Step 2 is to translate the hypothesis test onto a t distribution by calculating the t statistic, which is x bar minus mu divided by s by square root of n. This turns out to be a negative 3.9528. Trying to figure out whether the sample mean of 199 milliliter is way above 200 milliliter or way below 200 milliliter is now equivalent to figuring out whether the t statistic, a negative 3.9528, is way above 0 or way below 0. That is what is meant by translating the hypothesis test onto a t distribution. Step 3 is to determine the cutoff values for the t statistic, so that you can identify the rejection regions for the hypothesis test. This is done by first specifying a familiar value alpha, which in the context of hypothesis tests is also called the significance level. The values of alpha that are commonly used in the industry are 0.05 and 0.01, corresponding to a 95% confidence and 99% confidence respectively. Alpha is the probability that you are willing to accept for making an error, in the sense of rejecting the null hypothesis when indeed it is true. It is also referred to as the probability of type 1 error. In this course, unless otherwise specified, we will use an alpha value of 0.05. So, our cutoff values for the t statistic denoted by t cutoff are those values in a t distribution with n minus 1 degrees of freedom that cut off alpha by 2 probability to the right and alpha by 2 probability to the left. Remember, this is a two-tailed test with one rejection region on the right and one rejection region on the left. Hence, the total rejection probability of alpha gets equally divided across the two rejection regions. Using our familiarity with the t dot inv function for the t distribution introduced in this course, these cutoff values can be calculated as plus minus the absolute value of t dot inv alpha by 2 n minus 1. Note that the plus sign is for the rejection region on the right side and the minus sign is for rejection region on the left side. These turn out to be plus minus t dot inv 0.05 by 2 10 minus 1, which is a positive 2.2622 and a negative 2.2622. In other words, our rejection regions are marked as greater than positive 2.2622 and less than negative 2.2622. Step 4 is to see whether or not the t statistic we calculated in step 2, which was a negative 3.9528, lies in any rejection region. It indeed does lie in the rejection region on the left hand side. Thus, because the t statistic falls in a rejection region, we reject the null hypothesis at an alpha equal to 5% significance level and conclude that based on our evidence, the bottling unit does not put in on average 200 milliliter of beverage in the bottles. As a side note, had our t statistic not fallen inside any rejection region, then we would have not rejected the null hypothesis and concluded that the bottling unit could indeed on average be putting 200 milliliter of beverage inside bottles. This lesson applies the 4-step procedure for hypothesis testing to an application involving single tail hypothesis tests. Using the example of a fuel additive manufacturer, we understand what a single tail hypothesis test is and how to run and interpret this test. In the last lesson, we laid down steps to conduct a hypothesis test for a claimed population mean. There were 4 steps, and the first step was to formulate the hypothesis, where you set up the null and alternate hypothesis based off what particular claim you wish to verify. Step 2 was calculating the t statistic. Step 3 was calculating the cutoff values for the t statistic, or in other words, marking out rejection regions in a t distribution. And finally, step 4 was either rejecting the null hypothesis or not, based on whether the t statistic falls in a rejection region or not. As important as these 4 steps is to interpret the results of your hypothesis test, that is, you are rejecting or not rejecting the null hypothesis to the particular business application or situation where you are using this tool. In the last lesson, while laying down these steps, we had used the example of a beverage bottling unit and wanted to check whether indeed the bottling unit puts in on average 200 milliliter of beverage inside the bottle. This was a two-tailed test, because we would have rejected the null hypothesis either if the sample mean was way above 200 milliliter or way below 200 milliliter, or in equivalent terms if the t statistic was way above 0 or way below 0, that is inside the rejection region. In such two-tailed tests, there are 2 rejection regions making up the overall alpha probability. One on the left tail of the t distribution accounting for alpha by 2 probability, and the other on right tail accounting for the remaining alpha by 2 probability. In contrast, we could also have a single tail hypothesis test where the entire rejection region, that is the entire alpha probability, is on a single tail. It could be either the left tail or the right tail based on the context of application. Let us look at an example. A fuel additive manufacturer claims that through the use of its fuel additive, automobiles in the small car category should achieve on average an increase of 3 miles or more per gallon of fuel. So, this is the claim made, that the increase in fuel efficiency is 3 miles per gallon or more. To test this claim, what is done is that a random sample of 150 automobiles from the small car category is taken, and their fuel efficiency in terms of miles per gallon is carefully measured. Then these cars are used with the fuel additive, and their fuel efficiency is again carefully measured. From these 2 sets of measurements, you get 150 measurements for the increase in miles per gallon achieved. The sample mean increase in miles per gallon achieved in this case was 2.9 miles per gallon, and the sample standard deviation was 1.35 miles per gallon. With this information, let us set up a hypothesis test for this claim. The sample size n is 150, the sample mean is 2.9 miles per gallon, and the sample standard deviation is 1.35 miles per gallon. The first step is to formulate hypothesis. In this case, the null hypothesis is that the actual average fuel efficiency increase, which is the population mean fuel efficiency increase denoted by Greek letter mu, is greater than or equal to 3 miles per gallon. The alternate hypothesis then becomes that mu is less than 3 miles per gallon. Note that this is a one-tailed test, because you will not reject the claim if the fuel efficiency increase turns out to be very large, since the manufacturer itself is claiming that the average increase is 3 miles per gallon or more. The manufacturer is not saying that the average fuel efficiency increase is equal to 3 miles per gallon. Thus, you would reject the claim only when the observed sample mean increase is way below 3 miles per gallon. In equivalent terms, you would reject the null hypothesis if the t statistic that you calculate is way below 0. In other words, there is only one rejection region on the left hand side, and the entire alpha probability gets accounted for by this single rejection region. This is an example of a one tail or single tail hypothesis test with rejection region on the left hand side. You could also have single tail hypothesis tests with rejection region on the right hand side. In that case, the null hypothesis would have a less than equal to sign rather than a greater than equal to sign. An easy way to figure out which side is the rejection region is to look at the mouth of the inequality in the null hypothesis. If the mouth opens towards the left side, then the rejection region is on the left side. If it opens on the right side, then the rejection region is on the right side. And if the null hypothesis is a strict equality, that is, the mouth opens on both sides, then the rejection region is on the left as well as the right side. That is, two rejection regions. Coming back to our test, the next step, which is step 2, is to calculate the t statistic x bar minus mu divided by s by square root of n.
So x bar is 2.9, so is equal to open parenthesis x bar 2.9 minus mu, the value of mu that we'll use is 3.0 divided by open parenthesis s by square root of n. S, the sample standard deviation, is 1.35 miles per gallon, 1.35 divided by square root of sample size, SQRT, open parenthesis, my sample size is 150, close parenthesis, and one more close parenthesis. So that gives me the value of my t statistic.
This turns out to be a negative 0.9072. Step 3 is to calculate the cutoff values for the t statistic. Since no value is given for alpha, the significance level, hence we will take alpha to be the industry standard 0.05. Also, since this is a one-tail test with rejection region on the left hand side, hence as shown, the entire alpha probability will get accounted in that one region on the left side. The cutoff value for this region is then given by a negative of absolute value of t dot inv, alpha as it is, n minus 1. Note that we do not use alpha by 2 in the t dot inv command, as we did while solving for a two-tail test in a previous lesson. This is a single tail test with the entire alpha probability in that single tail. So the cutoff value turns out to be negative absolute value of t dot inv 0.05, 150 minus 1
is equal to a negative absolute value. So in Excel, to calculate the absolute value, we use the ABS function, ABS, open parenthesis, t dot inv, open parenthesis. The t dot inv takes in two inputs. The first input is the alpha value, and since no specific alpha value is given, we choose the industry standard of 0.05, comma, n minus 1, where n is the sample size. In our case, the sample size is 150, so we get 150 minus 1 close parenthesis, and then one more close parenthesis. So that gives us the value for t cutoff.
This gives us the cutoff value of negative 1.6551. Had our rejection region been on the right side, the cutoff value would be calculated as a positive absolute value of t dot inv alpha n minus 1. In that case, the cutoff would have been a positive 1.6551. So, given the cutoff value of negative 1.6551, the final step, step 4, is to check if our calculated t statistic, which is negative 0.9072, falls in the rejection region or not. It does not. Hence, we do not reject the null hypothesis and conclude that our sample evidence is consistent with the claim being made. In other words, we cannot falsify the claim that the fuel additive on average increases fuel efficiency by 3 miles per gallon or more. In this lesson, we lay down some guidelines for framing the null hypothesis in a hypothesis test and also do a recap of various formulae involved in hypothesis testing. We work out an example around ages of men MBA students to emphasize the applicability of the guidelines for framing a null hypothesis and the way around when these guidelines apparently get violated. Let us lay out some guidelines for framing the null hypothesis and recap the various formulas associated with the hypothesis test procedure for testing claims relating to a population mean. When you frame a null hypothesis, please make sure that the null hypothesis does not contain a strict inequality. What this means is that the null hypothesis cannot have a not equal to sign, a greater than sign, or a less than sign. What it can have is an equal to sign, a greater than equal to sign, or a less than equal to sign. An equal to sign gives us a two-tailed hypothesis test, a greater than equal to sign gives us a one-tailed hypothesis test with rejection region on the left side, and a less than equal to sign gives us again a one-tailed hypothesis test, but rejection region now being on the right hand side. So, these were some guidelines for framing the null hypothesis. The reason to have these guidelines is because the steps we have introduced do not allow us to test for a null hypothesis with a strict inequality. However, this is not a constraint because, as we will shortly see in an application, we have a way around when our null hypothesis naturally turns out to have a strict inequality. But before that, a quick recap of formulas associated with hypothesis tests involving a population mean. The first formula to keep in mind is the formula for calculating t statistic. It is x bar, which is the sample mean, minus mu, which is the claimed population mean around which you are building the hypothesis, divided by s, the sample standard deviation, by square root of n, the sample size. This gives you a translation of the hypothesis test onto a t distribution, resulting in a t statistic. Next, you need formulas to calculate the rejection regions for the t statistic. If it is a two-tailed test, that is, if there is an equal to sign in the null hypothesis, then there are two rejection regions, one on the right and the other on the left. These are calculated as plus minus absolute value of t dot inv alpha by 2 degrees of freedom, which is equal to n minus 1, the sample size minus 1. If it is a one-tailed test and the null hypothesis has a greater than equal to sign, then the rejection region is on the left hand side, and the rejection region is calculated as negative absolute value of t dot INV, alpha as it is, degrees of freedom, which is n minus 1. If on the other hand it is a one-tailed test and the null hypothesis has a less than equal to sign, then the rejection region is on the right hand side and it is calculated as positive absolute value of t dot INV, alpha as it is, degrees of freedom, which is n minus 1, n being the sample size. So, that was a recap of various formulas used in hypothesis testing around a population mean. Let us work out a problem. We will use this problem to illustrate how we can work around a situation where the null hypothesis naturally turns out to have a strict inequality. We wish to test a claim that the average age of men MBA students across various MBA programs in the US is greater than 28 years. For this, we collect data on average ages of men MBA students across a sample of 40 MBA programs in the US. The data is in the file averageage.xlsx. Let us take a look at this data.
So, this is the data on the average ages of men MBA students across 40 MBA programs in the US. A sample of 40 MBA schools across the many MBA schools that exist in the US. For example, this highlighted row implies that the 8th school in the sample had an average age of men MBA students to be 28.5 years.
Note that the claim states that the average age of men MBA students is greater than 28 years. It does not say that it is greater than equal to 28 years. Thus, when we naturally try to frame the null hypothesis, then we would be inclined to frame it as shown: mu greater than 28, and thus the alternate hypothesis becomes mu less than equal to 28, where mu is the average age of men MBA students across all US MBA programs, or in other words, mu is the population mean age of MBA students across US MBA programs. However, earlier in this lesson we had given a guideline that the null hypothesis should not have a strict inequality. That is, it cannot have a not equal to sign, a greater than sign, or a less than sign. So, the way we have framed our null hypothesis is in violation of this guideline. To deal with this situation, we simply switch the null and alternate hypothesis. So, our new null hypothesis is that mu is less than equal to 28, and the alternate hypothesis is mu is greater than 28. All our inferences now will be based on this new null and alternate hypothesis. Remember, in a hypothesis test, between the null and alternate hypothesis, one is rejected and the other is not. So, it really does not make a difference in the final analysis if you switch the hypothesis as shown, as long as your interpretations are properly done in terms of what is rejected and what is not. Let us now work out this problem. Step 1 of framing a null and alternate hypothesis has already been done. Step 2 is to calculate the t statistic, which is x bar minus mu divided by s by square root of sample size. Let us calculate this in Excel.
To complete the calculations, we will need values for x bar, we will need a value for s, the sample standard deviation, a value for mu, the population mean around which we wish to test the claim, and a value for sample size n. So, x bar can be calculated from data. X bar is the sample mean. So, we do a is equal to average open parenthesis, and then we select this entire data of ages, average ages, do a shift control down arrow, or select the entire column, close parenthesis, and that is my average age or sample mean age, 28.1 years. My sample standard deviation can also be calculated, is equal to stdev dot s, that is the function we use in Excel, open parenthesis, A2 through A41. That's my data, close parenthesis, enter. So the sample standard deviation is 2.97. The value of mu that we'll use is 28, because that is the value around which we wish to test the claim, and the sample size is equal to 40. So based on this, our t statistic is calculated as open parenthesis x bar minus mu. Pick up the value of x bar minus the value of mu. I'll use 28, close parenthesis, divided by s by square root of n. So open parenthesis, s my sample standard deviation, I pick it up from there, divided by square root of sample size. So to calculate square root in Excel, we use the sqrt function, sqrt sample size, close parenthesis, and then to balance all the parentheses, one more close parenthesis, enter. So that is my t statistic.
Given this calculated t statistic of 0.2232, step 3 is to calculate rejection region for this t statistic. This is a single tail test with rejection region on the right hand side. Remember the tip that since the mouth of inequality in null hypothesis opens on the right hand side, hence rejection region is on the right hand side. The formula to calculate the cutoff value for the rejection region is a positive absolute value of t dot inv alpha, degrees of freedom, which is sample size minus 1. Since no value for alpha is given, we will choose alpha to be the industry standard value, which is 0.05.
So the t cutoff value is calculated as a positive absolute value of the t dot inv function. So is equal to calculate the absolute value, we use the abs function in Excel, abs open parenthesis positive absolute value of t dot inv open parenthesis. The first input is alpha as it is. In our case, alpha is 0.05, comma, the second input required is degrees of freedom, which is sample size minus 1 or n minus 1, 40 minus 1, close parenthesis, and to balance out the overall parenthesis, one more close parenthesis, enter. So that's the value of my t cutoff, a positive 1.6849.
So the rejection region is to the right of positive 1.6849. The final step, step 4, is to check whether our calculated t statistic falls in this rejection region. It does not. Thus, we do not reject the null hypothesis, and since we cannot reject the null hypothesis, we automatically reject the alternate hypothesis. The null hypothesis states that average age of men MBAs is less than equal to 28 years, and we cannot reject this claim. The alternate hypothesis says that the average age of men MBAs is greater than 28 years, and we reject that claim. Thus, our final inference to the claim that average age of men MBAs across MBA programs in the US is greater than 28 years is that based on our data evidence, we can falsify or reject this claim being made. We have been conducting hypothesis tests, testing for claims made with respect to a population mean. We now extend this procedure to test for claims being made with respect to a population proportion. That is, we introduce hypothesis testing for a population proportion rather than a population mean. The 4-step procedure for hypothesis tests is applied with minor modifications. This is illustrated by way of an application. We will now look at hypothesis tests involving a population proportion rather than a population mean. Let us motivate it by an example. A medium-sized university in the US introduces a new lunch facility on campus on a trial basis. The university operates the lunch facility for a few months and then decides to survey the student body. Based on the survey, university would make this facility a permanent fixture or do away with it. Specifically, if more than or equal to 70% of the student body approves of it, then the facility would be made permanent, else it would shut down. The university conducts a survey with 750 randomly selected students on campus and finds that 510 of these students, or 68% of the sample students, approve of the new facility, and the remaining 240 students, or 32% students, do not approve of it. Based on the criteria set by university, should the facility be made permanent? Here the quantity of interest is the population proportion rather than the population mean. Specifically, the university would continue with the facility if more than or equal to 70% of its entire student body approves of it. However, the university only has a sample of 750 responses from this population of student body, and it needs to make a decision based on this sample. This situation is apt for a hypothesis test. However, the hypothesis test here would be for a population proportion. The 4-step procedure remains the same with a few modifications. Step 1 is to formulate the null and alternate hypothesis. The null hypothesis here is that the population proportion, denoted by lowercase p, is greater than or equal to 0.7 or 70%. The alternate hypothesis then becomes p, the population proportion, is less than 0.7. Step 2 is to calculate the test statistic. Here we will be using the z statistic. This is one change that happens from the hypothesis test we have been running for the population mean, where we have been using the t statistic. All hypothesis tests involving a population proportion will be using the z statistic. This is calculated as p bar minus p divided by square root of p times 1 minus p divided by square root of sample size n. P bar here is the sample approval proportion obtained in the survey, which is 0.68. P is the hypothesis population proportion around which we wish to conduct the hypothesis test.
To calculate the z statistic, we need a value for p bar, which is our sample proportion. In this case, it is 0.68. Then we need a value for p, the population proportion around which we wish to test the null hypothesis. In this case, it is 0.7. We need a value of n, the sample size, which in this case is 750. 750 students were surveyed on the campus. So given these values, z statistic is calculated as is equal to p bar minus p. So open parenthesis, my sample proportion minus the population proportion around which I wish to test the null hypothesis, divided by square root of p times 1 minus p by n. So square root of p, which is a population proportion, times 1 minus p divided by square root of sample size. And notice, since we have the square root outside the big parenthesis, we simply put in the sample size there. Close parenthesis. So once again, my z statistic is p bar, which is a sample proportion, minus the population proportion around which I wish to test the null hypothesis, divided by square root of p, population proportion, times 1 minus p, divided by sample size. So that is my z statistic, a negative 1.1952.
One caveat in using the z statistic is that the product of sample size times the sample proportion obtained from the survey should be greater than 5. So also the product of sample size times 1 minus sample proportion should be greater than 5. Both these conditions are met in this application. Had they not been met, we could not have done this particular hypothesis test for the population proportion. Step 3 in the process is to calculate the cutoff values for the z statistic. This is a one-tailed test with rejection region on the left hand side, and also since no significance value is mentioned, that is no value for alpha is mentioned, hence we would choose alpha or the significance level to be 0.05, which is the industry standard. The cutoff value is calculated using negative absolute value of norm.inv alpha 0 1.
So the cutoff value, z cutoff, is calculated as a negative of absolute value of norm.inv. So a negative, then the absolute function a, b, s, open parenthesis, norm.inv, open parenthesis, the value of alpha, the alpha in our case is 0.05, comma 0, comma 1, close parenthesis, and then to match up the parenthesis, one more close parenthesis. So that will give me the value of my z cutoff, which is a negative 1.6449.
As a side note, had the rejection region been on the right hand side, we would have used positive absolute value of norm.inv alpha 0 1. But the same logic, if it had been a two-tailed test, we would have used plus minus norm.inv alpha by 2 0 1 for the two rejection regions on the right and left. Step 4, the final step, is to check whether the z statistic falls in rejection region. Our z statistic is negative 1.1952 and the rejection region is to the left of cutoff value negative 1.6449. The z statistic does not fall in the rejection region. Hence, we do not reject the null hypothesis. The university cannot reject the claim that more than or equal to 70% of its entire student body approves of the new lunch facility. Thus, the facility should be made permanent. This lesson discusses the two kinds of errors that a hypothesis test is susceptible to, the type 1 error and type 2 error. We first understand what these errors are and then discuss ways and means to reduce these errors. While conducting a hypothesis test, you should recognize that you are susceptible to two kinds of errors. These are called type 1 error and type 2 error. Let us use an example to understand these errors. Your friend Sam claims that he can shoot 40 or more baskets in an hour from the 3-point line in a basketball court. So, Sam is making a claim about a population parameter. In this case, it is his true shooting ability from the 3-point line in a basketball court. This can be likened to the population mean mu. Thus, Sam is claiming that the population mean mu of his shooting ability is greater than or equal to 40 baskets in an hour from the 3-point line in a basketball court. Next, you decide to test this claim. For that, you take Sam to the basketball court every day for 10 days and make him shoot baskets from the 3-point line for an hour every day. You end up with 10 data points, which are the number of baskets Sam shot in those 10 days. You can calculate the sample mean and the sample standard deviation from these 10 observations. In step 1 of the hypothesis test, you will frame the null and alternate hypothesis. Your null hypothesis is mu is greater than equal to 40. Mu here is Sam's true ability to shoot baskets in an hour from the 3-point line. The alternate hypothesis is that it is less than 40. In step 2 of the hypothesis test, you would then calculate the t statistic from the sample data, and in step 3 you would mark out the rejection region for the t statistic. This is a one-tailed test with rejection region on the left hand side. In step 4 of the hypothesis test, you would reject the null hypothesis if the t statistic falls in the rejection region, otherwise you would not reject the null hypothesis. As mentioned earlier, Sam's true ability to shoot baskets in an hour from the 3-point line in a basketball court can be likened to the population mean. This population mean, which is Sam's true shooting ability, would never be exactly revealed to us. All that we can do is test various hypotheses around this population mean using sample data. Now, for argument's sake, consider that Sam's true ability is indeed greater than equal to 40 baskets in an hour from the 3-point line. However, the 10 days that you took him to the basketball court, he was not feeling very well and gave you a low sample average, which led you to reject the null hypothesis. In other words, you rejected that Sam's true ability to shoot baskets in 1 hour from the 3-point line in a basketball court is greater than equal to 40. Here you would have done an error in rejecting the claim based on your sample evidence, because the claim was indeed true. This is called type 1 error, rejecting a null hypothesis when it is indeed true. Would you know in a hypothesis test that a type 1 error has occurred? No, because to figure out whether type 1 error has occurred, you need to know mu, the true ability of Sam to shoot baskets, and this is an unknown quantity. So, though we would not know whether a type 1 error has occurred or not, we need to be aware that we are susceptible to this kind of an error. The probability or chance of type 1 error gets fixed by our choice of alpha. The significance level, which sometimes is also referred to as probability of type 1 error. We can always set alpha to a very small value to reduce the probability of rejecting a true null hypothesis. However, in doing so, we increase chances of the other kind of error, the type 2 error, which is the error of not rejecting the null hypothesis when it is false. In our case, a type 2 error would happen when Sam's true ability is not greater than equal to 40 baskets. However, during the 10 days you took him to the basketball court, he was lucky and gave a shooting sample which led you to not reject the null hypothesis. This is what is called type 2 error. Again, as with type 1 error, you would not know whether the type 2 error has occurred or not. However, you should be aware that your hypothesis test is susceptible to these two kinds of errors. So, how do we reduce the chances or probability of these two kinds of errors? Probability of type 1 error, as mentioned, is set by our choice of alpha, the significance level. Industry collectively has arrived at some common values of alpha, which are typically 0.05 and 0.01. An alpha value of 0.05 is telling us that we are willing to accept that 5% of the times our hypothesis test would be in error in terms of a type 1 error, whereby we will reject something which is true. Type 2 error, on the other hand, is related to something called power of a test and can be reduced to the extent possible by taking larger sample sizes. In summary, we should be aware that we are susceptible to these two kinds of errors while doing a hypothesis test. Probability of type 1 error occurring is set by our choice of alpha, and the probability of type 2 error occurring can be reduced to the extent possible by taking larger sample sizes.
Understanding the concept behind hypothesis testing, as well as the possible types of errors, will allow you to determine the best situations in which to apply hypothesis testing. You may not always know when conducting a hypothesis test whether an error has occurred, but being aware of the potential will help you more thoroughly think through whatever claim you may be testing. Perhaps your final business decision may be affected by additional data gathering or research. On the other hand, we learned about ways to reduce the possibility of these errors. Utilizing these methods will increase the likelihood that your hypothesis testing can help you make more thoughtful business decisions.
From this lesson onwards, we extend our hypothesis test procedure to a situation where we wish to make comparisons between population means across two different populations. These are called differences in means test. In the following lesson, we begin by a hypothesis test involving a single population and use that to introduce the difference in means test in the subsequent lesson. In this lesson, we get to understand conceptually what a difference in means hypothesis test is. We will now extend the hypothesis test for a population mean to a situation where we are interested in comparing the population means across two different populations. These tests are termed as difference in means tests, and we will introduce them by way of an example. The file athletes.xlsx contains data on a sample of Olympic athletes from some past Olympic games. In particular, it consists of the name of athlete, height and weight information, country of the athlete, and the athlete's gender. Let us take a look at this file.
The very first column of the file is the name of the athlete, the Olympic athlete, the height of the athlete in centimeters, the weight of the athlete in kilograms. Column D is the country that the athlete represents, and finally column E is the gender of the athlete.
An empirical study using data on heights of people claimed that the average height of men aged 18 years to 45 years across the world was 173 centimeter, which in inches is a little over 68 inches. This study included men not only from the sports fraternity, but across a wide spectrum of professions and walks of life. One could argue that men Olympians are likely to be taller than this claimed average height of 173 centimeter. Reasons could be many. For example, one reason could simply be a matter of self-selection. Only the best and good performing athletes get into Olympics, and it is likely that their average heights are more than the average heights across the general population of men. One could set up a hypothesis to test the claim that the average height of men athletes at the Olympics is higher than the average height of men across all walks of life, which the empirical study found out to be 173 centimeter. We can use the sample data in our Excel file athletes.xlsx to solve for this hypothesis test. That is, we will be testing whether we can reject or not reject the claim that average height of men Olympians is greater than 173 centimeter. Remember, we only have a sample data on heights of men athletes at Olympics. Based on this sample data, we wish to evaluate a claim being made about the average height across the entire population of men athletes at all Olympic Games. This is where hypothesis testing comes in. So, step 1 of the hypothesis test, our null hypothesis, is that the average height of men athletes at the Olympics is greater than 173 centimeter. Note that it is not greater than or equal to, but rather greater than 173 centimeter. That is, mu of height, which is the population mean of heights across all men athletes at all Olympics, is greater than 173 centimeter. Remember, the hypothesis is always for the population mean, because that is the quantity that we do not know, and we are trying to test some claims about that using our sample information. The alternate hypothesis is that the population average height across men Olympians is less than equal to 173 centimeter. Notice that we end up having a strict inequality in the null hypothesis, which based on our guidelines given in an earlier lesson is not admissible. So, we simply flip the null and alternate hypothesis. Thus, our new null hypothesis is that the population mean height of men athletes at the Olympics is less than equal to 173 centimeter. The alternate hypothesis is that the population mean height of these athletes is greater than 173 centimeter. This is the new null and alternate hypothesis that we will be testing. Lest there is confusion, we should erase the earlier null and alternate hypothesis. This is a one-tailed test with rejection region on the right hand side. Remember the tip that since the mouth of the inequality in the null hypothesis opens on the right hand side, hence the rejection region is on the right hand side, once the problem has been translated onto a t distribution. Also observe that there is a single population mean we are interested in, the population mean height of men athletes in the Olympics. We have not yet introduced the concept of difference in means. We will do that after we solve for this hypothesis test. Step 2 of the hypothesis test is to calculate the t statistic. By doing this, we translate the problem onto a t distribution, a necessary step to proceed with the hypothesis test. The t statistic is given by x bar minus mu of height divided by s by square root of n, where x bar is the sample mean, mu of height is the claimed population mean around which we are doing the hypothesis test, s is the sample standard deviation, and n is the sample size. Let us calculate this in Excel.
To calculate the t statistic, we need to calculate x bar and s. X bar is the sample average height of all the male athletes, and s is the sample standard deviation of the heights of all the male athletes. However, notice in this file we have data on both male and female Olympic athletes. So, we need to first segregate the data. One way could be to select the data and sort the data based on gender, sort by gender. So, now what has happened is all the male athletes data have been put at one place. So, now you could appropriately calculate x bar and s by selecting data only for the male athletes. Another approach could be to use a pivot table and then calculate the averages. However, a wrong approach would be to filter the data without creating a pivot table. So if I filter the data and I select only the male gender. Now, though in my file I see only the male athletes, however, when I calculate the sample average, the sample standard deviation, I would be getting a wrong answer. So we will not be following this filtering approach to calculate the t-statistic. So I'll remove the filter. Rather, what we'll do is we'll follow the pivot table approach. To insert a pivot table, we go to Insert, Pivot Table, a pivot table. I select my data range, my entire data range, and I'll create a pivot table in a new worksheet rather than putting it in the existing worksheet. Okay, so a pivot table template is produced. Let me increase the font size here, the resolution. So now I'll take the name of the athlete, drag it where it says row labels. So I have all my athletes in column A. Then I'll take the height information and drag it where it says values. So I have the athletes and their corresponding heights. Notice the height is given in terms of sum of heights. In this case, it really doesn't matter because there's only one height per athlete. Nevertheless, let us change it to average of heights. So I go to value field settings, change summarize value field by average, do an OK. So I have my athlete and the height of that athlete. Next, I need to segregate these athletes based on gender. I only need the male athletes. So I can take the gender and I can filter the report based on gender. So I drop it where it says report filter. So now I have a gender tab inserted in the very first row and I can select only the male gender. Do an OK. So now I have information only on the male athletes. And notice, unlike filtering without using a pivot table, in this case, when I calculate my sample averages and the sample standard deviation, I would get a correct answer. So now let me calculate my X bar. I'll also calculate my S. I'll also calculate my N, the number of male athletes. So X bar is given by average I select this column. So that's my average height, sample average height 183.83 centimeters. My sample standard deviation stdev.s open parenthesis. That's my sample standard deviation. The number of male athletes, I can do a count here, count. (771) male athletes, and now I can calculate my t-statistic. So t-statistic is calculated as X bar minus mu. So I pick up X bar minus mu. The value of mu is 173 centimeter because that is the population mean we are testing against, divided by S by square root of n. So I pick up my S, which is the sample standard deviation, divided by square root of sample size, SQRT. I pick up my sample size, which is the number of male athletes in the data. Close parenthesis, one more close parenthesis. So that is my t-statistic.
The t-statistic turns out to be 30.0351. Step 3 of the hypothesis test is to calculate the cutoff value for the t-statistic. This is a single tail test and there will be a single rejection region on the right hand side. For a one-tailed test with rejection region on the right hand side, the cutoff value is calculated as positive absolute value of t dot inv alpha degrees of freedom, which is n minus 1. Since no mention of a particular value for alpha is made, hence we will choose alpha to be the industry standard value 0.05.
So t cutoff is calculated as is equal to a positive absolute value of t dot inv. So ABS open parenthesis t dot inv. So ABS is the function for calculating absolute values. Alpha, and since no value of alpha is given, we choose 0.05, comma degrees of freedom, which is n minus 1. So we pick up n, our sample size from here 771 minus 1, close parenthesis, and one more close parenthesis to match up with all the open parentheses. So that is the value of t cutoff.
Given this cutoff value of positive 1.6468, the rejection region for the t statistic is all the area to the right of 1.6468. Step 4 of the hypothesis test is to check whether the t statistic falls in any rejection region. The t statistic does fall in rejection region on the right hand side. Thus, we reject the null hypothesis. What does rejecting the null hypothesis imply? It implies that we reject null hypothesis that the population mean height of men athletes at the Olympics is 173 centimeter or less. And since we reject the null hypothesis, we automatically do not reject the alternate hypothesis, which states that the population mean height of such athletes is greater than 173 centimeter. Thus, our final conclusion is that based on our data evidence, we cannot reject the claim that male athletes at Olympics are taller than 173 centimeter. So that was a hypothesis test involving a single population, the population of men Olympians. We had a sample from the population in terms of our sample data from some past Olympic games, and we end up not rejecting that the population average height of men athletes is greater than 173 centimeter. Now let us extend this test further. The empirical study we referred to at the beginning of this lesson found that the average height of men 18 to 45 years old from various walks of life across the globe was 173 centimeter. We then tested this claim in our data of Olympic athletes and found that the population mean height of men Olympic athletes was greater than 173 centimeter. That is, we rejected the claim of average height being equal to 173 centimeters. This empirical study also claimed that the difference in average heights across men and women from various walks of life around the world was 12.5 centimeters. We can test this claim using a sample data and see whether this claim holds for the population of men and women athletes at the Olympics. Note an important difference here. The claim involves the difference between two population means, the population mean height of men athletes at the Olympics and the population mean height of women athletes at the Olympics. This important difference slightly changes the way this test is carried out, and this test is now known as the hypothesis test for difference in means, because we are interested in testing claims for the difference in two population means. In this case, the difference between the population mean height of men athletes and the women athletes at Olympics. We will continue with this difference in means test in the next lesson. This lesson builds up on the previous lesson, where we introduced the concept of difference in means hypothesis test. We lay down the steps and formulas involved in the test. We also introduced two variations of the test wherein we need to assume the population variances of the two populations from where the samples come to be either equal or unequal. We will continue from where we stopped in the previous lesson. We wish to test the claim that the difference between the population mean height between men and women Olympic athletes is 12.5 centimeters. Recollect that the empirical study had come up with an average difference of 12.5 centimeters in heights of men and women from various walks of life across the world. We wish to test whether this claim also holds for the population of Olympic athletes. Step 1 of doing the hypothesis test is framing the null and alternate hypothesis. The null hypothesis here is that mu men minus mu women is equal to 12.5, where mu men is the population mean height of men athletes at the Olympics and mu women is the population mean height of women athletes at Olympics. That is the average height across all women athletes who have participated in any Olympics. The alternate hypothesis then becomes mu men minus mu women is not equal to 12.5. This is a difference in means test because we wish to test the claim about the difference in the two population means. Further, this is a two-tailed test because there is an inequality in the null hypothesis. Thus, when translated onto a t distribution, the test will have two rejection regions, one on the right and other on the left hand side. Step 2 of the hypothesis test procedure is to calculate the t statistic. This is where things get a bit more complicated as compared to the single population hypothesis test. To calculate the t statistic, you first need to make a determination of the nature of variation in the population from where these two samples are drawn. In particular, we need to consider whether the variation or spread in the population data across the two populations is likely to be similar or dissimilar. In other words, you need to either assume that the population variances for the two populations involved are equal or that they are unequal. Remember, you do not know the population variances or the spread in population data. So, assuming equal variance or unequal variance across the two populations becomes more of a thought exercise. Though there are some statistical tests that help you in the process of figuring out whether the population variances are likely to be similar or dissimilar, we will not be getting into those tests as the additional value in knowing those tests to business applications is minimal. So, we will do a subjective judgment in either assuming equal variances or unequal variances across the two populations from where our samples are drawn. Though looking at the sample variances from the two samples that you have may give some indication whether the population variances are more similar or more dissimilar, nevertheless, this is still a subjective judgment to be made by you. In this case, I would tend to argue that the variation in heights for the population of men Olympic athletes is likely to be similar to the variation in heights of women Olympic athletes, as they both belong to the competitive sporting profession and have emerged at the Olympic levels after a tough selection process, indicating that there are more of similarities than dissimilarities in the variation of heights. Thus, we would assume equal variances across the two populations. Notice this is a very subjective judgment. For example, some of you may argue that men and women are inherently different and hence the variation in heights is also likely to be more dissimilar, thus arguing for an unequal variance assumption across the two populations. That too is a reasonable argument and cannot be falsified. However, as you will see in subsequent lessons, in most applications this argument of equal versus unequal variances is more of an academic argument, and in terms of results of the hypothesis test, your conclusions really do not change. So, if in doubt, you may as well flip a coin and either assume equal variances or assume unequal variances. The t statistic, when variances are assumed to be equal across the two populations, is calculated as shown. X1 bar and X2 bar are the two sample means. X1 bar for the average height of men athletes in our sample, and X2 bar the average height of women athletes in our sample. Mu is the difference in population mean around which you wish to test the hypothesis. N1 is the number of men athletes in the sample, and N2 is the number of women athletes in the sample. Note that the two sample sizes need not be equal. S1 is the sample standard deviation of the heights of men athletes in our sample, and similarly S2 is the sample standard deviation of the heights of women athletes in our sample. So, this is the t statistic calculation in a difference of means test when you assume population variances to be equal across the two populations. When the assumption on the two population variances is that they are not equal, then the t statistic calculation takes a slightly different form as shown, where the various expressions such as x1 bar, x2 bar, s1, s2, n1 and n2 have similar interpretation as in the equal variance assumption case. Fortunately for us, Excel has an inbuilt data analysis add-in that will take care of these calculations for us. In the next lesson, we will introduce that add-in and complete this hypothesis test. In this lesson, we solve for the difference in means t-test using the assumption of either equal variances or unequal variances across the two populations from where the samples come. The Excel dialog box to do the calculations for such tests is introduced, and we use it in our application. Continuing from the previous lesson, let us solve the hypothesis test using the Excel built-in data analysis add-in. Given the null and alternate hypothesis in step 1, step 2 calculates the t statistic associated with the hypothesis test. Since this is a difference in means test, that is, it involves two population means in the null hypothesis, we can use the built-in data analysis add-in within Excel. Note that this add-in cannot be used for a hypothesis test where you have a single population mean. That is, you are testing for a null hypothesis around a single population mean. It is used only when you are doing a difference in means test. That is, the null hypothesis contains two population means. Let us demonstrate this in Excel. The file to be accessed is the athletes.xlsx file.
So, this is the file athletes.xlsx, and as a ready reckoner, I have copied and pasted the null and alternate hypothesis here. The null hypothesis is mu men minus mu women is equal to 12.5, or in other words, the population average height of men athletes at the Olympics minus the population average height of women athletes at the Olympics is equal to 12.5. And the null and the alternate hypothesis is that they are not equal to 12.5. So, given this data, we first need to segregate the data according to male and female athletes. We can do so by using a pivot table. So, let's do that. So, we go to Insert, Pivot Table, a pivot table. I select my data range, my entire data range, and I'll put the pivot table in a new worksheet. So, do an OK. So, a pivot table template is produced in a new worksheet, and let me increase the zoom level to 150. So, I drag my name column, put it in the row labels. Remember, I wish to segregate the heights of male and female athletes. I drag the height field and put it where it says values. So now I have the individual athlete in column A. Column B, I have his or her height, but I want to segregate it based on genders. So what I do is I take the gender field and drag it where it says column labels. So now I have the heights of athletes segregated as per gender. And as a ready reckoner, let me copy and paste the null and alternate hypothesis. So this is my data ready for a difference in means test. I do not need the grand total columns. So let me remove grand totals from the pivot table. So I do a right click there. I go to pivot table options. I go to totals and filters. And I uncheck the boxes where it says show grand totals for rows, show grand totals for columns. I don't need both of those grand totals. Do an OK. So these grand totals are removed, both for rows and columns. Now the next step is, given this null hypothesis that mu men minus mu women is equal to 12.5, I would do an appropriate difference in means test. So I'll be using a utility called the data analysis add-in for Excel. So I go to data analysis. In one of the earlier courses in the specialization, we had also mentioned if you do not happen to see data analysis in your spreadsheet, how do you make sure that you do see the data analysis tab when you click on data? So if you do not see a data analysis tab, please kindly refer to one of the earlier lessons and one of the earlier courses in the specialization. So once I click on data analysis, I scroll up and down till I find these three t-tests. T-test pair 2 sample for means, t-test 2 sample assuming equal variances, and t-test 2 sample assuming unequal variances. We have talked about the equal variance and the unequal variance test. In a later lesson, we'll talk about the paired test. So in this case, we'll begin by performing the t-test 2 sample assuming equal variance test. So we highlight that test, do an OK. A dialog box opens up, and let me erase whatever is there first. So this dialog box first asks me what to be put in variable 1 range. Now here I'll put the heights data for male athletes. Why male athletes? Not because it is there earlier than the women athletes, but because in the null hypothesis I have mu men minus mu women. If in the null hypothesis I had mu women minus mu men, then the variable 1 range would be the data for women athletes, and variable 2 would be data for men athletes. So it is critically important to look at your null hypothesis, and that determines the order of variable 1 and variable 2. So in this case, variable 1 is the men data. So I select all the men data. I would be using labels. My labels box is checked. So when I select data, I'll select including the label M. So I select this entire column. And similarly, variable 2 range, I do a C4 through C1, 4, 4, 2. So that's my variable 1 and variable 2 selected. The heights data for male athletes and women athletes. The hypothesized mean difference. Again, take a look at your null hypothesis. You have mu men minus mu women is equal to 12.5. So my hypothesized mean difference becomes 12.5. So whatever number is there, whatever numeral is there on the right hand side of the null hypothesis, that's the number that goes in the hypothesized mean difference column there or tab there. Alpha, the default value is 0.05, so we do not change it. And then I select any empty cell in my existing worksheet to put the output in. So I'll select this particular cell, F6, and do an OK. So this is my t-test to sample assuming equal variances. Let's now interpret these numbers. The very first numbers produced in the table are the mean values, the sample mean values. So the sample average for the men heights is 183.82 centimeters, and for women athlete heights is 170.90 centimeter. You could have also calculated it using the average function in Excel. The sample variances are produced. The number of observations for the heights of male athletes and the women athletes. So there are 771 male athletes in our data, 667 women athletes in our data. An estimate of the pooled variance. Remember, this is an equal variance test. So we are assuming that the variances across the two populations are equal. So this is some estimate of that pooled variance. The hypothesized mean difference. Our hypothesized mean difference is 12.5. Degrees of freedom 1436. In this case, the way the degrees of freedom are calculated is my sample size 1 plus sample size 2 minus 2. So n1 plus n2 minus 2. But again, we don't need to remember that because Excel automatically produces the degrees of freedom 1436. Then we have our t-stat. So what this t-stat is, this is a t-statistic. So this is a t-statistic 0.8541. Then we have our t cutoffs, which Excel calls the t critical two-tail. Remember, this is a two-tail test. So for a two-tail test, the t cutoff is the t critical two-tail. So this is our t cutoff two-tail test. Had it been a single tail test, Excel also provides you an option with that. Remember, Excel does not know whether you wish to do a two-tail or a single tail test. So it provides you an option for a single tail test too, and that is this number here, 1.6459. So this is your t cutoff one tail test. So these are the various statistics produced in the table. So this was our step 2, calculating t-statistic. Step 3 also has been done here of the hypothesis test of calculating our t cutoffs. Now the final step, or step 4, is to make a conclusion, to see if the t-statistic does it fall in our rejection region. In this case, since it's a two-tailed test and our t cutoff is 1.96, now remember, these t cutoffs that this table produces would always be the absolute value of your t cutoff. So if you're doing a single tail test, depending on which side is the rejection region, you either put a positive sign in front of the calculated t cutoff or you put a negative sign. So that's important to keep in mind, that these values, the t cutoff values in the table, would always be positive. So depending on which side is your rejection region, you either put a positive or a negative sign. So in this case, since it's a two-tailed test, my rejection regions are a plus minus 1.9616. So these are my rejection regions. And my t-statistic, which is a 0.854, does not fall in any of the rejection regions. So my conclusion My conclusion is that I do not reject the null hypothesis. And the reason is because my t statistic does not fall in the rejection region. So not rejecting the null hypothesis implies that I cannot reject the claim that on average the difference between the heights of men athletes at the Olympics and women athletes at the Olympics is equal to 12.5 centimeters.
So that was the equal variance and unequal variance t-test for testing differences in population means. In the next lesson, we will introduce a third kind of similar test known as the paired t-test for differences in mean. This lesson introduces the third variant of the difference in means hypothesis test, namely the paired t-test for differences in means. The earlier two variants being the one with equal variance assumption and the other with unequal variance assumption. We use an example to illustrate the test, the paired t-test, and solve for it using the Excel dialog box. The lesson also discusses the kinds of applications where a paired t-test may be used and the kind of applications where it is not appropriate to use a paired t-test. There is also a third category of difference in means t-test. It is called the paired t-test. Like the equal variance and unequal variance difference in means test, the paired t-test also is used when we wish to test a claim around the difference in two population means. However, what makes this test a little different is that there needs to be a sense of pairing across the individual observations in the two samples. Let us illustrate this by an example. You are the training manager for a large organization. It is your job to ensure that training needs of employees are met. One such training need is that of computer skills. You regularly send out batches of employees to such computer skills training organized by a third party vendor. Since the training costs money, you wish to evaluate whether the training is indeed effective in improving the computer skills of employees. You decide to give a standardized computer skills test to employees before they go for such training, and you again administer a similar test when they come back from training. You also set a benchmark that the training would be considered effective if on average the after scores are at least 10 points greater than the before scores. You administer such a before and after test on a set of 50 employees randomly selected from your training pool. The scores of these 50 employees is given in the Excel file training.xlsx.
The first column is the employee number 1 through 50 employees. The second column is the before scores, the scores obtained before the computer skills training, and column C is the after scores for these 50 employees.
To test whether the training was effective, in step 1 you set up the null hypothesis as shown. Mu after minus mu before is greater than equal to 10, where mu before is the population mean of all before scores. That is, if the test was administered across the entire population of employees, what would be the population mean score? Similarly, mu after is the population mean of all after scores. You have samples from these two populations, a sample of 50 before scores and a sample of 50 after scores. You will be using this sample data to make inferences about the difference in population means. Step 2 is to translate this problem onto a t distribution by calculating the t statistic. We need to do this in a hypothesis test, else we cannot solve for the hypothesis. Here, in calculating the t statistic, we need to use the data analysis toolbox of Excel, since we have two population means in the null hypothesis. the population mean of before scores and the population mean of after scores. Let us use Excel to solve for this hypothesis test.
Here the null and alternate hypotheses are as shown. Mu after minus mu before is greater than or equal to 10. That is, the population mean after scores minus the population mean of before scores is greater than or equal to 10. And the alternate hypothesis is that it is not. So this becomes a difference in means test because there are two population means in the null hypothesis. However, notice in this case there is a sense of pairing between these individual observations. For example, this 58, the score before 58 is paired with this 30 score after, and that sense of pairing comes in because it is from the same person. This fifth employee has a before score 58 and an after score 30. Similarly, this 10th employee has a before score 73 and an after score 61. Similarly, this 15th employee has a before score 47 and an after score 45. So the pairing comes in because of the same employee giving you the before score and the after score. So in this case, because of this notion of pairing, because of the sense of pairing, a paired t-test becomes more appropriate. So let's conduct a paired t-test for differences in means. So we go to data, data analysis, t-test to sample for means, a paired t-test paired to sample for means. We are doing a paired t-test test, so we select that test, do an OK. It'll ask me where my variable 1 range is and where my variable 2 range is. Let me delete these numbers first. So my variable 1 range, notice in this case in the null hypothesis it says mu after minus mu before. So the after scores would go in the variable 1 range and not the before scores, even though before scores come before after scores. However, because in the null hypothesis I have mu after minus mu before, hence mu after becomes the variable 1 range. So my variable 1 range is the after scores. So I'll select my labels box is checked. So I'll select my variable range including the label score after. And my variable 2 range is the score before. My hypothesized mean difference is 10 because that is the mean difference that I'm wanting to test around. And I'll put the output in an empty cell E6. Do an OK. So those are the results of my test. Notice it has calculated the sample mean of the after scores, sample mean of the before scores. It's calculated the sample variances of the two set of samples, the number of observations, both are 50. Remember, in a paired t-test, the number of observations in the two samples need to be equal. It has calculated something called a correlation coefficient. Hypothesized mean difference is 10, degrees of freedom is 49. In this case, the degrees of freedom are calculated as sample size minus 1. And since the sample size has to be same across both the samples, you just take any one sample size. In this case, 50 minus 1 is 49. Our t statistic is as calculated, a negative 1.8213. And since this test is a single tail test with a rejection region on the left hand side. Why on the left hand side? Because in the null hypothesis, the mouth of the inequality opens on the left hand side. So we would be referring to the t critical one tail, which is the t cutoff for a single tail test. And in this case, since my rejection region is on the left hand side, my t cutoff has to be a negative value. So I'll put a negative sign in front of 1.6765. So let me put down these numbers here. My t statistic turns out to be a negative 1.8213 after rounding it off, and my t cutoff turns out to be a negative 1.6765. 1.66. Now notice, as mentioned earlier, the t cutoffs calculated in these tests would always be positive because the t cutoffs are calculated as absolute values here. So depending on which side is my rejection region, I either put a positive sign or a negative sign in front of them. So my last step, or step 4, is to draw conclusions. And the conclusion here is that since my t statistic does fall in a rejection region, because my t statistic negative 1.8212 falls in a rejection region which is demarcated by a negative 1.67. So I reject my null hypothesis. And what does rejecting the null hypothesis imply in this case? It means that I reject the statement that the after scores, the population mean after scores minus the population mean before scores are greater than or equal to 10 points. Or in other words, based on the benchmark set, the training is not effective.
Thus, as shown, we reject the null hypothesis that the score increase is at least 10 across the population of employees. The computer skills training is not effective based on the benchmark you have set. A few important considerations while using the paired t-test for differences in means. Firstly, it is important that there is a sense of pairing across the individual observations of the two samples that you are using. You need to carefully look at your data to infer pairing. If there is no sense of pairing, then do not use this test and rather use the equal variances or the unequal variances test. Secondly, if using the paired t-test, then the two samples should have equal number of observations, since the test proceeds by comparing individual pairs of data. On the other hand, using the equal variances or the unequal variances test, you do not need to have equal number of observations across the two samples, since the test proceeds by comparing the overall means across the two samples rather than comparing individual pairs of observations. Thirdly, the choice between an equal variances t-test or an unequal variances t-test for differences in means is for most purposes academic in nature. Rarely would you have a situation where the results are reversed in using equal variance versus the unequal variance test. However, this is not so for the paired t-test. You may have your conclusions reversed in using a paired t-test versus either the equal or unequal variances t-test. Let us consider our data in the file training.xlsx once again and do the analysis using an equal variances t-test.
We had done this test using a paired two sample for means test, and our conclusion was that we rejected the null hypothesis, or in other words, we concluded that as per the benchmark set by the company, the training is not effective in increasing the computer skills of the employees. Let us now do this test again using a t-test assuming equal variances. So I go to data analysis. I'll choose a t-test two sample assuming equal variances. I do an OK. Let me remove whatever I have there. So my variable 1 range, again, because in my null hypothesis I have after scores minus before scores, so variable 1 range is the after scores, so I select the after scores. My variable 2 range is the before scores, so I select it including the label because I have checked labels. My hypothesized mean difference is 10. Alpha, I use the default value of alpha, and the output range, I put the output range here next to my earlier table of results. Do an OK. Now notice the t statistic that has been calculated is equal to a negative 1.5109. So let me copy it here. If I round it off, 5110, and my t cutoff since this is a one-tailed test with rejection region on the left hand side, I pick up the t critical one tail, and as mentioned, these values are always positive when producing the table, but I know that my rejection region is on the left hand side, so I put a negative sign in front of that, negative 1.6606. So now my t statistic does not lie in the rejection region. So my conclusion is I do not reject the null hypothesis. Or in other words, based on the benchmark set by the company, I would conclude that the training is effective in increasing the computer skills of the employees. So now notice, while using the equal variances tests, our results do get reversed as compared to using a paired t-test. So one has to be very careful when choosing between the two tests. In this case, a paired t-test is more appropriate. Why? Because a paired t-test proceeds by comparing individual pairs of observations. It will compare the after score with the before score for individual employees and then come up with an overall judgment whether the null hypothesis can be rejected or not. While on the other hand, an equal variance test, or for that matter an unequal variance test, compares the overall average of the after scores with the overall average of the before scores and then comes up with an overall judgment whether or not to reject the null hypothesis. So in this case, we get a reversal of results depending on the choice of difference in means test used. And we would have, had we used a t-test for difference in means, assuming unequal variances, we still would have gotten a reversal of results.
As we saw, our conclusions may change based on a choice of a paired t-test versus a non-paired t-test. That is either the equal variances test or the unequal variances test. So it is critically important to convince yourself of a sense of pairing in the data before using the paired t-test. In the next lesson, we will work out some more applications to help clarify the usages of these differences in means tests. The following two lessons give you some more practice with applying the differences in means hypothesis tests. An application using the store sales data file is worked out in this lesson. Let us work out a few applications involving the differences in means t-test. A quick recap of the differences in means test before we work out applications. A difference in means t-test comes into play whenever we wish to test some claim about the differences between two population means. For example, we may wish to test whether the average customer satisfaction from service companies in the US is greater than that for service companies in Europe. We would then get customer satisfaction scores from a sample of companies in the US and Europe and do the differences in means test. The Food and Drug Administration may want to test the claim that out of the two new treatment regimes for a particular disease, one regime is more effective. For this, a sample of patients could be selected to receive the first treatment regime and another sample for the second treatment regime. The outcomes from the two samples of patients could then be compared using a difference in means t-test. You may wish to test that the average productivity of women employees is greater than that for men employees. You may wish to check the claim by a business school that on average, business graduates with a major in finance earn $10,000 more than other majors. The list of such differences in means applications can be endless. There are three kinds of differences in means t-test. The first major differentiation is whether the application allows for a paired t-test for differences in means. For this, there needs to be a sense of pairing between two individual data points across the two samples. If there is a sense of pairing, then we use the paired t-test for differences in means. Else, we use one of the two non-paired t-tests, either the t-test for differences in means assuming equal variances across the two populations, or the t-test for differences in means assuming unequal variance across the two populations. So, that gives us three kinds of difference in means t-test: a paired t-test, t-test assuming equal variance, and t-test assuming unequal variance. Let us take a look at an application. The file store sales.xlsx contains sales data for an online office supplies store in Canada. The online store sells office products to various customers across 13 provinces in Canada, and we have data for 4 years in the file.
This file was also used in one of the earlier courses in the specialization. The very first column in the file is an order ID, an internal identification mark given to the orders, the order date in the format of month, date and year. If you wish to change the format, you can always select the column, do a right click, format cells, category, go to date and change the location to English UK. Do an OK. It will change the order of date from month, date, year. It would change it to date, month, year. But in this case, let us revert back to our original format. So, I will undo the change. Next column is an order priority. The store attaches some priority to various orders, such as a low priority, a high priority, critical, etc. The order quantity, how many, what quantity of orders came through, the dollar sales for that particular order, shipping mode by the company ships either through express air, regular air, delivery truck, the shipping costs, the province to which the product was shipped. So the company, this online office store, services 13 provinces in Canada, 13 states or provinces in Canada. The customer segment to which the product was sold, the order was sold. The company classifies its customers into various segments such as consumer, small business, corporate, home office. The product category that was ordered, furniture, technology, office supplies. There's a subcategory within the product category, the container in which the order was shipped, and the shipping date. So this is how this data is organized.
We can think of this data as a sample from a large population, where the population can be thought of as sales data for all the years that the store has been selling office products across Canada. With this sample data, in which we have sales data across various days in the 48 months across the 4 years, we wish to test whether the monthly dollar sales across the province of Alberta and British Columbia are the same. In other words, we wish to check if there is any difference in monthly dollar sales across these two provinces. We will be making this inference using the 48 months of sample sales data we have. This is a difference in means test, where we wish to test for difference in the monthly sales across Alberta and British Columbia. Before we proceed with this difference in means test, we need to appropriately set up our data in Excel, and we can use a pivot table for this setup.
Given this sales data, what we are interested in is in finding out whether the monthly dollar sales across Alberta, the province of Alberta, is it any different from the monthly dollar sales across the province of British Columbia. Remember that we have data for 4 years, which we can think of as a sample from some larger population. The larger population being all the months across various years that this office store has been selling its products across these provinces. So from that population, we have a sample data which covers a period of 48 months or 4 years. And given this data, we wish to find out whether the average monthly sales across Alberta, are they any different from the average monthly sales across British Columbia? Remember, we are not really interested in this particular sample of 48 months. Okay? We can exactly calculate what is the difference in sales across this sample of 48 months. But our real interest is across the whole population. And hence, we need some sort of a hypothesis test to test this. However, before we do a hypothesis test, we need to organize this data appropriately. And we'll be using a pivot table to do that. So I go to Insert, Pivot Table. I select my entire data, which is from A1 through M8400. I'll place the pivot table in a new worksheet. I do an OK. So a pivot table template is produced with the pivot table field list on the right hand side. So I need to organize my data in terms of monthly sales across provinces. So I first pick up my province variable and drag it and place it where it says column labels. So Excel goes into my data and figures out there are 13 provinces and places them across these columns. Let me reduce the column widths. Let me also increase the fonts, the zoom level. So next, I wish to put sales across these various provinces, and in particular, I wish to put monthly sales. So first, what I do is I pick up the order date, drag it where it says row labels. So in my template now, my row labels are every day that a sale was made. But I do not want daily sales. I wish to have monthly sales. So I would group this row label into monthly sales. So I do a right click anywhere on that particular column, go to group, and I'll group it by months and years. If I only group it by months, what will happen is across all the 4 years, it will group all the months together. That is, it will only have 12 months, January to December. It will not differentiate it in terms of years. While I do want a differentiation across years, that is, I want 48 months, not just 12 months. So that is why I'll group it by months as well as years. Do an OK. So now notice in this column, I have my row labels are January through December for 2009, January through December of 2010, 2011, 2012. A total of 48 months. Next, now I'll drag the sales variable and place it where it says values. So what Excel has done is Excel has placed the sales, and in particular notice it is the sum of sales, not the average sales, but the sum of sales. That is, this number that you see there, $61,597.99 was the total sales in the province of Alberta in the month of January 2009. Similarly, this number there, $54,293.56 was the sales in British Columbia in the month of December in 2009. So now I do not want the other provinces. I wish to only concentrate on Alberta and British Columbia. So I would remove the other columns. To do that, I go to column labels, click on that down arrow tab, and instead of all the provinces selected, I'll select only the Alberta and British Columbia province. Do an OK. So all the other data for other provinces gets hidden. I only have Alberta and British Columbia. Further, let me reduce the number of decimal points to just 2 decimal figures. So I select this entire data, do a right click, format cells, number, I have just 2 decimal points. Do an OK. My decimal points are now just 2 decimal points. I do not really need the grand total columns. So what I'll do is I'll remove the grand total columns. For that, I click anywhere, do a right click anywhere on this pivot table, go to pivot table options, totals and filters, grand totals, uncheck the 2 grand total boxes. That is, I do not want grand totals for rows, neither do I want grand totals for columns. Do an OK. So now I have my data in a format where I can run a differences in means test. The 2 samples are the monthly total sales across Alberta and the monthly total sales across British Columbia for 48 months from January 2009 to December 2012. So given this data, these 2 samples, now we'll do a differences in means test.
Step 1 of the hypothesis test is to formulate null and alternate hypothesis as shown. Mu Alberta is the population average of the monthly dollar sales in Alberta, and mu BC is the population average of the monthly dollar sales in British Columbia. The null hypothesis is that the difference in the 2 population averages is 0 versus the alternate hypothesis that the difference is not 0. Remember, we are interested in the differences in population means, which we do not know. However, we have a sample of 48 months from that population to make our inferences. Step 2 of the hypothesis test is to use Excel to calculate the t-statistic and rejection regions for the t-statistic.
Given the null and alternate hypothesis, this is a difference in means test because there are 2 population means in the null hypothesis and we are wanting to test something about the difference between the 2 population means. Further, notice that this is a 2-tailed test because there is an equal sign in the null hypothesis. So what that means is when this problem is translated onto a t-distribution by way of calculating a t-statistic, there would be 2 rejection regions for the t-statistic, one on the right hand side on the right tail and the other on the left hand side on the left tail. So let's do this test. We go to data analysis. Now we have a choice of 3 tests. We could either do a paired 2 sample for means test, a 2 sample assuming equal variances, a t-test 2 sample assuming unequal variances. The choice between equal variances tests and unequal variances tests is more of a subjective choice, as was discussed in one of the earlier lessons, and we could always do these tests, either the equal variance or the unequal variance test. However, in this case, we could also argue for a paired test, a paired t-test, because there is a sense of pairing across the 2 samples, and that sense of pairing comes across because this number $61,597.99 is in some sense paired with the corresponding number for British Columbia, which is $35,684.20, and this pairing comes about because both of these sales occur in the month of January of the year 2009. Similarly, for example, the sales $52,791.42 in Alberta has a sense of pairing with the corresponding sales in British Columbia, which is $44,297.90, because the sense of pairing comes across because both these sales happen in the month of September of 2009. So one could argue that there might be some macro factors which equally affect the sales in Alberta as well as British Columbia depending on the period of the year, depending on which particular month it is. For example, some months may be lean sale months, some months might be high sales months. Some months might be holiday season, some months might be maybe beginning of a financial year month. So depending on these months, the sales could vary, and that variation could be equally affecting sales across the two provinces. So one could argue for a paired t-test. In this case, however, you will find out that either of the three tests, the conclusions remain the same. So what we'll do here is we'll demonstrate the paired t-test, and I'll leave it as an exercise for you to confirm that the results do not change even if we use a equal variance test or an unequal variance test. So we go to data analysis, a t-test paired to sample for means, do an OK. It asks me for my variable 1 range and variable 2 range. So my variable 1 range is the data for Alberta, because in my null hypothesis I have mu Alberta minus mu British Columbia. So my variable 1 becomes data for Alberta. So I'll be selecting labels. So I select my Alberta data including the label all the way down. My variable 2 range is the data for British Columbia. Again, I selected including the label all the way down. My hypothesized mean difference is 0, because my null hypothesis says that the difference between the two population means is 0. So the hypothesized mean difference is 0. Since there's no mention of alpha value given, I'll choose my alpha value to be the industry standard, which also is the default option used by Excel, which is 0.05. And I'll put the output range in an empty cell out here, any empty cell in your spreadsheet. Do an OK. So this is the output that is produced, and the numbers of interest in this output are firstly the t statistic or the t stat, which is a negative 0.9999, and since this is a two-tailed test, I would be looking at the t critical two-tail, which is 2.011. So what this tells me is that there are two rejection regions. The rejection region on the right tail is any number in excess of a positive 2.0117, and on the left tail the rejection region is any number less than a negative 2.0117. So these are the two rejection regions in my t distribution, and since the t statistic, which is a negative 0.9999, does not fall in any of these rejection regions, hence I conclude that I cannot reject my null hypothesis. That is, mu of Alberta minus mu of British Columbia being equal to 0, this cannot be rejected given the evidence in my data.
So as shown, we do not reject the null hypothesis that the difference in the two population averages of monthly dollar sales across Alberta and British Columbia is 0. In other words, Alberta and British Columbia generate similar monthly dollar sales. Continuing our aim to gain more familiarity with the application of differences in means hypothesis tests, we work out another example using the age data from a sample of first year MBA students across various business schools in the United States. One last application to wrap up our study of the difference in means hypothesis test. The file agedata.xlsx contains age data for a sample of 40 men first year MBA students and 40 women first year MBA students drawn from various business schools in the United States.
Column A in the data file is a sample of 40 men MBA first year students and their ages, and column B is a sample of 40 women MBA students, first year students and their ages.
Given this sample data, we wish to test the hypothesis that the average age of women MBA students in the United States is greater than or equal to the average age of men MBA students. Step 1 of the hypothesis test is to set up the null and alternate hypothesis. Here the null hypothesis is that the population average age of women MBA students is greater than equal to the population average age of men MBA students. That is, the average age across all women MBA students is either greater than or equal to the average age of all men MBA students in the United States. The alternate hypothesis then is that the population average age of women MBA students is less than that of men MBA students. This is a difference in means hypothesis test, and we will use Excel for the next step, which is to calculate the t statistic and rejection region for the t statistic.
The null hypothesis we had mentioned was that the population average age of women MBA students is greater than or equal to the population average age of men MBA students, and the alternative hypothesis is that that is not so. However, while writing the null and alternate hypothesis, we write it as mu of women minus mu of men is greater than equal to 0, rather than writing mu of women is greater than equal to mu of men. The reason being that on the right hand side of the null and alternate hypothesis, we need to have a numeral there, because when we use the Excel utility to run this hypothesis test, we need to put in a value for the hypothesized mean difference, and that is why it is important on the right hand side of the null and alternate hypothesis we have an actual numeral there. So let's do this test. In this case, out of the three options that we have, a paired t-test, a test for equal variances, a test for unequal variances, clearly there is no apparent pairing between the two samples, because, for example, this age 28 has no sense of pairing with this age, this women first year MBA age of 27 years. Similarly, for example, this particular age of a particular first year MBA student, a man MBA student 30 years, has no sense of pairing with the corresponding 24 years for some women first year MBA students. So we really cannot use a paired t-test in this case. So that leaves us with either the option of a equal variance test or an unequal variance test, and we could use either of the two tests. So in this example, while demonstrating, I'll use an equal variance test, and I'll leave it as an exercise for you to try this test using an unequal variance assumption. So we go to data analysis, a t-test, 2 sample assuming equal variances. Okay. Now here it is really important, what do you choose as variable 1 range and what do you choose as variable 2 range. So let me erase this data there. Because in my null hypothesis I have mu of women minus mu of men, so my women data comes before the men data in my null hypothesis, and that is why my variable 1 range would be the age for women MBA students, and variable 2 range would be the age for men MBA students. So I'll be using labels. My labels box is checked. So variable 1 range, I'll select the column of the ages of women MBA students, including the label age underscore women. So that's my variable 1 range, B1 through B41, and my variable 2 range would be the ages of men first year MBA students, the sample of 40 data points. My hypothesized mean difference is 0, and here I put in whatever number is on the right hand side of my null and alternate hypothesis. And so again, since no particular value of alpha is given, we choose the default value, which is 0.05, and I'll put the output in an empty cell in my spreadsheet. Okay, so this is the result, and my t statistic is this highlighted number, which is a negative 1.7937. If I round it off, 38. In this case, this is a single tail test because I have a greater than equal to sign in the null hypothesis, and since it is a greater than equal to sign, that is the mouth of the inequality opens on the left hand side. Hence, my rejection region is on the left hand side. And since it's a one-tail test, I would be looking at my T critical one tail. And as was mentioned in an earlier lesson, the T critical one tail would always be a positive value in this test. So depending on which side is our rejection region, we either put a positive sign in front of it or we put a negative sign in front of it. So in this case, since my rejection region is on the left hand side, because in my null hypothesis I have a greater than equal to sign and the mouth of that inequality opens on the left hand side, hence my rejection region is anything which is less than a negative 1.6646. So any number which is less than a negative 1.6646 would fall in the rejection region. And since my T statistic, which is a negative 1.79, is indeed less than a negative 1.6646, so my T statistic falls in the rejection region. So my conclusion is that since the T statistic falls in rejection region, hence reject H0, the null hypothesis. And since I reject null hypothesis, what it implies is that the population average age of women is not greater than equal to the population average age of men, MBA students. Hence, since I'm rejecting the null hypothesis, I accept my alternate hypothesis, which says that the population average age of women first year MBA students is less than the population average age of men first year MBA students.
As seen, we reject the null hypothesis that the population mean age of women MBA students is greater than equal to that of men MBA students in the United States. Thus, accepting the alternative hypothesis that the women ages are less than that of men ages for MBA students across various business schools in the United States.
Hypothesis testing is a useful tool across different businesses. There are different claims you may want to test, such as whether your machines are producing as expected or whether a training provided to employees is useful. In addition to determining whether the claim itself is rejected or not, hypothesis testing can also help you manage your budget better. If you find that in fact scores after the training are statistically significantly higher than the scores before, you will know that the training was a good use of your money and you will be likely to offer it again for new employees. Hypothesis testing allows you to use data to influence some of your decisions as well as your budget.